Andrea.
Just said that this conference is going live. He's pushing it to introduce.
Yes. It's just no, I think it's anyway, now so you get from my
So this probably
Because you see this little microphone for the online speakers. So just don't let the one last question to be counted. Otherwise,
is don't give me microphone after this session, okay? Before.
Yeah, sure.
that's all.
Yeah, better.
It is what local speakers. It's so later part.
Okay, so I guess we can start. So next speaker is Mikael Shapovalov, and he's gonna talking about wildfire.
Yeah, thank you very much. Thank you very much for the organizers for this meeting, for invitation. So I'm going to talk today on wild-invariant undecided particle gravity and explain why I think that it may be essential for quadratic problems and for strong CP problems. And the work I'm going to talk about is recent that was submitted to our files in June, and it was done together with Georgios Karananos, who is at LMU of Munich, and Sebastian Zell, who is at London University in Belgium. Okay, so I will start from some introduction, which will explain you why I think that Einstein gravity is a very interesting theory, and it may have an interesting relationship to particle physics. Then I will explain why I think that wild symmetry may be an essential ingredient in theory of gravity and also in particle physics. Then we will come to Einstein's wild-invariant theory, and I will tell you why I think that we think that this theory can be the key for solution of strong CP problem. And later, I will discuss here inevitableness. So Higgs mass is really related to quadratic problems. Yeah, the HML masses I will explain later what HML are. And then I will tell you that I think that this theory also is very interesting from the point of view of Euclidean formulation that will allow a transparent Euclidean combination. Moreover, the path integral in this formulation may suffer from the conformal factor problem. And then they come to the conclusion. Okay, so what was right? So there are different points of view about this theory. Okay, Einstein was saying that this is not an ordinary force, and it's not associated with particle physics. It's very far from it. It's a property of space-time geometry, and the proper name for that is geometric dynamics. Okay, and yeah, so historical approach to gravity is that you start from the principle of equivalence, and then you develop a geometrical viewpoint. That there are many arguments in favor of this point of view. There is solid experimental evidence at astronomical and human size distances in favor of this approach. There is mathematical beauty. Well, if you go this way, then at the end of the day, you want to create some unified theory, okay? Gravity, particle physics, forces, etc. And then if you follow this direction, then you should geometrize, so to say, all other forces like electromagnetic forces, electroweak theories, etc., etc. So that's one possibility. You've seen already this type of picture. And one of the talks we said, no, gravity is nothing special. Okay, it's just particle physics. Just electrodynamics. So what we are describing there is just another entity. Okay? In particle physics, we have spin 1, particle spin 1/2, whatever spin 0. Right, just you have spin 2 graviton, that's it. Okay, and geometric dynamics it's not fundamental, so to say, simply low energy fluorescence, just low energy description of this generic particle physics thing. Okay, and this point of view is also very successful. Okay, so in particular, argument in favor, if you say, okay, I want to construct a unitary Lorentz invariant quantum field theory of spin 2, you are coming to lower energy gravity. That's the Weinberg has shown. Okay, so we can go even further, and people will go even further in this direction. In particle physics, the lab have very much gauge interactions. Okay, we have different global symmetries, and we want to make this global symmetries local. And that's a great idea, which allowed the construction of the standard model of particle physics, QCD, where all these global symmetries were gauged. Okay, so the actual question is, can gravity be considered as gauge symmetry? So the answer is yes. And this gentleman, Kibo, Yama, demonstrated that. So you can gauge the correct group, and that gives you a description of gravity on the same footing as the standard model. Okay, so for me, that looks very attractive. Okay, and this is the point of view which I'm going to take. Okay, so gravity is just a gauge symmetry of the Lorentz group. We want to gauge all the global groups which we have had, so to say, confirmed. So how gravity as a gauge symmetry is constructed? There are two fields. So one is T12, okay, which gives potential 16 degrees of freedom, 16 fields. Then we have spin connection, omega, okay, which potentially gives you 24 fields. So these indices A and B are Lorentz indices, and Greek indices are associated with the space-time. Okay, and omega AB is a gauge field of Lorentz rotations, and the top is a gauge field of translation. Okay. In this way, the whole group is gauged. You have two different field strings. So the one associated with the Lorentz field curvature. Okay, and then there is another field which is associated with the tetrad, which is torsion. And then you just take this object and you go a curve, as we used to do in particle physics, with all gauge groups which we have. So we construct different invariants. If we are talking about lower order invariants, lower order terms of dimensionality. Okay, so this is the first one, and this is the second one, F2. Another object, mathematical, which is also very convenient in different computations. You have torsion. So here I define torsion with one Lorentz index and two space-time indices. You can lower and upper indices with the help of tetrad. You can define several irreducible components of torsion. So one will be called vector torsion, another will be called axial torsion, and this will be tensor. Okay. So these are lowest order invariants, and you can say, hey, we have this lowest order invariants, and so we can construct the lowest order action. Again, lowest order, meaning that I'm taking the operators of lowest dimensional. And then this is how the action will look like. You have a massive parameter, a blunt mass, then you have one invariant, another invariant, and then there are several quadratic invariants associated with solution. Okay, so this is the most general action here in this solution. Okay, so you look at this action, you analyze it, and then you find out that's 2 out of potentially 40 degrees of freedom happen to be propagated. So everything else are different constraints. Okay, so this theory is written here. It looks a little bit scary, maybe in comparison with the Einstein action, which is simply R, is nothing but Einstein action. But it describes absolutely the same physics and no deviations, nothing. Okay.
So all this A, B, C, D, it's a coefficient.
Yeah. Yes. All these guys, which are here, A, B, C, D, are just numbers, and other stuff are different vectorial structures, which you have there. Okay, so let's make one more step. You localize the Lorentz group, but let's add yet another symmetry, okay, so initially, as you know, Weil symmetry was introduced by Weil to describe electromagnetism with before, okay, logically, but still, this is a very interesting symmetry. So why is symmetry is interesting? If you have a Weil invariant theory, then it's flat space limit, you get conformal symmetry, and I'm going to distinguish this notion. Okay, and conformal symmetry was first discovered as a symmetry of 3 Maxwell equations. So it's an interesting symmetry. It's also symmetry of the standard model, classical standard model, if mass in the Higgs boson is put to 0. And if we are considering flat space time, then conformal symmetries are very interesting and are special. Just mathematically, if you have a theory which is conformally invariant, then this symmetry restricts a lot of form of different correlation functions. Okay, it's the set of theories which are very helpful and indispensable to describe the behavior of any system in the vicinity of critical points associated with phase transition. It's to describe limiting behavior of different kinds of field theories deeply in UV and in infrared domains of energy. And CFT theories without infinities. As I already mentioned, if you have the Lagrangian of the standard model, then at the classical level, it is invariant with respect to conformal transformation, and that's very interesting because this is a symmetry which can impose Higgs mass in this room.
Which you mean wide seams, not physical.
Conformal. No.
Formal is different.
Yes, this is what I want to ask. What's your definition of right?
Yes, I will. You will see in a second. So even maybe I can even write here.
So is it multiplication
okay.
by general factor of the
While symmetry, say in GR, will be multiplying G mu by some factor of its functional factor, and corresponding to different fields are multiplied by this factor with different weights. So this is what I'm calling Weil symmetry, and I will tell you what is the Weil symmetry for Einstein confound. When I'm talking about conformal symmetry, I have in mind flat space-time, Minkowski, and then this is a symmetry which has, in addition to Poincaré dilatations, plus 4 special conformal transformations. So this is 15 per meter group. Okay, so conformal, when I say conformal symmetry, this is global symmetry. It's only defined in Minkowski space-time, but Weil symmetry is a global symmetry of dilatations in different, which are different in different space-time points. Okay. again, if we are talking about Minkowski space, and if we are talking about CFT, then here the ground state energy is equal to 0. And this is also very interesting because we know that cosmological constants.
I have a naive question. So, I mean, if gravity has a dimension for nothing, why did you talking about? I mean, Young is G.
No,
G.
the thing with we show it's not well invariant. Before I will come to well invariant here later. So if you have a general relativity, whether the exclusive Planck scale, this theory is not well invariant.
In a new theory of coupling, you see
And my theory
doesn't have gravity. The standard model is without gravity.
yeah. Okay. But we'll come to that. Okay, so let's try. We started from Einstein quantum gravity, and let's see what is going to happen if we require that our Einstein quantum theory is violent. So we have to see how different fields are transforming, and here is the transformation. So tetrad is just multiplied by omega. And in metric formulation of gravity, that corresponds to the metric multiplied by conformal factor. Okay. The gauge field associated with the Lorentz group not changing. Axial torsion is not changing. The tensorial torsion is changing in this way. Yeah, what is interesting is that the vector torsion is changed in this way, which is like a billion one field. Okay, and that's a great thing. Why this is a great thing? That means that in Einstein quantum gravity by itself, you have possibility to consider gauge invariant Lagrangian by making your derivatives long and using the vector torsion as the gauge field. So we don't need to introduce anything else. It is already. And now we are going to construct more general violent invariant action. Okay, so I want to have it containing not more than 2 derivatives. More or less normal requirement. And while analyzing the different structures, you can find out that there are 10 different structures which are constructed from the curvature and tetrad, which have dimensionality 4, and so they can be used for construction of violent invariant theory. Okay. In general, this type of theory contains many propagating degrees of freedom, and it's pathological because of ghosts. And that's why we decided to consider only a subset of these theories which do not contain ghosts at any parameters. And this subset of theories is given here. You take one invariant square, another invariant square, or the cross. Okay. Yesterday, I learned that maybe we shouldn't scare folks. So explain to us that maybe that's all fine. Okay. Now, I was thinking about that, and I realized that everything we are going to say from this point should be applicable to this case as well. So all the benefits of the theories, which I'm going to discuss here, would survive if the ghosts are treated in a way they don't introduce any problem. But okay, what I'm going to show now is that I take just these 3 guys. All the ghosts anyway, they have very large masses. Care about them, and then if you have this type of theory. Then this theory is nothing but Einstein gravity with cosmological constant and with 1 extra degree of freedom. Okay. So how do you see it?
And what is it?
This F, this were different curvature. So this is F, this is the first one. So this is analog of R, if you want, of scalar curvature. And this is some special guide which appears on our website.
Such just this this is up by
Yeah.
this is and down.
Yeah, I will show actually the formulas so you will recognize what are these guys.
And at the moment, you do not impose any sign restrictions on the C, B, and C.
No, that's a very good question, and I will come to that today. It will be important for the
your theory of constructing Kibble and Yama is actually only violent, only Lawrence, no violent if you wish, but Lawrence would actually drop my career. On the goals. Your field lines are like probably like gauge fields. As negative E's. If you're going to transform.
Well, there are two symmetries in this theory. There is local Lorentz plus general polarity.
Yeah, fine.
But no translations are in this in general polarity.
But you gave up like already. You gave up local like you started with it.
Yeah, you're right. So it's Lorentz, but the translations are hidden in general polarity.
If you don't want to give up the local translation symmetry, you do it in its longer story.
Yeah, okay. Yes, there are further generalizations of gravity. People discuss monetaristic. No. The previous Lagrangian is not allowed because it violates Lagrange's limit.
Okay.
Yeah. So I just said, I just gonna try to consider theory, which is Einstein Cartan, which is invariant under this two symmetries, plus one extra, which is Weisenberg. Okay.
I mean, I thought it's still that. Related so any of that is not correct. I mean, sorry. I mean,
Well, I think it's actually what that's you will see Charnow. I was asked some questions. I suppose I didn't give it a little bit. Okay, so I will take away cross term because it's not essential at all for what we're going to discuss, because it can be added, no problem. And so this is the theory I want to look at, which is invariant. And Slava, so these are expressions for you, how F and F tilde are associated with the things which we have in metric notation. So F contains R, and then some derivatives of vector torsion, some square stuff, and F tilde, it contains derivative of axial torsion and some others.
And the extent you come here.
The extent term will come from the first term. Eventually, you will see the second. Okay, so once you have this theory and you see squares, you want to simplify that, and then there is a trick, you introduce Lagrange multiplier, and so this action is equivalent to that one. So there are two auxiliary fields, pi squared, and there is field phi, and so if you integrate out these guys, you will get the previous. Okay. Now, this theory is well invariant. Let's fix a gauge, and I will say that this field pi is simply m blank over 2, and then that will be a gauge fixed Lagrange. Okay.
But this is from top here from where?
From nowhere.
It's just gauge fixed.
Check gauge fixed.
But you still have a metric G theory? No, it's not that.
metric G should reproduce as a product of ease so everything is dynamical at the moment. Everything is dynamical, metric is dynamical. So this is an equivalent action in this gauge. And then you want to simplify it with this whole classical theory. So you write equations of motion for all fields. Some of this equation of motion will not contain derivatives, so there are constraints. You resolve the constraints, and this is what we find. Just maybe one comment here. So I produce this parameter f and f tilde. So since we are standing in front of the field string square, so it's natural to call them cutting costs like Young's field. After doing all this algebra, you find that the vacuum energy is proportional to the gauge coupling times m blank to the fourth, and the gauge coupling f tilde determines the scalar max, which is left in this theory. And so very, very small, extremely small couplings are needed for this theory to be viable. But this is interesting also because the topological constant in this node is nothing but
Completely confused. So you start with the action which is quadratic in capital F and capital F tilde.
yes.
And it would seem that you from exclusion of torsion in terms of connection in terms of metric, you would one would expect to get quadratic in the curvature Lagrange. It does not. So how comes that the quadratic in curvature terms? Roughly speaking, F was a curvature.
Yeah. No,
How F squared becomes
you have an equation of motion for phi. Phi says that phi squared is orthogonal is proportional to r. If you insert it back into the Lagrangian, you will get r squared.
You get rid of the curvature square term like
Certainly.
Are you getting rid of the curvature square term like that?
There is no doubt.
And well, you have combinations of curvature square and curvature dual square. Now, it depends on the combination you take. If you have the right combination, you'll construct out the name. And that will get rid of the curvature square term.
Okay, so what I'm saying is something which is extremely simple. Take F tilde. Okay, so you see here there is this auxiliary field phi. Equation of motion for phi says that phi is of the order of F tilde. You have inserted F tilde back, you get F tilde squared.
The problem already appears in the first line, because in the previous line you had a square, and here in the first line you have only F. So
Yeah, and then tries to go.
Sorry, going to not advice frame, but getting rid of the one scaling freedom in place of the.
Okay, this tree is kind of formed if you see this type of interaction, okay? And it allows you to solve it in a simple way. However, you can get all these results without introducing auxiliary. Yeah, without auxiliary fields on some, without auxiliary field phi, and without auxiliary field phi.
Third order equation.
And you can replace chi square by capital phi. You will get this. It was introduced.
You have to take into account equation as well.
Sorry.
Phi has an equation, cubic equation.
No. Phi is Lagrange multiplier. Okay. What? No.
That's not imply.
So there are no derivatives of phi.
It's not the Lagrange multiplier.
When people was very Well, okay, it's.
Let me continue. Okay, so this was a technical trick which allows to solve the theory and simplify it, count the number of degrees of freedom, etc., etc. There is nothing deep. What is interesting is that you have this gauge couplings, and this gauge couplings must be very small for theory to be viable. Okay, you can add fermions to this theory, also in a wild invariant, and in Einstein formulation, and this is written here. Okay, again, so we're looking at G is just determinant of E. You have covariant derivative, which contains the Lorentz group gauge fields, and then there are other couplings which are allowed between vector and axial current with the axial torsion. So vector torsion doesn't have this coupling because vector torsion doesn't transform in a homogeneous way with respect to wild transformation. Okay, you can understand it more with the theory. Again, no problem. In a gauge invariant way, it's important to use wild invariant derivative, which contains distortion. This is how the part associated with the Higgs field looks like. So again, no dimensional coupling, nothing like that. There are several non-minimal coupling of field H with F, field H with F tilde, H with different parts of torsion. Anyway, so all these terms are wild. You integrate out all non-dynamical degrees of freedom, and we look at resultant theory. So I guess if I have higher other terms which contain those, this part remains intact. Okay. So let's concentrate on the physics of the scalar field, which appears in this case. I will consider this scalar field by all dimensions. Okay, so this field has kinetic term, then it has a mass term, and then it has a coupling to divergence of axial coupling. Okay. Because this field has divergence, coupling to divergence of axial current, this is the field that is axial like current. Okay. And so in particular, it gets mass not only at the tree level, which is written here, but also due to PCB. Okay, and it has all the properties of the axiom except this term. Now, if the mass coming from gravity is smaller than the mass coming from extreme dynamics, then this field moves up like an axiom and is also responsible. Okay, and for this to happen, this coupling must be very small, okay, of the order of 10 to the minus. So the gauge couplings in this theory are extremely small, and well, this goes along the lines of different claims saying that gravity is the weakest force. So yes, here the gravity is the weakest force. The gauge coupling associated with gravity, two gauge couplings associated with gravity are extremely small. Okay, this is about solutions of the problem, and I can compare it with the traditional way to solve long QGC problem with PJ symmetry. As you know, in QCD, there is one unnatural number, with the angle, which is a order of 10 to the minus 10. Now, if we have PJ symmetry, which is introduced specifically to solve CP problem, then the known models which do that, KSVZ or DFSZ, they contain 6 new degrees of freedom. and actually two continuums. So one of them is the ratio of electroweak and Peccei mean scale, and then yet another one is the quality of Peccei mean symmetry. So we introduce all this stuff to remove one dimensional number, and it's not clear what is the need of EQ symmetry besides solution of strong equal. Whereas here, it follows this degree of freedom is in gravity, and I'm saying for a formulation afterwards. So I think this is more economic solution. Okay, there are extra benefits here. So one of them, you can do a computation and find the Higgs mass, which is induced by all these effects. And the Higgs mass is written here, and it also contains this gauge coupling constant of gravity, which must be small because it's associated with cosmological effects. So this means that the mass of the Higgs boson at the free level is very, very small. And that means since mass of the Higgs equal to 0 is a fixed point of normalization through evolution of the Higgs mass in this theory, this means that the Higgs mass is computable in terms of other parameters. And sometime in the past, we proposed a mechanism which can do this job, which is associated with some instantons which appear in the gravity Higgs sector, which may lead to the non-perturbative contribution to the Higgs mass, which is exponential minus action. This is action times energy. Yes.
So I hope that you're doing this more. So to that. But probably speaking, this one was a scale which should reduce by half. And now there is a tunneling which seems to abuse the scale in a sense.
Yes. Yeah. Tunneling is the right word for that. It's a question, but yes, there are some non-perturbative. That would be. I'm not claiming that we're able to compute this parameter X. Okay. Also, at this time, we didn't know about this formulation, so it was somewhat different type of theory, but it's kind of resistance proof that gravity might happen to lead to exponentially small contributions to that. Okay, then. I'm not going to discuss how this happens because that would be a topic on another seminar. Yet another thing which was kind of bothering me and which is associated with the extension of the standard model and neutrino sector. So this is the standard model. There are no right-handed neutrinos. If you have right-handed neutrinos, then you can solve simultaneously all problems in neutrino physics. You can explain dark matter in the universe. You can explain baryon symmetry of the universe. So you solve all the problems of the standard model. And there is always a question: what is the mass of this right-handed neutrinos? So these are my mass. So in this theory, which I am talking about, at the tree level, this mass is equal to 0. So there is no way to do this mass. I find that this is a benefit. This means that this mass we should be able to compute this mass. If you are smart enough, or if you didn't manage to do so. I would expect that this mass must appear because gravity normally leads to breaking of all global symmetries. So I would hope that this mass can be generated non-perturbatively, though I have no idea how to do any reliable computation. Okay, and this is the last point which I want to discuss here, and that's related also to a great question about the signs of different terms there. So Einstein-Cartan gravity allows very easy and transparent continuation of the theory to Euclidean space-time. So what you do basically, you are introducing I in the places where you see 0 Lorentz intervals in different quantities. So for instance, This happens with E, so this happens with omega. And so Euclidean action of Einstein-Cartan gravity looks like this. So if these guys F and F tilde are positive, then the path integral formula doesn't exist if it diverges. Okay? And this was in principle the case, which I considered previously. However, there is nothing wrong if you take these couplings to be net. And then our previous discussion also goes through the principle up to so this means that we can start with a theory where these guys F tilde and F are negative. And then the Euclidean action have a sign which gives you formally a conversion pattern. So there is no problem which we have in the Einstein graph for this type. And so whether that will understand something that's an open question, but I find this an interesting feature of this thing. And so I'm coming to my conclusions, and I'm actually quite this time. I think that while invariant Einstein-Cartan gravity is an interesting theory with the following properties, it has one extra scalar degrees of freedom, axiom-like particle, in comparison with the standard model or neutrino standard model. The cosmological constant, free value of the Higgs mass, and gravitational induced out mass are all proportional to gauge coupling of the Lorentz group, which are required to be very small. And that perhaps may lead to non-perturbative generation of the Higgs mass with computability. The same for H and L. Euclidean action is bounded from below for specific choices of gauge coupling constants. Perhaps in this case, we have no problem with conformal part of the metric. And of course, there are many local problems which are currently under investigation. Cosmological application, so what kind of inflation we can have to have Higgs axis inflation, whether we induce temperature perturbations. Of course, this type of theory, the axion dynamics in the early universe is completely different from that which was considered in page 8 case. And we are looking at that now. There is a question about quantum anomaly. It appears there. The theory is not normalizable by standard method, but maybe if we don't separate hosts, we can conclude that with other terms, then this question. So, this. Thank you very much.
Like 1 second.
That was very interesting talk. I have a couple question. Is it the case that this mechanism you started with the action which is roughly quadratic in the curvature, but then you get to the action which and the curvature plus 1 scalar. This mechanism is it roughly equivalent to the mechanism of Clausius-Stravinsky model, this quadratic scalar curvature term? Can we represent it as Einstein plus 1 scalar cube? Is it roughly equivalent mechanism?
Well, I wouldn't call it equivalent mechanism. However, if I add, suppose that I forget about while invariance, let me make a long answer to your question. Okay, so here I was talking about while invariance. We can ask ourselves, suppose that I get the rate from this requirement, and instead of requiring while invariance, I will just require scalar. Okay, scalar invariance for me is a global symmetry. What is going to happen here? Answer: all conclusions remain the same, except one. We will get one extra degree of freedom, which will be a D level. Another scalar height, which was gauged away here, will stay. Okay. Now, I can add that. Now, let me get rid of. Fine tuning. Okay, I get rid of file symmetry, now I get rid of requirement of scaling patterns. Then the terms which are linear in R all meet, and then we are coming to Stravinsky theory. Okay, then again, all conclusions which I said are there. And you still add an extra axial-like particle. You have Scaleron as Alex had. So everything remains in force.
Can you get also the wide square term?
This is a question to Kelvin and to.
I'm going to agree with that, Rail, that you have fourth order differential equations, or we can use Ostrogradski 1850 and so forth and rewrite it with an auxiliary field, not a Lagrange multiplier. So, and either way, it's same dynamics, that's fine. But you have fourth order equations, which you can rewrite as a couple of second order equations. You're welcome to do that, but you have the concept. Those equations also have, solutions to second order equations inside their solution set, but they also have the higher ones too. Fourth order ones.
And so not for the state. If we don't add, if we are going to add wild square terms and all other things. No, here, no, because this is if you have rules. No. Once you introduce this auxiliary fields, phi and I, if you get plus.
No, that's a sense of Ostrogradski. That's just rewriting fourth order in terms of a couple of seconds.
Yeah,
You're welcome to do that.
Yeah, but you will
The
get
theory
which is
same thing. Do that. But it's the same dynamics.
It's the same dynamics, and this dynamics is fully covered by the way I described it.
If you go back to the formalism.
These are absolutely equivalent things. These are absolutely.
Actually, your f squared is not f mu squared. It's just
It's f squared. It's the whole stuff squared.
the whole stuff squared. So
Yeah,
it's
it's
a
like-
scalar square.
It's like FR theory of gravity.
Riemann square. It's just a scalar square. For this reason, he gets the Riemann on the.
This is FR theory. Some.
That's why.
I want to ask you, what are the between charges of torques in your model?
There are no indications in charges.
Okay.
Yeah.
So how does this particle communicate with QCD?
Yes, it communicates to precipitation.
That's a constraint.
So this is the terminal impact. So based on this derivative here, I did write a chart which was associated with the standard method fields. I also wrote some D, which is associated with the ground. So D don't have to be supplemental. Speed is 1:1.
So there's another couple between A and
Yeah, yes, this happens here. No, there are no those. So there is a couple between axle and vector cars and axle. Vector cars and axle are minus from more to all that is.
okay, so
If you start on the general scale environment, I sort of theory. You integrate out the connection. That is what you can do.
Yes.
Any degrees of freedom that are canonical. What kind of theory do you get? The most general scale invariant natural theory?
It will not be most general. Okay.
But we do be scale invariants.
Yeah, so if I draw values, there are
It's more general.
Yeah. If you just have scale invariants,
Yeah.
then there are more other terms which can be added to that. Okay, so for instance, here in Fermat parts, I'm on this page, you will get also interaction of vector torsion with this guy. That is going to be a lot.
And there are no dimensional full parameters.
There are no dimensional parameters. In other parts, which is where okay. So here you will get a bunch of other terms. So for instance, here I use covariant derivative of H, which contains vector torsion. If you have just scale invariance, this is not the need. You can use normal derivative, but then you can have interaction of H with vector torsion or other terms in some way. But still, in this case, if you are using this type of action, which is a polynomial in H, and which doesn't allow, say, curvature downstairs. Okay, so everything is polynomial in gravitation. Here's the thing. Then the statement that the torsion can integrate out remains in force. You will simply get more complicated action in the Einstein frame.
And it's very much.
Yeah, well, I do is yeah, it's going to stay like that, and in particular, you will get one extra degree of freedom, which is so then if you just have scale invariance, then of course this type of gauge knows, and the height will be dynamically visible. So in this case, you will get two scalar fields in addition to standard form. One will be dilaton and another.
Okay, most general
Yeah.
transition was taken by a theory plus the scalar.
Yes.
Okay, that's good.
We focused on the scale of the freedom of there are formula vector and not. And I understand that in your model they don't they're not dynamical because you have chosen a particular ground.
Yes.
But you expect that to be stable when you want to correction.
Well, quantum corrections I can consider here as being psychoactive problem. So there will be other terms generated, in particular higher order curvature terms. But yes,
I expect that they are of the same order if you were
yeah, but we are not going to change this one.
So you're just focusing on this as a particular example.
Yeah, so for me, yeah. Okay, of course, there is an aspect after what happens with this theory in fact finite domain, and this kind of comes. But if I don't worry about ghosts, right? I thought that this terms is not happening really because
Yeah, but you know, there is a discussion in the literature whether this torsional theory suffer from a strong coupling problem at the perturbative level. So have you checked whether at the gravity part? Have you checked whether this problem appears in the problem usual?
well, for this particular theory, we are working with that. Okay, however, this question was studied for theories without R square. Okay, and this is a question which appears when you study inflation, etc. So you can find corresponding outlaws, you can find the domain of energies. Then if you ask physical question, for instance, whether inflation occurs or not, of course you have to do all this program. We did do this program without R square, studying Higgs inflation, but we are working on that.
I think we, last question.
Maybe comment on the stage.
Well, I said that this is the thing we are working on, but there is
Maybe a question like.
myself wrote a paper some time ago saying that the viral normal is tells that the while symmetry can persist. Just scale invariance persist, but while symmetry cannot persist. This statement is not necessarily true here because of the following reason. Because the main, so to say, point of our analysis with Anna was that if you make a wild transformation, then Euler density changes in a non-trivial way. Anyway, if you make wild transformation and natural formulation of gravity, then many things like curvature, etc., they do not transform homogeneous. There are some pieces which are associated with derivatives of the wild transformation. Okay, and in Einstein-Cartan formulation of gravity, the realization of wild symmetry is different. So, for instance, the curvature f here and f tilde, they transform uniformly if you make conformal transformation. So this means that the question of wild invariance should be reanalyzed here. And so in particular, Gauss net term also transforms in a homogeneous way. So it's not the case of that may happen to be different, but I can't tell you what is going to happen here.
And if you have no one advanced problem, is it will break your construction?
You are potentially prepared because we are working.
Sorry. Thank you very much.
Do something on the metric perspective. Something in metric G. Right? Remember the G, it's not the end of the formula.
That's just the pure line square.
Yeah. So G is if the determinant of G is E, I think it's my E squared.
No any other. Very nice.
If the theory is normalized, but when your bounce is such a hard.
Sorry?
If your theory is normalized, so your bounce is that.
I'm bounded to.
Depends where you're writing.
As example,
You have no zero functions, you're not.
No. The statement was that if you have non-zero ether functions, then there isn't necessarily a wild normal. This is not the case. Okay, so there is a way to construct theories. And this is a very simple way, actually, which tells you that all these terms are out. The way how to do that is the following. The anomaly you are talking about appears because your regularization, quantum computation, breaks scale invariance. So, for instance, if you do dimensional regularization, then you introduce two parameter mu, which breaks this invariance. And then because of the loops, you have one over epsilon times epsilon star, which gives you, okay, a changing way of your computation. Instead of introducing the parameter mu, introduce dynamical field. In this case, that is the field. Okay, and then you can show that all these wild normal terms which you are talking about disappear. Then this part of anomaly is dealt with.
Okay, we need really to close, so let's thank the speaker again. Now, the next speaker, Laudao Shuku. So it's gonna talk about
This
bounce cosmology.
this and this is like this mix of this. This is what we call
Okay, can you hear me? You should hear me because I have three microphones. Yeah. So it's very I'm very happy to have this opportunity to talk here and thank the organizer to give me such an opportunity. And today I want to talk about some series of work that I have been performing with my collaborators in some maybe nearly 20 years, a long time. That is, I'm focusing on bouncing cosmology, and the current topic is based on this works and collaborated with these people. So some of them are here, and some of them supposed to be here is not here. So anyway, so I will give you I will try to give overview of the bouncing cosmology that we are developing, and we will talk about the problems we confronted and the possible solutions which to these problems. So this is the brief outline. So first of all, I will just give a preliminary introduction of the Big Bang and the inflationary scenarios, and then I will focus on the bouncing cosmology. So I will show why we have a bounce and then the problems and solutions. So as we know that nowadays the current cosmology has developed very much, and there are a lot of more and more experiments that becomes more and more accuracy, and also the theoretical parts also have a lot of development. Then it allows us to touch the areas of the cosmology that have been out of reach. So one of the one of such an area, I think, is the very early stage of the universe. Maybe even before the BBM or CMB. So it's a very early. So that stimulates us to ask the question. So what will our universe be like in its early stage? Because the early stage of the universe provides us initial condition of the current universe. So in order to understand the current universe as better, so I think it is necessary to find more information from this early stage, or even you can see that as also known as the childhood of the universe. So in the textbook, I think everyone knows that in the last century, in 1948, the people such as Gamow and his collaborators invented or proposed the theory of our universe called Big Bang theory. So this theory starts with claims that our universe starts with a very hot and dense region, and then explored everywhere. And the expansion experienced nearly 14 billion years, and with this the hot temperature get cooled colder and colder and become our cosmic microwave background. And also the relics of the Big Bang becomes the galaxies and the structure, the large scale structure. So this is a very simple, very easy understanding theory, and it's also very famous. And the Big Bang theory is but the Big Bang theory is both successful and unsuccessful. So it is successful in terms of that it can predict many things. For example, the age of the galaxies, and also the redshift of the galactic spectrum, and also the helium abundance, and also the most important prediction is the cosmic microwave background, so the same temperature. However, the Big Bang theory is also not successful because it has so many problems called flatness problem, the horizon, and unwanted relics problem, and singularity problem, and so on. So it has many problems, so it is not a complete theory. So in order to solve this, or in order to get rid of these problems in the last decades of the last century, people proposed a scenario in the early universe called inflation scenario. So inflation means that in the very early universe, in a very early stage, the universe experienced a very fast acceleration in very short time period. So its scale factor is like this. So in a very short time period, it expands many times. So by such a rapid expansion, the inflation can stretch the space-time to a very large volume, and and also it can dissipate all the matters and curvatures to a very small to a very small amount. So by this mechanism, the inflation can solve the horizon problem and the flatness problem, and also the unwanted relics problem. So everything becomes diluted. Addition to that, the inflation also can have a mechanism for the structure formation by decohering the fluctuations to primordial perturbations, which is to form the galaxies and large scale structures. However, because the inflation happens after the Big Bang point, so it cannot solve the singularity problem. So singularity problem is still there. So what is the singularity problem? So this problem is proposed in the so-called singularity theorem by Hawking and Parents and so on, essentially in 1970s. It claims that our universe will inevitably meet a singularity point, either in the past or in the future. It will meet the singularity point if it satisfies these two conditions. One is described by general relativity, and the other is satisfies non-empty condition. So the singularity means that in a finite time point, the scale factor of the universe goes to 0. Therefore, the energy density and temperature and so on blows up, gets diverse. So this is the singularity. And because our universe is expanding, so it's very natural that this singularity happens in the Big Bang point. So the Big Bang point is a singularity. So this is a singularity problem. Of course, there's in the current conference we heard about many talks about quantum gravity. So maybe people will claim that in the very early universe, the quantum effect will be robust. But here I just turn off this quantum effect, I just assume that our universe is totally classical. So if so, the singularity will be there. Then how to solve this singularity problem, or how to avoid the singularity? So in in a classical universe, and if we restrict ourselves in four-dimensional space-time, there are at least two scenarios that is non-singular. It avoids singularity. One is called bouncing scenario. It means that the universe, we assume that universe is very large in the very beginning, and then it can contract to some single minimum. The scale factor contract to some single minimum, but not zero, and then bounce back and go into the expansion area. So in this scenario, there's no singularity because in the bounce reading the scale factor is not reaching zero. So this is one possibility of getting rid of the singularity. And the other possibility, actually, we have heard in the robots talk yesterday, that is emergence scenario, also or genesis scenario. It means that the universe starts with a very static it starts with the static status, and then gradually expands and into our expansion. So this is also non-singular. So there are only two. There are at least two scenarios, two possibilities. And in this talk, I'll focus on the first one, namely the bounce cosmology. So as I said before, the bounce cosmology requires the scale factor goes from so it decrease and then reaches some minimum and then increase. So what is the condition? What is the condition of how to realize such a bounce cosmology? So from this very naive sketch plot, we can see that for the contracting case of the universe, the Hubble parameter is smaller than zero because the scale factor is decreasing. And then in expansion phase, the Hubble parameter is larger than zero. It requires very naturally. It requires that in the bouncing point, the Hubble parameter will have a positive time derivative. So this means that from the equation, from the Feynman equation, this means that the rho plus p, the energy density plus the pressure, it will be smaller than zero. This means what? This means that the non-energy condition is violated. So this is consistent with these singularity theorems proposed by Hawking et al. So in order to realize that, we need to violate the non-energy condition. Okay, so of course this scenario is very simple, but in realizing, in getting a realistic bouncing model, a bouncing scenario, will meet many problems. So this I will share with you the problems in constructing the bouncing models. So first of all, in the background level, I think the very serious problem is the so-called anisotropy problem. And in the perturbation level, we have several problems. That is the scale, how to get the scale invariant spectrum, and also we found that some bounce models have a ghost instability, and also there's some gradient instabilities and so on. So what are these problems? And how can we get rid of these problems? So in the next part, I will discuss in detail of these problems. So the first problem is the cosmic anisotropy problem. So what is anisotropy problem? So as you know, the initial usually we do the cosmological background. We usually take the FRW metric, which is which is in principle isotopic and homogeneous. But for the realistic method, it's always it is always possible to have some anisotropy. So it is very hard to exactly exactly make the all the directions totally isotopic. So there always have a little bit anisotropies. So if the metric is not exact isotopic, means that there's some anisotropies. The anisotropy will be described by such a factor. So the scale factor in different in different directions is not exactly the same. So in the Friedmann equation, this anisotropy will appear here as an additional energy density. And then this we can also get the equation of motion of anisotropy like this. So it gives that the effective equational state of the anisotropy is +1. So it means that the effective anisotropy energy density will scale as a scale factor a to the -6. So in expanding universe, it is fine because the anisotropy will decay very soon. So for example, in this picture, when this purple line is the inflation where the energy density is remains constant, but the anisotropy will decay soon. So it will not be dominant. So nobody cares about the anisotropy, but it will be problem in the contracting phase where the anisotropy will grow soon because it is equational state is very large. So as long as the background of the contracting phase have the equational state smaller than +1, it will be overwhelmed by the anisotropy. So we will get a very we'll finally get a very anisotropy universe that cannot bounce to the expanding one. So this is somehow a serious problem. So it requires that we need the contracting phase with the equational state larger than 1. But this actually this is not so difficult to solve because we just need the contracting phase with large equational state. This is realized in 2004. 2001 by people like the Curie and Overloot and Steinhardt and Turok. And they proposed the idea of the apotheotic universe. Although the apotheotic universe comes from string theory, but you can reduce it into 4-dimensional space-time, and we can have such a effective potential, which is have a minus sign in front of it. So the effective potential is negative. So this will give rise to a large equational state, larger than 1. So it is very simple. So we put it there and we discuss other problems, and then we will go back to it later. So anyway, so it can be realized that the equational state is larger than 1. And the second problem of the Gaussian series is how to get scale invariant Hall spectrum. It is known that our CMB observation favors a nearly scale invariant Hall spectrum of the early units. This is the newest data, newest related by the Planck and Bicep and Beck in 2021. So it seems it shows that this of course the constraint on the tensor scale ratio is tightened to the 0.03 something, but the spectral index of the Hall spectrum, the spectral index of the perturbations remains nearly 1. So it means that the primordial perturbations will have a nearly scale invariant Hall spectrum. It is very easy to realize the Hall spectrum, nearly scale invariant Hall spectrum in expanding phase, namely inflation. But in order to get such a spectrum in contracting phase, where the fluctuation is generated in contracting phase, we should calculate the perturbation equations, also known as Mukhanov-Sasaki equations. That's ours here. So when we solve the equation, we'll get two solutions, two branching solutions. One is constant and the other is growing. So in expanding phase, one is constant and the other is decaying. So here the growing mode will dominate the solution, and we can calculate the Hall spectrum and spectral index, and we find that in order to get a scale invariant Hall spectrum, the equation of states should be nearly zero. Okay, it's different from the expanding case where equation of states is required to be -1. So in expanding case, sorry, in the contracting case, we need the equation of states nearly zero to get scale invariant Hall spectrum. Okay, so this is proposed by David and Robert in some 20 years before. In order to illustrate, we showed some numerical calculations, and we did indeed we get some scale invariant Hall spectrum in the bouncing in the matter so-called matter bounce scenario, which have the equation of states is nearly zero in contracting phase. Okay, so these two it's fine that these two these two problems can be solved separately and very good. But if we put together, we'll find a problem. So in order to solve the anisotropy problem, we need the equation of states larger than 1. But in order to get meet with observations, we will have an equation of states is nearly 0. So the equation so the equation of states of the contracting universe is large or not large. I think this makes some controversy, inconsistency. So how to solve this inconsistency? So here we propose two mechanisms. One is called the entropic mechanism. That is, we have to have another field in contracting phase to generate the primordial Hall spectrum, while the background keeps the equation of states is larger than large equation of state. So the other mechanism is so-called bouncing inflation. So we have a bounce inflation period after the bounce. So and the perturbations that is observed by CMB is supposed to be generated in inflationary error. So it will not ruin the bounce, which is supposed to be solving to solve the anisotropy problem. So it is a bouncing inflation. So we have two mechanisms to solve this problem. So I will return to these two mechanisms later. So the third problem is the ghosting instability problem. So as I mentioned before, in order to realize the bounce, we have to violate the non-empty condition. But in field theory, we know that the non-empty condition violation will cause a ghost instability. And the very famous example is the phantom field. In phantom field, there will be a minus sign in front of the kinetic term in the Lagrangian. So this minus sign will be called as ghost mode. And if you calculate the Hamiltonian, you'll find that the Hamiltonian will have a minus sign in front of it. That means that the energy state of this phantom field is negative. So it will be unbounded from below. So it will be more and more negative. So it will this problem, so it will not be stable. So this is called ghost instability. In general, in a field theory when non-condition is violated, we will have such a problem. However, in 2008, people including Alex, so they proposed some field models, field theory of the Galilean theory, and it's later extended into the generalized Galilean. So the Galilean theory, it can also be equivalent to the Hornetsky theories proposed in 1970s. So the Galilean or Hornetsky theories have several parts of these Lagrangians. It's a little bit complicated, but this Lagrangians, the essence of the Lagrangians is that it introduces some box problem, the box terms, the higher derivative terms, braided into the kinetic term. So by such a design, by such a company, it will have some nice properties, such as the Lagrangian will have a higher derivative, but the equation of motion remains the second one. So it means that we will have a more degree of freedom, but only one of the degree of freedom is dynamic, and the other degree of freedom is not dynamic. It's a constrained degree of freedom. So in background, we can violate the non-condition, but this theory is free of ghost. So making use of these nice properties in 2011, we proposed some bounce models with Galileo theory, and we discussed about the ghost instability, and we find that the correlation is indeed the ghost free, because this kinetic the factor in front of the kinetic term, namely P, is always positive. It's always positive. So this is a ghost free model. And taking into account the previous two issues, namely the entropy issue and the scale event issues, we can get some improved models. One of the models is the multi-field bounce model, which is proposed in 2013 by me and Manus and Xian Gao. And our model is like this. So here is the Galilean term, which is the kinetic vector braiding term, and we have the negative potential in order to solve the anisotropy problem. And to generate the primordial conditions, we introduce another field called curvature. Here is curvature. But this curvature is not a minimal coupled curvature. This curvature is coupled to the Galilean field via these vectors. So in Kentucky case, the minimal coupled curvature is cannot give rise to scale event output. But if we introduce such a interaction, it will make the curvature field itself in the inflationary error. So it can give rise to a nearly scale invariant oscillation with K dependence almost zero. So here are the plots of the equation of state. This equation of state is larger than 1, showing that it can solve the anisotropy problem. And this is the QR is positive, so it can do not bring the ghost. So the second model is the bounce inflation model, where we put some inflation error following the bounce after the bounce. So here we make a more complicated Lagrangian, and here we can find from the numerical calculation that maybe sorry, this is not very clear, but after the bounce, the equation of states is stays in the value of -1 for a very long time. So here is the inflationary region. And then we calculate the power spectrum, and we can see that the power spectrum is split into two parts. One is for the large K, one is for large K node. When the equation of state, when fluctuations exit the horizon during the inflationary era, we can get nearly invariant power spectrum, which NZ is nearly 1. But in a small K region, when the fluctuations exit the horizon in a contracting space time, in a contracting region, we will get a blue tilted power spectrum. So this blue tilted power spectrum will give us some bonus on the namely the small L suppression, but because since the fluctuations the perturbation is blue tilted, it is suppressed when K is very small. So it means that we can get some small L suppression. This is observed by the Planck observations as somewhat called the anomaly. On here, we can see that this is the 2015 data, because our work is done in 2015. So you can see that a very small L. There's some data points that tends to be suppressed. This red line is the theoretical fitting of inflation, normal inflation. And this is the newest 2018 data, but almost the same. And this is our fitting of the data. So you can see that normal. Sorry, this is too up. Position is not correct. So this green line is the normal inflation, and this blue line is the bouncing inflation. You can see that the bouncing inflation in a small L, the bouncing inflation goes below the normal inflation line, and then you can fit better to the data. Okay, so the fourth problem is the gradient instability. So in constructing the bouncing models, we found that it is very, very difficult to also have a sound speed square to be positive all the time. We found that no matter how we try, there's also some region where the sound speed square drops below 0. This means that when you calculate the perturbation, you'll find that you will get a blow-up solution. So this is not stable. So this is the so-called gradient instability. And then people prove that if you use the cubic Galilean theory, it is inevitable that this problem will happen. So this is called no-go theory. And then from the effective field theory approach, we find that we find the condition of getting rid of this problem. So this is the Lagrangian of the effective field theory with some coefficients here. And for cubic Galilean, f is equal to 1, and this can be 0. And for more generalized Oleski theory, we can have this m4 squared equal to m4 squared, and this can be 0. But if you beyond Oleski, every coefficient can be not 0. So in order to make use of the effective field theory approach, you can see that if you want to get rid of this gradient instability, you will have the m4 tilde is 0, where the m4 tilde is f plus m4 tilde. So this means that m4 tilde cannot be 0. And additionally, m4 tilde square should be negative because f is positive. So it means that for the condensing theory for cubic for cubic binomial theory cannot be realized. Here is the effective field theory model where we add some effective terms, including M4Q square. You can see that without such a term, the CL square in the green line drop below 0, and for the if we take into account this term will go up, it will be positive both times. And then we calculate the M4 and which indeed that this is drop below 0. So this is how to calculate of this the gradient instability problem. Okay, so this is the last part. So this in the previous discussion we all focused on the field theory, and but another way of realizing a bouncing theory is modified gravity. So this is violates the other condition of the singularity problems, that is generated. It is described by the GR. So if we extend the GR, so maybe things will be different. So here we focus on newly proposed modified gravity called FQ gravity. Or Q is related to the covariant derivative of the metric. So in this theory, we also have some bound solution, and we also check this instability and the power spectrum. So we find that in some parameter space it will be fine to have a healthy loss, but I don't have much time to go into details. So since my time runs out, so I just conclude. So we start with the singularity problem, which is suffered by the Big Bang inflation scenario, but the singularity problem can be solved by bouncing scenario. And also we mainly discussed some new problems and the solutions. And also the avoiding the singularity can be done in modified gravity, but this is still more developing. So I think I can stop here because he's standing here. So thank you very much.
Speaking of multiple data does not say much about the model speed because of cosmic variance.
Cosmic variance, yeah. Yeah, we can say that the fitting is due to the cosmic variance, but if we fix the very center value of this noting, I just said that yes, we can explain this with the cosmic variance, but I just say that in the bouncing scenario, it is possible that we can fit better.
Yeah, but it's not significant.
Yes,
It cannot be significant.
yeah, but I think that maybe with more accuracy of data, maybe we can find something more.
I don't think so.
Okay, so let's thank the speaker.
Okay.
So there are two short announcements. One of them I suggest we combine in 10 minutes since we're going over that. And second, after the next two talks, we will have a group photo in front of this auditorium. And the third one, that I remind you that today we have a dinner at 6 p.m. We will start from here around 5:30. We just 10 minutes walk through the campus, but we will navigate. Don't worry.
I have one picture. Not coming.
So we have another mic. We have another mic, so.
Oh,
you can put this thing.
Well, I have 3 months.
Yeah. This is for the local, the speakers. Yeah. So you should put this thing up because its sensitivity is not that good. Yeah, that will be good. Huh? And this you can put, yeah, it's fine. It's fine.
Should I turn on?
Yeah. Here. Yes, it will take a few minutes before it turns. Just maybe 30 seconds to.
Of 30 seconds.
Yeah, then it will be.
Yes. Okay.
Yeah.
No? Do you hear me? Yeah. Okay. Good.
So yeah, the clip is on the opposite side. So it works like this.
Ah,
It looks like almost.
Okay, so let's start the second session of this morning talk. So the next speaker is Professor Mata from the Hangzhou Institute of Advanced Study. So he will talk about UV extending Higgs integration in Einstein quantum gravity. So let's welcome.
Okay, so thank you. First of all, I'd like to thank you for the kind of invitation. So yesterday I talked about something on integration. And it is a bit more bottom up or phenomenon, but I like to explain why I need to go into something like Einstein quantum gravity, so the Misha explained just before. And so I think that the expression is somehow more or less different from Misha, so I have not understood how I can interpret it in relation to Misha's way, but let me explain what it will be done. So the work is done by Nizifor at the IBS CPU and Kyohei Mukai at Delphi. Okay, so let me start. Okay, so my talk is organized as follows. So first, I would like to introduce inflation, and indeed, I'm not satisfied with the user inflation, and so it is. I say there is some problems in Higgs inflation, and so as I said, I work on some more or less phenomenological or bottom-up approach. So I didn't say I will complete integration, but yeah, I said you will extend. So it is not easy completable, but I say it is it's consistent. Okay. Then I'm sorry. Then the user inflation is analyzed in terms of so-called muted formalism. But now recently people work on targeting formalism and also Misha recently work on formalism. And then so in the meta formalism, we have a good extension, but I also would like to discuss how the Higgs inflation in partially Einstein quantum formalism can be extended in a similar way in the meta formalism. Okay, so let me start. So first I would like to talk about Higgs inflation. Okay, so and we have already had several talks on inflation, so I did not have to explain much. But so inflation is now kind of a key ingredient in modern cosmology. So it solves it is an accelerating expansion of the universe in the primordial universe here, and it solves the horizon problem, bottleneck problem, and the monopole problem. And then it explains the origin of large scale structure of the present universe, as well as explain the same anisotropy of cosmic background. So it's fine. And so first we would like to construct a model of inflation. It is often the case. It is not always, but it is very often the case. We introduce a scalar field and whose potential energy drive inflation. Of course, we have another possibility to have kinetic term driven inflation, but mainly it is driven by the potential term. So anyway, so we would like to know. So first we might think that the standard model fast field have a good candidate of the scalar field that drive inflation. And in order for a scalar field to drive inflation, we have several requirements, such as Planck potential of relatively for the relatively is required. So so now from the bottom-up phenomenological point of view, we will add that so people often think that I thought the standard Higgs cannot be equal, but it is clearly so this is the question. So of course the scale of inflation is relatively high. We think it would be a gap scale or some high scale. So one approach is that it is different from the electric scale. So there are huge energy separation. But the standard model it can be known natural problem and it can be extrapolated up to the large scale. So in this point of view, the question is the standard model is there are technical inflation. It's a very important question for us. So of course, we know that the standard model capability can drive inflation. This is because we know that in the standard model, Higgs potential is well-known double potential or final time potential. So we will have two types of inflation. One possibility would be, of course, neutral inflation, where the inflation starts from the close to the origin and from there. But such a kind of inflation is impossible because the throw parameter around here cannot be small, because that inflation cannot be derived for the model Higgs. On the other hand, chaotic inflation where the field value is much larger than the Planck scale, then the chaotic inflation just for the accelerating expansion is possible. So it will be if we can have the condition where the expectation value is much larger than that. However, the great motivation for inflation is now to explain the presence the large scale structure of the universe and the synchronized entropy. And in this point of view, in this model, if we have the lambda in the Coulombic potential, then the amplitude of the primary base perturbation, it can be served to lambda. This requires, and the observation, as you know, up to 10 to minus 10 and 10 to minus order. So we need to have very small lambda. But for the standard model Higgs, of course, it is order 1 or 0.01 or something. So the Higgs inflation, standard model Higgs ability, it would like to have chaotic inflation. We suffer from very huge Alice problem. So that we can experience this problem can be resolved because so now we do not take into account, so we just put the Einstein reduction and the usual canonical kinetic time and the white bottle time potential. But we could add other potentials that could change the system. So for example, the most popular model would be the nominal coupling to gravity. So if we add at the second time, then so the primary density perturbation can be understood explained by as the Hubble sphere over Planck scale of times c as epsilon in flow parameter. But once we introduce this term, then C can the Higgs value C Higgs h square time become much larger than Planck scale. So it acts as ejected Planck scale. Then so it will suppress the huge primary base perturbation. So it is one understanding in the topological donor plane. Of course, it is also understood by going to Einstein plane, as you know. So that by following such a component transformation, we go to this action, such that then by performing the mechanical by canonically normalize the Higgs field. Field H is transformed into chi field such that we have a canonically normalized potential and isotropic structure. And then so we know that the potential is like this, and this is the potential. So in the Einstein plane, the Higgs potential is flattened, and so that this is the NS and R figure in the same B, and it goes here. Such that we explain if we take C over square root of lambda to the left in that, then we get the total index to be 0.97 and the therapeutic scale ratio for the 0.063. So it is fine. So it is the complex model of inflation driven by the standard model and it is the same data. So far. However, I will add that there are still several problems in this inflation in this inflation. So the first thing is that just after initially proposal in 2008, people discussed the problem in the cutoff state of the problem. So of course the physics should be frame independent, so we should be able to get the same result from the Jordan frame and action frame. But so in the Jordan frame, we have such an interaction such that such a big fluctuation scattering should be the cutoff state related by this interaction, but that we get the cutoff state graph over property. In the action frame, if we take into account the complex nature of the field, we have the several fields such that this time cannot be normalized, but that we get such a contact terms to get the cutoff scale of the macro. So on the other hand, typical energy scale of the inflation is lambda over 4 or Planck over root C. Now root C is 24th order. So this is much larger than cutoff scale. So some people add that in the prediction of its inflation might be unreliable. Fortunately, so the point is that this is discussed the cutoff scale of the vacuum. But during inflation, it has a non-vanishing expectation value such that the scattering is not the one in the vacuum. That we need to think about the scattering in the inflation vacuum. And Misha has shown that the cutoff scale during inflation becomes larger due to the texture value such that it is the So just after around 2009 or 10, so there has been a problem, but people that have thought it might be not problematic. But sometime later, people notice another problem. So indeed, during inflation, the evaluation doesn't occur. But there is another problem. That at the end of inflation. So at the time of after inflation, we have the dissociation phase. And in this point, the Higgs field oscillates around origin, and then we can think about we should think about the behavior of the weak boson or non-voltage boson. They are equivalent up to the high energy momentum due to the non-Goldstone equivalence theorem, but it's different statistically. They have been noticed by energy and the growth study for the people. So the origin is that form. So his death and his time is the other time like a friend in that this and another. So from this interaction, we have the effective mass of the number of mode or the continual mode of the connected. Then the infrared offset H dot becomes almost lambda Planck scale over lambda Planck force over C square. And Higgs becomes almost. So it becomes the effective mass becomes almost Planck scale. So they found that there is such a spiky feature in mass like this. And by analyzing the polynomial coefficient, we will think that by the excitation of this boson or non-boson mode with such a high momentum. So the big number to be root lambda or Planck scale. So the root lambda is lambda is the order 1, so the almost Planck scale energy will be the apparently produced. And its energy density just as dt, we calculate the energy density and it will be the much larger than the electron energy. So then, so this is the Higgs bed and the energy scale and cutoff scale is like this. So that inflation we have and here for we are saying, but now we go inside here. So you get the violation, or I would say at least we can describe the heating stage of inflation of the So this is the problem. So, yeah, indeed, it could be resolved by adding alignment. So we could apparently management operate algorithm like this. Then, and we have already discussed sometime in this workshop that R-square introduce a new scale degree of freedom. So in the Einstein frame, it is apparent that we have the conductor here, but now we have the this current happening such that it will cancel. Such that the other scale goes up to the next scale. So it's fine. And so in this case, so that this model is indeed very similar to the model introduced into the PDX formation scenario. In this case, it is something like a 2P the inflation model. But in our case, the difference is that in this model, the interaction, the nominal coupling has a negative sign, such that in his model, the black scale, effective black scale is decreasing. So the structure is different. And in this model, the inflation becomes something like effective single field model that described by the field that the potential has such a value and the inflation goes down in this line, or it's still from this image. So anyway, the field but along this line, the inflation potential is the same to the Higgs inflation as the cosmological prediction is up to the. Okay, so this has been already, I think, Alberto has pointed out. I'm not sure, but some people have already pointed out. But so this indeed, this interpretation is very natural because we have the like interaction, then we introduce quantum connection to the give rise to R-square time. And but I would like to, so it would be good to analyze it in terms by extracting the conformal mode of the mechanism. So in your analysis, you can analysis and you can analysis they extracted the conformal mode because so sometimes people confuse with the frame dependence of the Einstein frame and Jordan frame. But the essence is that in the Jordan frame, the essential effect has come from the scalar part of the method. It is not originally it is not the physical degree of freedom, but there is not the degree of freedom that is the conformal factor of the method. So we extrapolate it and such that the determinant of the method to be -1 theta. Then with this frame we get alpha. So in this point of view, the sum is non-particle from the summation of the dominant value correction. The theory is conformal. Sorry. Okay. So if we think about just user case, so in the case of n is the number of scalar cases. So in the third model case, it's the doublet, so the degree of freedom is 4, and equal 4. But in this, if the number of scalar degree of freedom is that we have other quantum corrections. But if we take large infinity, then this gives rise to the dominant contribution. Such that we can just focus on it. But if we have structure speaking, if a number of n is not large, we need to take into account other part. Yeah, especially for the practically we can introduce here and but the essential point is that so as we have discussed sometimes that if we have R-square term, we will also have the dangerous Y-square term, such that it will induce the individual. But in this case, we suppose C is very large. So as shown, but the correction for the R square term comes from the scale of Planck over C. But the R revised square term comes at the Planck scale. As a result, there is a energy scale where we can just focus on the scale, but we can neglect the dangerous fraction. So this is the good point of the large C and the large C case. So this is the answer to some more or less initial case, the question to initial outside in the previous talk. So there is answer. So if we have a large C, C is sufficiently large, then we can have the energy scale where effective as the effective field theory, we can just focus on scale term and the dangerous go slide where scale term can be. So it is not this point. Okay, but unfortunately, I didn't explain much, but in this analysis, this good contribution also gives rise to the Higgs mass and the cosmological constant. And in this analysis, the Higgs depth and Higgs mass will be also sent to Planck, the scalar mass Planck over C. So we have the naturalist problem. So this is the reason I'm not satisfied with the metric formula with scale extension. Okay, so let me introduce the Higgs inflation in Caratini and Einstein-Kazan formula. Okay, so I hope you are convinced that, at least in my point of view, Higgs inflation with unscaled with extension is given and free from unitary problem. But it has a unitary problem. So how is the situation inside? This is the question. So and this also says that so unscaled is just with the extension, but not completion. So in order to complete it, then we need to take into account various step time and other time. So such that we need to care about. But at least if we would like to understand inflation, when inflation takes place in this regime, then we do not have to care about the.
So which mode drives inflation? Is it the hybrid model of inflation or one of the other?
Okay, so yeah. So now we have the Higgs field in this direction and the Higgs current direction, and we have potential inflation. Then the delta potential value, and the inflation takes place in this direction. So in this one, the linear combination of scalar and Higgs drive. Yeah. So the Higgs process is also more important than the Higgs inflation or different inflation. But it is a different story, and we are now we have on that, and we are now also working on the case of the Einstein. Okay, so let me continue. So. Okay, so sometime after the proposal of the Higgs inflation, people also studying the Higgs inflation in particular. So so we studied the Higgs inflation in the metric formalism. In the metric formalism, we described the connection to be the repeater or Christopher symbols. But in a similar philosophy to Misha's presentation, so we could think about the connection and the metric. A priori independent quality person. This is the case of the formalism. And with so in the case of just we have Einstein interaction, then the connection is understood to be the auxiliary field, and by integrating out, we get the effective connection given by electricity or Christopher field. But in the case of inflation, we have C is square, and R now is square is a function of the metric and connection. And in this case, the connection is still non-dynamic degree of freedom, and we can integrate out, and we can go back to the, we can go to the formalism with the chemical normalized character. But in the case of this, in the case of the formalism and partial formalism, it is more suppressed and itself, so that we need to have much larger field. So this looks also good, and yeah, so the technical scalation is very small, so it is not the so the semi observation will not be able to see the data propagation associated with volume. But so okay, so but as I said, there are several discussions in the data formally. So let me repeat the same stuff to the funding equation. So okay, so the cutoff space, the theory as a vacuum is already the the Planck over the so the Planck over C is the case of the formalism and scale is in hand metric. And then in this point of view, it is less dangerous than in equation. And indeed, the violent preheating of the numbers model of gauge function is happening. It has being considered with people and non-genetic problem than in equation. But anyway, so in a similar way to study the quantum collection, we can look for how quantum collection generates R-square term. And indeed, possible so that we can add R-square term. But in the case of partial formalism, R-square term do not give the higher derivative interaction such that it does not produce the new degree of freedom, but just it goes to the pH derivative scale. And so by performing a quantum collection, and it does not command mode does not lead to the EV extension. So then, okay, so in this point of view, now the compared to the method formalism and partial formalism, we get to the question. How can we understand the differences? And the natural model of communication. Then so we get to go inside the Einstein problem. So now the similar to partial formalism, we take okay, so in this case the connection and the metric are a priori independent field. And now in the Einstein formalism, we also allow the existence of torsion. And but the reality again is reproduced by solving the equation motion with Einstein integration. And we take into account then but once the equation so integration in Einstein and we can introduce now another term called near term in the generalization of the integration. So now we can add this term and then so and R is the scalar given by the metric and the connection. And then we can and but anyway, integrating out torsion and other non-dynamic degree of freedom. We can go back to the Einstein action in the metric formalism and the chemical normalized and the potential. And indeed, we found that if this C eta is taken to be the same to C here, then it will produce the metric integration. And if we take C eta to be 0, go to partial integration. So this has been posited by initial by tuning C eta, we can analyze the Higgs equation in the Einstein formalism that connect metric formalism and partial formalism in the case. And then now we get to the interpretation as like this. Okay. So how to change this from the two quantum unit and how to quantum correction with surround and how our scale term will be extended theory and how do we have the natural value of the ratio of the scale terms. So this is the question. And then we follow the same analysis. So now we have the T mu is V mu in initial notation, and S beta is A mu in initial notation. But we can perform this the extended theory will conform like this, and then so we can integrate that. So now as we said, this field is non-dynamic integral freedom, and we can integrate out, and then we go to actually in this action, and then so the field met. So now we turn on the conform mode, and then so now the good thing is integrated conform mode is that the transformation is just the field definition of a shift of the field of phi e. So such that the field, we can discuss the field metric like this, and then the scattering actually can be evaluated by the field curvature of the field space. And it is indeed recently we discussing the field theory of some model case. We can have, so by looking at the field metric, we can evaluate the curvature of the field metric, and it is equivalent to the total field. And it is good that, so as I said, the metric, which curvature is field distribution independent part, independent part, so that this shows the frame independence of the total field. And then so we get this result. So you say that once we reproduce the case of the inflation, and once we take the value of R become 1 over root of C, then it goes to probably 1. So we say we get the partition limit, and the R becomes 1 over root of C. Okay, so then you get extension, so let me so that in a similar way, we can perform the control collection to look at what kind of interaction appears. And then, so like this. So this interaction is essential to introduce a new degree of freedom. And you can see, if R equals 0, then there are no kinetic term for omega, such that we do not have the new degree. So in other words, the absence of the new degree of freedom in partial formalism is because R equals 0 in this point of view. Okay, so we can see similar things, such that so again, the large N and large C limit and scale term is appears as a leading order parameters, and then so and the scalar also induced with a mass like this, and the cutoff scale is given like this, so it is enhanced. And the mass and cosmological constants are also still reduced, so the problem is not resolved. But anyway, so let me explain the situation. So now we take, so now in order to explain the cosmological observation, C is not dependent on R, but we take the R to take minus 5 to 1. And so this is the original the cutoff scale of the theory without the contact collection, and this is the infinite scale demonstration. And once we turn on the R scale collection, the cutoff scale of becomes like enhanced like this, and this current mass appears like this. So this means that so in the metric limit, we have the enhancement of the cutoff scale, and it is much larger, it becomes much larger the cutoff scale inflation in this scale, and it is fine. But in the partition limit, the scalar mass appears the apparent scalar mass appears the above the cutoff scale. So the scalar does not make sense anymore. So it is also explained why we do not want the scalar in the partition limit. Okay, so let me know that. So heat inflation in the Middle form is one of the very complicated model, and but it has military issues. And Amsterdam is a natural extension of the theory, and it is solved the several problems. but we have seen the current program, and the inflation current, in fact, the formulation is good, but but we analyze between the point of the item gravity. So we find the so-called protein limit in the item gravity, and we clarify how the difference between the formalism and the formalism appears. Okay, that's all. Thank you so much.
Okay. First of all, let's talk about questions or comments.
Then, is there a simple explanation for why Einstein quantum gravity could connect the other three formula, given that exactly there is more degree of freedom?
So, okay, so one explanation, okay, so it is apparent that for article 0 flow, for article 0, sorry, then okay, so so for article 0, that we introduce the connection. So so at this level, we cannot distinguish between formalism and Einstein character. And then by integrating out this, that we get to the same action for the platform. But for this I did not a clear answer to why if we take C to be the integral, we should be having the answer to this question. By adding me and tan, it becomes the equivalent integration.
Yeah, you can consider different limits of these parameters, and then you really see that there is smooth transition from one. Newton has to look at specific formulas.
So I will ask something about motivation behind that. So all the idea about Higgs inflation was there in order not to introduce a method or take one scalar that we already have. Model and this will drive inflation. Now instead of this inflation, you don't need a scalar, you have this modification gravity correction HGR and this can drive inflation. So what do you do if you consider both of them? I mean, what's the one that's compared to simple inflation?
Okay, yeah, so stability is fine, I would say, yeah. So but anyways,
So are you getting better observables compared to stability?
so in this point of view, so in this model, so the model is different, so the reheating process is different. The reheating temperature is different. So then once this out, so how to do so there is a so if reheating temperature changes this thing. So now this is Einstein model can increase will have a different prediction of this. So in this
better or different, yes.
But so in this point of view, but there are no preference, I would say. So it is distinguishable and the PR has a problem, I would say. In the point of view that we cannot describe the but stability is fine, and I think so. But if we start from the inflation, like see, then the R scale is naturally introduced so that it is, I say it is very easy.
Other corrections you should compute directly in the Einstein formals or in the effective value theory.
Okay, so we did in the effective formula. So after integrating out to torsion, we perform the equal computation.
Can one establish some equivalence? This computation in the Einstein formals or
okay, so what we okay, so Yeah, so what we did is that first going to the method, description in the method formation, and you know, the extrapolate the conform mode and calculate the conform correction. So I think you might wonder that the portions are non-dynamic term, but it could contribute to the correction. This is the worry. For example. Yeah, so it is so I'm not sure if there are some discussion about but yeah, at least what we can calculate definitively is the theory that the method form so but yeah, direct we didn't perform the direct calculation.
Because when you integrate out the money, this is like classical equation, solid equation.
Yeah. But equation motion is a constant, not direct equation, but the constant integration. So, yeah.
So, actually, we find the paper which tells how to do computations in food lowering in Einstein carbon theory. But I don't think it exists the way in this stuff. So it would be a great problem. So
Yeah. So at least we don't know how to calculate without before performing the integrated in other portion. Yeah.
Okay, so last question.
The two field model you showed here, it seems you have curved field space.
Yeah, indeed, so, okay, yeah.
Is that an hyperbolic field space?
So this is a potential, but indeed the kinetic time for the scalar and edge in this description, it is not the current time, and it is curved. So so you might wonder so this is curved so that the exponential mode effect. But we as long as lambda is sufficiently large, the exponential mode is heavy enough, and also the time of the intercontractor is mine, such that there's no problem in the.
Right, I'm wondering about the field space curvature. Is it an active one or is it a positive one?
So there are no instability there, so it will be positive.
It's a spherical field space.
It's a scalar field state. Yes, and indeed, so in our analysis, from the analysis, we also introduced the auxiliary conformal mode, and we need to take into account. So by taking into account with the conformal mode, then the frame independence is apparent.
Okay, so due to the time limits, let's start the speaker again. So our next speaker is Professor Li Jingzhao. He will talk about
Mass.
And this is the details of the
Okay, he will talk about super radiant instabilities of bosons around the BCOs. So let's welcome.
So first, I'd like to thank the organizer for the invitation. My name is Li Jingzhao. I'm from the Carnegie Institute for Astronomy and Astrophysics. And first, I would like to have a disclaimer. I'm a single-minded phenomenologist, and actually, the talk is conference wonderful, but I have to perform for me. And in this talk, I will only talk about the gravity at the classical level. And actually, there are two branches of modified gravity theory. The one with quantum correction, the other actually also have a very large community with the classical modification to the gravity theory. So I will only talk about the classical modification to gravity theory. And this talk is based on some work in cooperation with Richard Greenko from Lisbon, and also my former postdoc, Mai Jiafeng, now he is a faculty in Guangxi University, and also an undergraduate student who is actually the main labor behind this work. He is now going to Caltech to do his PhD. And the outline of the talk is the following. I will first give a brief introduction to maybe students here about the Penrose process and the black hole superradiance. And then I will talk about the gravitational wave atoms. And later I will focus on the exotic compact objects as the alternative to black hole superradiance in some probably modified gravity theory. And finally, I will talk about the gravitational atoms with modified black hole horizon. This work is actually published last year in PRD, and if you have, there will be many details will be neglected. If you have interest, please refer to this paper. Okay, so first the Penrose process. So we know black hole, curved black hole have two horizons. And actually, between the two horizons is the so-called egosphere. Inside this egosphere, there's some interesting things could potentially happen. And one particular thing is the Penrose process. So Penrose process means if there's a particle decays into two pieces, and one piece go outside of this outer horizon, and the other piece go into this black hole. And in this process, if the outgoing particle might have a larger energy than this original particle in the view of an observable at infinity. This is the classical process called the Penrose process, which you actually effectively extract the energy from the black hole. So, but what if it is not a particle, if it's a wave? If it's a wave and there is some correspondence to the Penrose process. If it's a wave, it might be get amplified. If we if there is an ingoing wave and outgoing wave might have a large amplitude AF, might be larger than this AI. This is the correspondence of wave in terms of the Penrose process. But there is some condition to be satisfied if this wave can be get amplified. The condition is that the mass of this omega here is the time evolution this frequency should be smaller than m times this omega h. Omega h is the angular velocity of the horizon. So if this omega h, only if this omega h is large enough to satisfy this condition, this superradiance will happen. If the black hole is rotating too slowly, this process cannot be triggered. In this process, the wave actually extract rotational energy from the black hole, and then the constant energy is conserved. Okay, there are multiple ways to understand this superradiance condition, including if you solve the wave equation explicitly with this time dependence, and you can really find this AF larger than this AI if this condition is satisfied. You can also using some Wronski determinant to relate these two quantities and also get this the same result. And also you can actually use the black hole area theorem to get this result as well. So I will just give an example of using this the third method. All these three methods, they are equivalent to get the same result. I will just use this third method as an example in the following. So the area of a black hole is written in this way, and this R plus is here, and this is the angular momentum. This is the charge, and this A is the angular momentum divided by actually this mass, normalized angular momentum. And if we perform a differentiation, we get the first law of black hole thermodynamics, which is right here. I think many of you are very familiar with this. There we have this omega h here. This is the omega h we mentioned before, and this here is a phi in front of this Q. This is a very simple exercise for maybe for a senior undergraduate student to do this. And if we consider only curved black hole, because later I will only talk about the astronomical black hole, which we expected to be neutral, otherwise they will be neutralized by the plasma around them. And if we only consider this for a scalar wave, we can relate its frequency and azimuthal number m by this relation. And the loss of angular momentum from the black hole and the loss of mass from the black hole also can be read in this way because of this relation. And the differential of the area, which is shown in the previous slide, if you just put the dq equal to 0 because we only consider neutralize the black hole, we have this relation. And it's very simple to observe that if the black hole area theorem is fixed, is required, then we will have in any process we will have this delta A larger than 0, which already gives you this omega smaller than m times omega h as a requirement for the black hole to lose energy. So this gives actually exactly the super-radiance condition for black holes. This is some result well known from 1970s. And also this is interesting, has some implication for the black hole astrophysics. We will see later. Actually, I have related the Penrose process and the black hole super-radiance. Well, in the former process there we consider particle, and in the later process we consider wave. They have some correspondence, but they are not exactly the same. Actually, in Penrose process, we only need the existence of an equal region, where but the black hole super-radiance, we not just need the equal region, but also need some dissipation mechanism at the event horizon, as we will show later. The similarity is also very clear that we need to have negative energy state in this equal region. So actually, this super-radiance behavior requires one more condition, that we need an event horizon or need some other dissipation mechanism in order for this super-radiance to occur. Okay, so this is basically a brief introduction to Penrose process and the super-radiance behavior of black hole. So now we talk about the gravitational atoms. Let's start with this black hole bomb, which was proposed by Press and Tukhilsky in 1970s. So they imagine that if there is some ingoing wave and it gets amplified here, but if there is some kind of mirror outside of the black hole, this outgoing wave will be reflected back to the black hole and get amplified again. So this is actually it's called the super-radiance plus this confinement, which from the mirrors. They will give super-radiance instability, and this wave will get amplified again and again, and eventually this will explode. Like this is the black hole bomb idea in this Nature paper in this 1970s. And actually, but we know there is no mirrors around the black hole. But we can have some other way to get an effective mirror. The most natural way is to have a field of mass mu. The mass mu field can provide some kind of mirror behavior because of this quantum the typical wavelengths of this field, and we have roughly at the wavelengths of 1/mu, we get a kind of a mirror behavior which can reflect back some part of the wave, and which can later increase this field. This is the idea of gravitational atom, and this provides a mass, a small mass of the field, provide some behavior of the middle, and which triggers exponential growth of this field, and which will eventually saturate and form some kind of state which we call gravitational wave, gravitational atom. Okay, this is, and if when the gravitational atom is formed, because of its quadrupole moment is time dependent, because the wave is oscillating and the quadrupole moment is time dependent. This which will introduce some radiation, because a time varying quadrupole moment will introduce gravitational waves. Actually, this is one of the targets for observing gravitational waves. Okay, there are many other methods to put a constraint on this gravitational wave atom. Actually, as I said, the superradiance condition need only if the black hole is located fast enough, this superradiance condition can be satisfied. But if we observe fast rotating black holes which do not trigger this superradiance, then we can put a constraint on this gravitational atom picture. So this is what was did for the past decades. People measure the mass and the spin of the black hole and put a constraint on this gravitational atom behavior. And another kind of thing is, as I mentioned, eventually when this superradiance is saturated, this system will produce some gravitational wave emission. You can view it from some classical point of view, like a time-dependent quadrupole moment. You can also view it via some quantum point of view. Like if you can view this as some scalar, some fields, they are annihilation and also have some level transition, and also maybe in some extreme conditions they will have some the so-called Bosonova behavior, which is very similar to the black hole bomb idea that I introduced before. And this system is actually can be solved analytically because this the potential of this system at a far distance is very similar to a hydrogen atom. This is why this is called the gravitational wave atom in the first place. And the people also perform numerical simulations to evolve this system, and they really observe this kind of level transition behavior, and also the related gravitational wave stream in the system, and which make this kind of system become targets for gravitational wave observatories. Okay, so this is the idea of gravitational wave atom. This can be formed if the superradiance condition is satisfied, and there is ultra light massive scale, massive field. Also now we talk about the black holes. Because I previously assumed there is a black hole. But the black hole is observation. As we know, there are many observations which point to black holes, like the M87 observation by the Event Horizon Telescope. These are normally considered as black holes in general relativity, which means they have event horizon. And the event horizon actually is protects this the world inside the horizon, disconnect this space-time inside the horizon with the outside horizon, and this is the cosmic censorship conjecture. And also, this black hole are very simple object. They have some uniqueness property like the Nobel theorem, which relate the mass or the higher order mass moment to the spin and the mass of the black hole. And these kind of black hole are also actually relatively well understood in terms of astrophysics. We know how this massive star evolve and how they eventually collapse into a black hole. And there are also some phenomena like the observation of this kind of image and also the movement of S stars around this galaxy center. They should be explained by some massive compact object. But however, the black holes, because they are so fundamental in our gravity theory, so we have every right to question it and test it. There are some motivations to consider alternatives to black hole. There are also problems with the interior space-time of the black hole. There are singularities in the classical general relativity. And there are also, as mentioned many times in this workshop, there are also information paradox. And there is also, because if you test this black hole idea further and further, even you get a non-result from the test, you get a stronger paradigm for the black hole picture. Okay, so that's why we want to consider some alternatives to test against the black hole idea. The alternative can be very complicated. But we here only consider a very simple case that only the horizon is modified by this parameter action. This is what we consider in this talk. This is called the exotic compact object. There are some deviation with this epsilon. Epsilon is larger than 0, but very small. There are some deviation like this deviates from the black hole, and even such a simple idea already gave us many interesting phenomena. Okay, as we know, if this object, this compact object, is made from some isotropic perfect fluid and also assume static and GR, we get epsilon larger than 1/8. This is this theorem tells us. And in terms of black hole, this epsilon equal to 0. Okay, there are many studies actually, in particular in recent years, because this picture makes it possible to connect to observations. And there are studies on this long-lived modes and echo signals and also echo region instability. And this is just one example, shows that in gradual waves, after two black holes merge, if there is a modification like in the previous slide here, we could potentially produce the so-called gradual wave echoes, and these echoes are already searched for in the LIGO camera data. And although we haven't, some group have claimed that they have detected something from low signal event, but it's not widely accepted. But the search is ongoing inside the LIGO camera corporation and also for by many external groups. And this is actually, as I said, a very small epsilon can already produce interesting phenomena which can be related to the observation. And if there is a massive perturbation, then the potential of the space-time looks different, and there may be some trapped fields, and also the outgoing fields get modified. This is the idea we want to investigate in this talk, with massive field around exotic compact object. Okay, this is what we will talk in this final section about the gravitational atoms with modified black hole horizon, which is something we might want to study in light of recent observations from gradual waves and also black hole physics. Okay, so in short, a massive field will produce some decay of the wave at the far region, like is proportional to E2 minus kappa times r star. R star is the tutorial coordinate in the black hole totally the coordinate for the black hole. And here, around this this horizon region, this horizon to B region, there will be income and ingoing and outgoing waves. And we want to solve this system. And we want to solve this system in a time-dependent way, not just the static solution to this system, which actually correspond to the black hole gradients that I was talking about earlier. Okay, the problem is very simple. It's just to solve this equation in a modified Kerr space-time with a modified horizon, the event horizon. Actually, you can, of course, to solve this equation, people always assume this answers and input this answers, and you get all the equations. And actually, the angular part is very simple. It's just basically gives you some spin-weighted spheroidal harmonics. You can solve it analytically, and these functions are very well known, even in the Kerr space-time. But for the radial part, is very hard to solve. Actually, we don't have analytical solution, exact analytical solution to this radial part. But we want to understand this behavior, and there are many ways to do this. And actually, this the whole equation they form eigenvalue problem, and the eigenvalue is lambda Lm, and this omega is the oscillation frequency. And in this theory, this equation, this lambda Lm is very close to L times L plus 1. If the spin is small, but the omega actually, if you solve this problem numerically, you will find this omega is not real. It has a complex component, which actually will trigger this is the part that trigger the black hole gradients and the time evolution of the field. Okay, let's try to solve this equation using some approximation. So first, at the far region, the equation gets much simplified, and this equation actually in the far region, as you can imagine, it's basically the problem is exactly the hydrogen atom problem, which we have exact solution in our quantum mechanics classes. And in the near region, the problem is also near this R class is also solvable. So this far region and near regions, we can solve this problem. And here we define a Z parameter, which is basically it's R, it's a rescued R. And when R equals R plus, this is Z equals to 0. Okay, but we want to also have the whole solution because we want to investigate the whole behavior of this this field. And at the some place, if the horizon is modified, and at this modified horizon, there will have some ingoing wave and outgoing wave. Outgoing wave is characterized by refraction coefficient, which we call K. This capital K. This capital K will be very important in our study here. It actually reflects the proportion of the incident wave reflected at this R0. This gives us the boundary condition. And if we want to solve this problem in the whole space-time outside of the event horizon, we need to do some match. And the match is done in this overlapping region, which the near zone solution and the far zone solution both are validated approximately. So this is some approximation to solve this problem, and this can be solved approximately, and we will see how good is this approximation later on. Okay, so by matching these, we actually get some result like this. It's very lengthy, but let me just this blue part is actually already known in 1980s. It's the no result for Kerr black hole. But if we put it in some modified horizon, The only change is this G. G is a function of this K. The K is the reflector coefficient, which is actually a very simple solution. Although this expression is quite long, but this is a known result of the curve black hole, and only the modified gravity only introduced a modification here. This is kappa. Kappa, the explicit expression for kappa is in this way. Here, this P and A are just some functions of the spin and the mass of the spaceship. Okay, let's see some simple behavior on this G kappa. G kappa, when this kappa equal to 0, this is G equal to 1. This goes back to the curve black hole case. When this kappa equal to 1, and which means all the incident waves are reflected, this is G goes to 0, And in between this GK also has some well-defined boundary between this parameter and this expression and this expression. Okay, so this is some plots for this G kappa as a function of this C naught. C naught is the how far you are from this event horizon scaled by the scale by the length scale of the horizon. And you can see there are some oscillations in this log space. And here we have chosen kappa equal to 4.8 for some illustration. And this the dependence of this expression on this spin parameter and all this mu times m. Mu is the mass of the scalar field, and m is the mass of the black hole. And they also have this oscillation behavior. This which is different from the curve case. In curve case, as I said, this G kappa is just equal to 1, which reduces to the curve case. Okay. But when this kappa is very close to 1, and this oscillation actually can get very large. We can see here the volume can be very large, and this can introduce a very quick superradiance behavior, as I mentioned before. This is the analytical method that we use to get this G kappa function, but this is basically approximation. You have done after you matching in the overlapping region of the problem. But you can also do some semi-analytical method, and you use some expression and want to match it with some if you carefully choose this R match, and you use some not only this leading order terms of this the power of R, and you use some special functions. I do not show details here, but you can get a better accuracy in solving this problem. And here I just show some matching in this near zone and far zone for the radial part of the problem. And here I just show this dashed line is basically the black hole, and this solid line is some illustration for the modified horizon. And if we compare this analytical method that I mentioned before, and also this semi-analytical method, which is more time consuming but more accurate. And you can find that they do not differ very much. In particular, when this alpha parameter is small, alpha is mu times n. And also we actually tried another the so-called continued bracketing method, which is a standard method in calculating the black hole spectroscopy. This is very accurate, and we compare this, and we found this semi-analytical method gives better accuracy, and actually it's already very close to the continued bracketing method. And here we also show this omega I as a function of the spin, and this also will introduce this modified horizon introduce some oscillation behavior here, and this changes this omega I in the curve black hole case. And this will actually have some phenomenological consequences that will be relevant to the black hole atom observations. Okay, we also calculated different modes corresponding to different L. This is the angular quantum number, and this the curve case is simple. It's like this is blue curves. And if the horizon is modified, then you will have this oscillation behavior in terms of this as a function of this alpha parameter. Actually, this alpha parameter is very the analog of the fine structure when you compare this graphene atom with the hydrogen atom. Okay, this also shows the symmetric analytical behavior of this omega I for three different topics as a function of this A, is the spin parameter. Okay, this is the analytical solution we get with a very simple modification with respect to the Kerr solution is this G kappa. And the G kappa can be physically understood in terms of energy balance. So here because of the time limit, I will just skip the details and show that the energy balance, because you use energy balance at this boundary, and you get this omega I modified with these two factors with respect to the Kerr solution. And these two factors actually these two factors just give the relative amplitude of the wave function of R naught and also give energy flow across the boundary. These are the two factors that appear in this G kappa function. And this is exact factor. And this CLM is approximated in our analytical solution to this 1 over this blue factor. And if you really calculate CLM, you get this picture. And if you calculate the G kappa divided by this red factor, then you get a very similar plot, which shows that the analytical solution is quite accurate to this level. And so eventually, what will be realized in real life is we want to see this omega I, imaginary part of the time evolution, if they will give some kind of growth rate to the boson cloud. And with respect to the Kerr case, the maximum mass of the boson cloud do not change, but the time scale is changed. So which means the time evolution of the massive field around an exact complex object is different from the time evolution of the massive field around a black hole. And we will see some behavior here, and here we show the mass of the scalar field divided by the black hole mass as a function of time, and they increase as a function of time. For this is the Kerr case increase as a function of time, and in the later stage, this is super radiance, and the super radiance when this is saturated, the black hole emission kicks in, and we can have observable graphene wave emission starting from this point. And for kappa different from zero, we have similar behavior but with some oscillation modification. And we will see what is the implication in real observation in the following slides. And this omega I is modified as I said by this expression. This is GK expression with respect to this Kerr black hole solution, and this the denominator actually is some oscillation function, and on average they will have this behavior controlled by this 1 minus kappa square. And we do some random simulation and show that in most cases this time scale is getting longer with respect to this Kerr case. And this is understood that this Kerr case divided by this 1 minus kappa scale is a very good estimate for the time scale of this exotic complex objects. And this is behavior, I will just skip this, and this is my final few slides. This is the evolution of the boson cloud as a function of time for two different masses, just as illustrations. And as you can see, this is the growth of the boson cloud is the super radiance, and after this, it emits gradual waves. And this behavior are very sensitively controlled by the mass of the boson field. And if we do some analytical, empirical switching, and we can find that there is some faster radiance region, which when the time scale for super radiance times this vector is smaller than the apparition time scale, and this gives us some fast super radiance region. And if we relate this to the mass spin plot, which is popularly used in this field, and this shows the constraint from the observation of the mass and the spin to the super radiance. And this dashed line gives the result for the curve case. And if the exotic complex object, the horizon behavior is modified, you give this bias, which changes the previous constraint. So there are some possibility for the modification to the super radiance with this very tiny modification to the event horizon. So here goes my summary, and we investigate this kind of super radiance behavior around exotic complex object, and they predict a different growth rate for the boson cloud. And this is actually very simply controlled by this function only of this refraction coefficient. Usually this the influence of this boundary reflection gives a longer time scale, which have some implication when you put the constraint using the astronomical observation of black hole on this massive field. And this is the end of it. Thank you for your attention. Thank you.
Just one question. No? Very good. Last time all the speaker in this no check again. I can see what I was. Those are back again. Maybe Alex will.
The mic is
So everyone is off. Just off.
So anyway, I think all of these projects are.
Say is.
Oh,
So your case is solution that is running on.
Yeah.
It's just an.
I don't know, the thing that is done on that, we have to make sure that it is not increase, that. So, now here we want to.
Well, the exterior. So we had an exact solution, you know. Yeah, it's in fact, except for the place where the source would be. No, instead of talking about points, which are even bigger than this. Right? Oh, spread it out. Yeah. And then. Oh, okay, okay.
走不掉了，是吧？周六有一场多少直播，我是吗？这你说的，他说哎不行，你们正好在上海，有没有问的？我没看，这两天真是，哎，你们不说人吧？是吧？
Um,
这个话题就没那么大，因为上次老师说把贴这个的话，大家就握这的话，下面经常在这里是握的，会有杂音。
我那你也不会贴。
也我是好的，但是不好意思，就是我的意思就是说，能不能看要不就往上，
往上也 even if it at best you can hold it like this。
或者往下，往这儿。
往下也可以。
嗯。
Yes.
嗯哼，yeah。I don't use Mac keynote.
It's not here, so maybe
Yes.
sticking there.
Maybe I recommend that one in me or it's fine, but yeah, it's going to so
No, but you can make a video about it.
I don't know, maybe. Or another way to just plug this one. And it's to plug this to
Yeah, yeah. I don't know.
Oh, you're here. Oh, yeah. Okay. Well, we wait 5 minutes or because I see that everybody is outside. Okay, so we wait 5 minutes. Yeah. Because I see everybody's in the meeting.
So yeah,
So for the switching as live is
yeah. For switching slides, you can use this. So you should put this mic.
this is a microphone.
Yeah. So this is clip on. Yeah. So this is for co-share. This is for Zoom. No, I think.
So, so I'm a theoretical physicist. Okay, so
Another.
now so
And if you speak loudly, then this is not required. But if you want to, like,
all right, yeah. So
no, this will not amplify. So this will amplify these things.
okay, yeah. But I think I will speak now.
Okay. And this is your point.
This is for which
Yeah. And this will
this for switch.
this is what.
Okay, I like this just. Not perfect, to move to, I like it very much. Oh, yeah, not. But most of the time I'm with my wife, so I'm traveling now. You travel every month? So every week. Yeah, it's training. Flying, training, flying, like, you know. In the weekdays, and you can. I live in Boston. Most of them. Live in former French. Maybe we can start the first session of this article. So our first speaker is Andre Adati from Japan University. The title of this talk is Blockchain Waves from First Order Phase Transition. Welcome. Okay, thank you, the organizers, for the invitation and the nice workshop. So I'm going to talk about a topic more related to cosmology than quantum gravity. That is, in particular, the possibility to test gravitational wave signal that are produced in early universe dynamics from first order phase transitions. So it's based on a series of work, in particular with Roman Pasechnik, Antonino Macciano, and several other authors, so it's here, and Luca Visinelli, several others. So this acknowledgement of the foundation. And the main of this talk, so we are going to introduce the idea of first order phase transitions. What I'm going to introduce is different than the phase transition of the very first speaker of the conference, because it's more induced by thermal correction in early universe. So we are going to talk about phase transition post-inflation, let's say. And it is very well known right now that from first order phase transition, if a particularly violent one, you can produce a gravitational wave signal in a form of a stochastic background. So everywhere, in every point in the sky, we should see almost the uniform one. And I'm going to talk about the possible connection with the issues beyond the standard model, in particular for the neutrino mass and dark matter model that are still the most urgent issues, as we know, beyond the standard model. And in particular, we put forward a long-standing idea of the existence of magnons. That is an idea that for years was not discussed anymore, but recently got some interesting news. And then I will mention the possibility of complementarity with other channels, in particular with possible collider physics or tests for lepton and baryon violations, for instance, neutrinos less double beta decay, or neutron and anti-neutron physics, and so on. So the idea of first order phase transition, I think most of you knows very well, that is related, considering a scalar field, is related to an effective potential of a scalar field with the thermal field theory corrections. It may come from the coupling of the scalar field with other fields like fermions or gauge bosons or the self-interactions, or you can have a possibility of multi-scalar field that may play a role. And according to this theory, there is a critical temperature where the tunneling probability is starting to be order 1. While in universe today, these transitions are UKB suppressed exponentially. And if you have this and you have a first order phase transition, then you have a nucleation of bubbles from nothing. The bubble that is separating the two minima the false minima and the true minima. And then since there is a difference in the pressure of vacuum, the bubbles they expand. When they expand, the bubbles, if there is a nucleation rate that is high enough, they have a high probability of scattering each other, so you can have a collision of bubbles in a transient around the critical temperature, and therefore from scattering of bubbles you can emit gravitational waves. Moreover, recently people realized that this is not the only leading contribution, but you can have also contribution from the expansion of bubbles in the early universe plasma, which is generating turbulence in the plasma, and moreover also sound waves. And this is shown to be order 1 in several cases, or even the dominant contribution. So there are 3 main contributions. Is really much similar to the boiling water process in some sense, in a broad analogy. And what we mean is for first order phase transition, the picture from simulation that you can get is pretty much like that. So you can see really bubbles where the wall is related to the scalar field profile itself. So this is an example of simulation starting with the nucleation of bubbles. And then when you start to have several ones, you have a scattering, and the process is highly non-linear. You have a several contribution from turbulence and sound waves. And finally, after a transient that is not far from the cosmological time that is inverse to the temperature, the critical temperature, you should have a very chaotized situation producing gravitational waves. So pretty much the physics area where first order phase transition can be interesting are for gravitational waves messenger is between the cosmic inflation, let's say, and the particle era, let's say, so before Big Bang nucleosynthesis. Moreover, you have to be careful to not have phase transition that are too closer to the Big Bang nucleosynthesis, otherwise you will destroy the nice predictions that we know about the nucleosynthesis. So how this can happen? First of all, we believe that this is involving necessary physics beyond the standard model. Because if you take the minimal standard model and you consider the parameters testing for lighter physics and other constraints, like high precision electroweak constraints, then we know that the Higgs boson is too heavy to undergo a first order phase transition alone. So necessary, you should have some extension somehow, and there are 2 very well-known ways to do that. Adding higher order operators, for example, D equals 6 operators involving the Higgs boson, and but lambda in that case should be not so far from the D scale to have a transition that may be test. On the other hand, you can have a multi-scalar models. In particular, in a minimal setup, you can couple through the Higgs portal the Higgs boson with some extra field. For instance, it can be in a very simple scenario a complex scalar singlet, for example, but it may be also a second Higgs, like a twin Higgs. And in this case, the phase transition are relevant as first order if this guy is not far from the Higgs boson, which is not excluded at all, because LAC is giving very strong constraint on color states and strong interactions. But when you talk about the electroweak sector, the constraints are not so strong as well. And in future, it may be interesting, if possible, to consider an electron-positron collider to test with higher precision and cleaner channel, if possible. And when? So when is related to the cosmological time, related to the thermal history, and in particular, an important parameter is the enucleation temperature, which is typically related to the vacuum expectation value of the scalar field, even if there are some exceptions like the so-called supercool first order phase transition, but in many cases, this temperature is not far from the vacuum expectation value of the field that you consider. And the typical temperature, the typical parameters that are critically important here related to the bubble enucleation that is generated from the tunneling from force to true vacuum state. The two critical parameters are the latent heat that is this alpha related to the latent heat that the transition is releasing in the thermal plasma, and the beta that is related to the enucleation rate. In particular, beta over the Hubble at that time should be at least higher than, let's say, 10 or 1 or around 100, 1000. Otherwise, the process would be not having enough enucleation rate to be relevant. Another important thing is that the critical temperature of the process is typically proportional to the gravitational waves frequency of emission that is getting several contributions, as I say, from collisions, the sound waves, and turbulence. This means that from the gravitational waves frequency can say to you which kind of phase transition temperature is involved. To be more specific, alpha and beta over H are completely controlled by the Euclidean action of the scalar field that is thermally corrected. So for more details, I can actually explain later, but this is just to say that the critical parameters for emission of gravitational waves that are alpha and beta, they are fully controlled by the scalar field effective potential. And you have typically primordial gravitational waves that from strong first order phase transition, so from violent phase transition, they are produced in early universe. And as a first approximation, they are in form of a stochastic background of gravitational waves. And the polarizations can be mediated in such a way that are assumed to have the same spectrum and they are mutually uncorrelated. And typically, even if to compute with simulation, this gravitational wave signal is not easy task. Indeed, there are codes that they take for running several months, but there are some semi-analytical formula to understand how to relate the gravitational wave signal peak in energy density and in frequency and in energy density with respect to the parameter alpha and beta and the regulation temperature. So typically, to make the story simpler, we can have three important windows. The most probably the one that is attracting most of the attention recently is around 100 megaelectron volt of the critical temperature. That may, as I will explain, may eventually be detected in pulsar timing and radio astronomy physics. In this case, would be subelectroweak phase transition, even if there are cases in which in supercooled phase you can also have a signal around there. But typically, the electroweak first order phase transition involving the Higgs boson should be around the millihertz, which is important for space-based interferometers such as LISA experiment, or in China, the Taiji and Tianqi project proposals. And on the other hand, you can have also a possibility of super electroweak phase transition that may be inspired, for example, by grand unification inspired scenarios. For instance, if you consider SO10 breaking down to left-right symmetry model, you may have a intermediate stage in the desert from grand unification to electroweak scale. And in that case, it would be very motivated to consider scenarios of first order phase transition from extra X in the model, for example. But it's just an example. In that case, the frequency would be more around the terrestrial interferometers. You can have even constraint right now, and it can be interesting for the future terrestrial interferometers such as the Einstein telescope that maybe will be in Italy and the Cosmic Explorer. So concerning the electroweak phase transition, there are several works. This is just an incomplete list, but an efficient way to do that is I can give you a particular example. Is Lagrangian of the Higgs coupled to a complex scalar field with the Higgs portal, and I will show you that it's enough to have a renormalized portal, but indeed you can also consider 6-order operators if you want. And from this mixing, you have a bidimensional potential, so it's easier to find direction in which you have a first-order phase transition that can be multi-step. So you can have more than one just electroweak phase transition, but also one involving the extra sigma that is thought eventually as a complex scalar field with respect to extension of the standard model symmetry in an extra U1. And I will explain, for example, how to do that.
Without this extra operator.
You can also avoid the extra operators. Extra operators, you can, in a standard model coupled to the extra scalar field. In the minimal one, as in the textbook of Mukhanov explain, we cannot if you so yeah. So one motivation to do that is it may be motivated by dark matter. There are several right now. The situation of the so-called winds, la thermal miracle is strongly disfavored by experiments, and this is motivating the consideration of alternatives that may be primordial black holes, for example. But if you want to stay still in a particle physics explanation, you may try to consider minimal extension of the standard model with an extra U1. They may be related to the existence of dark matter. The extra U1 is not naturally suggesting that the phase transition in general may be of first order. And on that, we actually assume a probabilistic approach that I will show you to show that there is a very strongly favored in case of an extension of an extra U1 to have the first order phase transition that are testable. For example, you can make this game in several ways. One of the certainly you can make an extension of the standard model with the extra gauge symmetry. For instance, the idea of B minus L, which is anomaly free, or dark extra symmetry, or in general some combination of the baryon, lepton, and some extra numbers. And this is going towards the idea of the dark photons, the baryophotons, extra zeta prime bosons, and so on. However, a possibility that in string theory they don't like is also that you have a global symmetry that can be spontaneously broken. There may be eventually also an anomalous one, for example, lepton one, or B minus L, or B, or a patch between symmetry, etc. You can have several pseudo-Goston bosons, like the so-called majorons and axions, and this is pretty much related to the possibility of having a minimal model particle physics for dark matter. In that case, the mass is not necessary at the electroweak scale. We know that the axion is a very light particle, and the very same for the majoron, in which there are several models. One is that the majoron is a so-called warm dark matter candidate, but there are also versions in which a majoron has a mass very similar to the axion. So the possibility that we study is that the global symmetry can have a spontaneous symmetry breaking, and this is introducing obviously a new scale, a new vacuum expectation value scale to be compared with the electroweak one. So in that case, the idea is that generically the pseudo-Boston related to the imaginary part of the complex field would be the dark particle. And there are several ways, several mechanisms to produce exactly the right amount of dark matter that is needed from experimental constraints in cosmology. The idea is pretty much inspired by the Ettore Majorana in 37, and Majoron indeed is taking the name from him, that is based on the idea of Ettore Majorana that the neutrino can be, or in general, a neutral fermion can be a Majorana particle. So in some sense, in a colorful way, that the particle is identified with the anti-particle itself. And but there is this idea that if you introduce this portal by n, you violate by n the lepton number of 2 units. So one possibility is that actually this violation is from a spontaneous symmetry breaking. So in other words, you can couple the complex scalar field with the neutrinos, can be the right-handed neutrinos in a seesaw mechanism, and after getting a spontaneous symmetry breaking, you generate the operator delta L equal to violating spontaneously after the symmetry breaking. And this is very interesting idea because it's very simple, very minimal, but it's relating fundamentally the issue of the neutrino mass to dark matter, because the so-called majoron can be a candidate for dark matter, and it can be implemented in several seesaw mechanism ideas. So the majoron is certainly one of the best at these pseudo-Goldstone dark matter models. It's not the only one. And it's, as I say, it's motivated as several parameter space as warm dark matter candidate. There are several papers about that from the same chain, Moapatra, Berezinski, Valle, Schechter, Ahmedov, Berejani, Volkov, Segnanovic, and Klein, and so on. So it's an outstanding idea that for many years was not studied so much, but still very motivated. And you can do this in several ways. In seesaw type 1, which is maybe the easiest idea, and you can couple, as you see here, the majoron field with the right-handed neutrino, and after the spontaneous symmetry breaking, so when this guy is getting expectation value through the seesaw, this is generating a right-handed neutrino mass. The through seesaw is giving you the desiderata left-handed neutrino mass. But you can have also other scenarios, like an inverse seesaw, in which you have an extra fermion in the game, mixing with the right-handed. And here the seesaw scale can be a lower scale than a typical round grand unification like. And this is why it can be more interesting for tests in colliders, for example. Or you can have the so-called extended seesaw. What is changing is the lepton assignment of this guy. That in the first case is -2 units, while in the others it's -1 and 2 respectively. So let me show the results of the analysis of first order phase transition, considering the majoron coupled with the Higgs boson as a Lagrangian that I introduced before. And I can show you that it's very, after Stanley scan plots that are very boring to do, but I think very insightful, you can see that in a large space of parameters, you obtain peak points that are lying in sensitivity cards interesting for future space-based interferometers in a very large space of parameters. So this for us, from a probabilistic blind approach, it may indicate that this model very likely can be tested in future experiments. Here, other scan plotting varying the various coupling constant. I don't want to bore you too much with the details, but you can see that varying the coupling because of thermal loop corrections, thermal correction to the Higgs potential coming from standard model coupling, you can obtain several points that are favored as a candidate for test. The typical spectrum, if you don't plot only the peaks, but if you consider the whole spectrum, it's looking like that. So you can see that it's growing kind of polynomially, and then it is decreasing sharper, and typically it's around a critical temperature. So you cannot test this signal in so much, crossing so much frequency windows, but it's pretty localized around the critical frequency that, as I say, is proportional to the critical temperature. So this is the idea. And yeah, these are other scan plots, and you can compare. You can also consider scan plots considering sensitivity curves of alpha as a function of beta over h. I remind you that alpha is the latent heat, and beta over h is the nucleation rate compared to the Hubble at that time, and so on. So you can consider several scan plots to convince yourself. And you can also, there is a very nice complementarity window between gravitational waves and collider physics, because every time you have first order phase transitions that can be tested as gravitational waves, you also touch the trilinear coupling correction to the Higgs boson. And these things can be tested in colliders, even if in LAC we don't have a very strong constraint right now, but still you can get some of them. But this may be very important for motivating eventual electron-positron colliders that are considered boring, but in reality, we can really get a lot of information about the nature of the electroweak phase transition. And here there is a scan plot comparing gravitational waves and test for the trilinear coupling. Okay, I don't want to bore you too much with the scan plots, but eventually you can see that there are several points. One comment about how to make this kind of analysis, actually it's kind of involved analysis because you consider typically an effective thermal corrected potential plus the three-level Baer one plus the Coleman-Weinberg, the one-loop potential that you can see here and that most of you already know. And you can choose, it's convenient to choose a Landau gauge, but there are also other possibilities, of course. You can see that you consider the mass as a function of the field itself. This is a typical structure of the Coleman-Weinberg potential after you also subtract properly the counter terms. Everybody knows here that the Higgs sector has a possible hierarchy problem that here you want to subtract a node. And there are the counter terms that you can choose conventionally satisfying these rules, and this is a specific case of the parameters of our model. There is another important issue here that is the fact that to make this computation, for years people fight each other to choose the right gauge because apparently it's a gauge dependent computation. And in particular, most of the community right now is using the so-called MS bar scheme that you can find all the details, for example, in the review of Mariano Squiros in several other publications. Of course, when I consider phi alpha here, the indexes will indicate that you can have more than one scalar. You can have a X, but of course also the Majoron and so on, and you include them in the game. These are the thermal correction to the potential that are the relevant one to understand the dynamics of the first order phase transition. And yeah, there are several techniques that I don't have time to mention in all the details, but there is a so-called resummation via Daisy or ring diagrams that define a temperature. This is a series of papers showing this. But what is important is typically the correction, the thermal mass correction, that is scaled with coefficients that are proportional to coupling, to square, in any case for the gauge bosons, and for the linear for the Yukawa, that are coming from the interaction of the scalar fields with the standard model fermions and gauge bosons, and of the scalar fields each others, of course. So this is really interesting because all the physics here is basically controlled by the standard model parameters and the parameters of the scalar field potentials. So there is a really clear connection established between the parameters of your theory, the fundamental parameters of your theory, the one appearing in the Lagrangian, and the thermal correction to the scalar potential. And these are also the details. So you typically consider the mass of the bosons as functional of the fields and of the temperature. And you can see that typically the mass squared, they obtain a quadratic correction in the temperature. That's why around the typical critical temperature, these corrections are important, are relevant. But in late universe, this correction will just disappear out, they are completely suppressed. And typically, the delta bool T correction, the thermal correction at 3 level, they appear as T to 4 proportional to the JB and JF functionals. times the number density of boson and fermions. Of course, there is an understood sign of the two terms each other, and the JDF integrals that appear as the logarithm of 1 minus plus exponential of the minus square root of x squared plus y squared. And you can have a leading order correction, including also eventually one loop that we scale as t2 squared and a very understood combination of masses. And then you can plug in, you can plug inside the correct degrees of freedom, and you get the correct thermal corrections. So the Majoron model from first order phase transition, even is so simple, why it's interesting? Because it's a minimal model for trying to have some intuition about neutrino mass and dark matter at the same time, but it has also a very rich phenomenology. So not only in gravitational waves physics, but also, as I say, in trilinear X coupling correction. Moreover, if the Majoron is usually lighter than the X, so the X can decay into invisible channels. And this is also something that can be tested with important accuracy in future. So there is a strong interest to go in next high luminosity phase for LAC, but as everybody of us knows, LAC has a very dirty background in several electroweak channel tests. So that's why for the electron-positron collider would be for that better, but we don't know if we can discuss if the investment is worth in this is anyway for that for the electroweak test it would be better for sure. And this is actually we discussed this in several papers with Roman, Antonino, Antonio, Raul, and Jose Valle. And we discuss exactly the complementarity that is not expected a priori, but it is in this model is very clear the complementarity of two very different kind of physics, it is gravitational waves and collider physics. But not only, because of course the issue of the Majorana portal for neutrino is related to the neutrinos less double beta decay. You can see a review of Jones, for example, about that. And if you have a Majoron, you have here a portal of invisible channels of emission of Majorons that can be tested with high precision in future experiments. For instance, in our university, Sichuan University, we have a group of legend experiment that will be operative in Gran Sasso Laboratory, and they will achieve a very strong constraint on emission of Majorons. But it's not easy to compare this physics because it's involving nuclear transition physics. So something we are working on right now with in collaboration with Michael Ranstein-Usov, that is in TDD Institute in Shanghai, is to try to connect this kind of physics parametrically with first order phase transition. But to do that in a proper way, you need to use the so-called effective field theory formalism for the neutrinos less double beta decay. We expect relevant emissions, especially in the so-called inverse CISO implementation of the Majoron model. That is also the one that is more related to first order phase transition that can be strong and test in future. And a possible perspective are also related to the possibility to have the so-called electroweak baryogenesis that is typically related to first order phase transition. And since if you couple this guy, this Majoron, with a baryon B-L assignment with the Higgs boson, it is natural from electroweak phase transition of the first order to generate the correct amount of baryon and type baryon asymmetry. Also, this is not easy, you need to make several simulations. And then you can have also another possibility that is a little bit more complicated for several reasons, but is a possibility of having the phase transition in only the dark sector from lower scale subelectroweak first order phase transition. There are several models in which you can do that. One is a Majoron with another different potential, a 6th order dimensional potential, but we suppress the coupling with the Higgs boson here. So it is undergoing to first order phase transition in the dark sector D per se. Or you can have the possibility of a dark photon that is naturally subelectroweak in the scale, and other possible dark symmetries. I also saw some works about conformal dark symmetries. So there are several possibilities of trying to explore that. And this is related to the recent anomaly that they saw, especially the notorious nanograv 15 years, and the other tantalizing anomalies related to that from PPTA, EPTA, and CPTA. And these are radio astronomy physics from pulsar timing. As most of you know, this is because if you have a gravitational waves stochastic background that the size of millielectron volts is around the nanohertz, so it's a super electroweak transition eventually, or a super cooled electroweak one, then you can have a possibility to try to explain these anomalies as an alternative of the conventional explanation that people explore from supermassive black hole merging. And recently, okay, this actually is an idea that we proposed when the anomaly with the Ifuzai and Antonino Marciano, when the anomaly was still a few sigma. And we already noticed that with this guy, this operator, we can do that easy, can be tested. And recently, after the news about nanograv, we make a fit. And something that we discover is that nanograv is even indicating which kind of phase transition may be. That is typically the one related to the dominance of the sound wave contribution. So it is not going to be eventually a so-called runaway dynamics where the bubble are propagating as almost the speed of light, but it's going to be, let's say, more regular one. And the sound speed contribution is fitting really well. If you consider temperature that is not far from the mega electron volt or 100 mega electron volt. However, this is posing some puzzle about model building. So here, by the way, I plot gamma and this power law exponent as a function of logarithm of the amplitude in front. And you can see that you can explore varying alpha and the temperature. You can explore which region is favored by the experiments. So it's fitting pretty well. And according to several works, it's fitting better than supermassive black holes. It's still early to say that this is fair explanation, of course, but it's an interesting possibility that can be realized in a minimal extension of the standard model. Another thing that I want to mention is a work in progress inspired by my former advisor, Zura Beregiani, in L'Aquila Gran Sasso Laboratory. That is a so-called idea that is not very well explored, is a so-called idea of what we call the baryo-majoron. So there is this interesting story that actually, if you read the paper of Ettore Majorana, he proposed at that time that the Majorana fermion is not the neutrino, but the neutron. And this is an open possibility, of course, beyond the standard model. And from the point of view of the Weinberg operator is related to a dimension 9 operator UDD squared divided by the entropy scale to pi, or QQ squared. And the current limit on that is, on this scale, is 300 TeV, related to the Baldo-Channing experiment in 97. So the idea is that you can have a sort of seesaw mechanism related you can implement in two ways, in several ways like that, in which introduce an extra, let's say, right-handed neutron as a fundamental particle, the baryo-majoron that is inducing the delta B equal to violations, and some extra scalar color triplets that reminds a little bit of the sports, but this is not a supersymmetric model, just reminding. And you can construct a scale, for example, sending these guys at very high scales. So, for example, can be multi-dB scale, and the baryo-majoron in that case can be a low scale. So you can have a spontaneous symmetry breaking of the baryon number as a global symmetry that can be related also to first order phase transition. In Europe, there is great attention about the construction of the neutron spallation source. That is a €1 billion project in Sweden. And they are gonna increasing the limit on M of 1 order of magnitude. So this can be extremely interesting because you can test from this long range baseline for neutron. You can test in a very clear way if the neutron is transiting to an anti-neutron, and then from a typical annihilation target, you would see clearly this guy transit to a neutron, to an anti-neutron. So you would see this very clearly. So there is great interest on that. And it can be an interesting idea to test baryon violations beyond the standard model. And I claim that there is a possible nice complementarity to explore better in future between the idea of first order phase transition and this kind of low energy physics. I also mentioned that in a neutron called neutron physics, that is extremely interesting physics, you need to realize the experiment with a very low magnetic field. So you need to shield your beam of neutrons with a magnetic field suppression that is below the milligauss. So technologically it's kind of difficult to do that, but there is the technology to do that for few kilometers. So it's a very interesting physics in some sense alternative to the standard searches of Majorana neutrinos. So it's more a Majorana neutron. The real difference is that for neutron, if you give a Majorana mass in this case I didn't plot, but it would be proportional to lambda QCD to 6 divided M to 5. And this corresponds, if I'm not wrong right now, mine, to something around the limit of 10 to minus 23 eV. So it's a very tiny mass, much below the neutrino mass, but from the point of view of Weinberg operator, is corresponding to a PV scale physics. Okay, I think my time is really finished, so just thanks for the attention.
Thanks a lot for Vanessa. Let me start from smaller frequencies. In another last year, nanograph paper by Mixer and collaboration by considered among new physics alternatives based conditions. First question is how you whether you compare your results with their results. And the second question is about LISA. In March, LISA paper by Caprini and others showed that the LISA will be able to constrain the parameters of phase prediction models better than with better than with accuracy. Did you look into those results and compare with yours? And question 2B is if you imagine that the nanograph signal is constraints based on prediction models, then you prolong that signal down to user frequencies, and that should in principle improve the accuracy with which you would constrain parameters, because you would have a smaller primes. If you believe that if you assume that the nanograph signal is the left end of your stochastic diagram.
So let me say that since the nanograph signal is confirmed 15 years, there are several analyses that came out on first order phase transition. Most of them, they agree on the point that it should be contribution dominated from sound waves, from the fact that bubbles expand and generate contribution of gravitational waves from the sound shock waves, let's say, like a wave propagating in the plasma. But there are several things still to discuss. For example, one typical problem is that many models they release with such a phase transition too much entropy into the plasma. This can be a very serious problem because if you produce this is releasing in form of radiation, like in many models, like the dark photon effect, which is radiation like form, then this is contradicting and destroying many bounds from nucleosynthesis. So this is a challenging point. Other people also discuss if QCD itself may be the cause of that. There is a controversy in that, very strong. For example, if you talk with the lattice QCD people, they would say absolutely not possible, but it's still something under discussion. I don't know if I answered to your question. And about LISA, yes, LISA promises very strong sensitivity and very high accuracy. Many people talk about gravitational waves physics in this sense as high precision physics. But there are several critical points that, and so I tend to disagree that can be such a precision in the particle physics sector, because there are several order 1 corrections from uncertainties on turbulence modelization or sound waves. So it may be, I think, order 1 precision test, but it's difficult to say at the moment. There is a kind of discussion that I think it's very interesting physics for the fact that at least the order of magnitude can arrive to the sensitivity, and you can even have some information about the shape of the signal. To answer about your question, if you can extend the signal from nanograph to LISA, according to our simulation, we tend to be negative with that. So the phase transition is typically kind of localized in some sense, in some window, but there are other phenomena that can have a broader spectrum. For example, people discuss cosmic strings, their spectrum can be flatter, crossing several order of magnitude.
Okay, so since time is limited, so let's come to speaker again. So, next speaker is Zhongzhi Xian from Tsinghua University.
Hello, hello.
Yeah, so the title of our talk is analytical method for cosmological analysis. Welcome.
Oh, okay. In this way. That's a lot of. Okay, sure. Okay. Okay, thank you. So first, let me thank the organizer for all the hard work making all this great conference possible, and also for the invitation giving me this opportunity to present our recent works on the so-called cosmological correlation functions. I will put emphasize on the analytical techniques. And I'm Zhongzhi Xian from Tsinghua University, and this talk is based on several works we have been doing in recent 2 years with 5 of my PhD students here. A lot of work here, but I'm not talk all of them in equal detail. So 5 of them, I think, is also covered in Johan's poster. You can find some details outside. And I also talked about some of these works in previous talks. So today I will mainly focus on 2 recent works, especially the ones with this family tree decomposition I will mention later. So the outline of my talk is the following. I will first give you the background of the cosmological collider physics. The big word is cosmological collider. What is a cosmological collider? What is the signal we are after in this program? It turns out these are the correlation functions of quantum fields living in the de Sitter spacetime during cosmic inflation. And their correlation functions are what we call cosmic correlates. And if you really want to dig out those signals from the observations, it is very important to have a precise computation, very efficient computation of this stuff. So I will discuss the general structures of this cosmological correlation function, especially a method we call partial Mapping bands. I will explain why this method is very useful. And also I will touch very briefly on the loops. I will describe some analytical techniques we have been developing, including the factorization theorem, spectral decomposition, and also dispersion relations. And the central topic of this talk is actually to deal with the nested time intervals. This is a little bit technical, but I promise you there's a lot of fun inside this. So the keyword is so-called family tree decomposition. I will explain later. And finally, I will apply all these techniques into a recently very extensively studied point model, which I call conformal amplitude in FRW. And I will show you why the family tree is useful to obtain the general result. So that's the plan. To set the stage, let me still put my talk into the context of this conference, which is quantum gravity. The whole idea of a cosmological collider is really to think of the whole universe as a giant collider. It is actually very natural. So in this graph, I deliberately contrast the working of LGC, large hadron collider, in particular the cross-section of the Atlas detector with the evolution of the universe. We know that the universe has been evolved in a non-uniform fashion. There is a layered structure in different history epochs. We have different events happening. This produces a lot of possible cosmological observables, including a cosmic microwave background, a large field structure, and also more futuristically, the 21 centimeter tomorrow through the dark ages. So all these observables provide us opportunities to dig out the high energy process that was happening in the very early stage of the universe during cosmic inflation. So the metric of the whole program is that we believe that if there has been a stage of cosmic inflation, then scale of cosmic inflation can be very high. It's measured by the expansion rate, the Hubble parameter. It can be as high as 10 to the 14th inflation scale here. And when we talk about the quantum gravity, the natural scale we talk about is M1 with the 18th gene. And this is to be compared with the currently best machine we have ever built, which is Large Hadron Collider, which is roughly 10 to the 4th GeV. So if you really want to study very high energy physics, what you really want is very high energy collider. This is very obviously beyond our reach. You want to M1. So the cosmic inflation really provides you an alternative to explore this high energy, very high energy particle physics. Now, what is the cosmological collider signal we are looking for? These are the correlation functions of large scale fluctuations, either scalar mode or tensor mode. Everything you can measure through the large scale measurement in cosmology. And from the viewpoint of cosmic inflation, these correlation functions are produced by the quantum fluctuations of fields living in the de Sitter spacetime, because we know the inflation in the spacetime is expanding nearly exponentially, and this is very well approximated by the de Sitter spacetime. Here in the left diagram, I'm plotting the Penrose diagram of the de Sitter. In particular, the inflation path corresponds to the upper triangle here. So we talk about the whole inflation path of the triangle. Early time limits being equals to minus infinity, the late time limits, the end of inflation being equals to 0. This curve is the so-called conformal time. It's not very important. The important thing here is that you have fluctuations of quantum fields. And the fields have very high energy fluctuations, then they are quickly redshifted. The upshot is that you have very active particle production. And you can think of this production as a Schwinger pair production-like process. And these are promising observables to really look into the data. Actually, in this year, there are already works trying to dig out those correlation patterns through the real data, either in CMB or large scale structure. I think Donggang will cover one of this topic in this talk after me. And if you look into the forecast from experimentalists, people are talking about 2 to 4 orders in initial improvement in the precision of measuring these functions. So there's a large parameter space to be explored. And the question is, what is the particle physics inside this parameter space? The particle physics inside this parameter space is nicely summarized in this kind of plot, which I call cosmological climate signal. What is plotted here is if you think of this 4-point correlation function of infraton fluctuation, the density fluctuation, mediated by a massive scalar theory, which are described by a red wiggle line here. And if you go to the very soft limit of the exchanging momentum of this 4-point function, and if you measure the 4-point function as the momentum ratio of this soft momentum with the hard momentum of external ones, then you will realize this very characteristic oscillation patterns. You can separate this function actually into 2 parts. One is what I call background, the blue line, which features a smooth, very smooth dependence on momentum ratio. And on top of that, you have the oscillations. And people have shown that this oscillation is actually a consequence of resonance between a heavy field of these massive red lines with the external mode. The consequence of this resonance, you will have these wiggles, which shows you the mass of particle. And also, if you look more closely into the wiggles, you can also obtain the information about the speed, the interaction times, and also expansion history. So there's a lot of information to be extracted if you can really measure this signal. And the one point I want to emphasize in this talk is that these signals are not only important and interesting from observation point of view, it's also very interesting from theoretical point of view because they represent our data for understanding quantum field theory in the space time. In particular, if you look at these oscillations, if you think of all these correlation functions as functions of complex momenta, then these oscillations appear on the complex momentum plane as branch time. So there's a very close relation between the analyticity of the correlation function and the observations, the signals. So over the years, basically in the last decade, we have been working very hard, trying to find natural particle physics models that can give you visibly large cosmological climate signals. By naturally large signals, I mean we do not tune any particle. If you allow us to tune, you can get any large signal you want. But the real question is just give you very generic particle models, either within standard model or beyond. And you actually find natural models which give you untuned cosmological climate signals, which can be observable in the near future. And the answer turns out to be yes, although the process is quite non-trivial. And this has been summarized in this actually a little bit outdated diagram in the 2019 paper, where we plot a lot of cosmological climate signals as functions of frequency of the oscillation. I just show you there's a dimensionless frequency, which shows you the mass of the particle. And the horizontal, the vertical axis is the signal size. So most of this parameter space is expected to be covered by the large scale structure and 21 centimeter observations in the future. So you can see there's a lot of models that can actually be explored in the future. So behind these signals, a simple Feynman diagram like process shown here, either tree level or one loop level. If you just think of this particle process in flat space, this is a standard quantum field theory material. You have a good quantum field theory course, you can compute this item very easily. And now the problem is that you live in the Basile space time, and things get a little bit non-trivial. So if you really want to dig out this signal, what you really need is a very high quality template. You need to evaluate quite precisely, quite efficiently, these correlation functions so that you can get a decent template back. And you hand this template to observation colleagues, and they can use this data to search for things in the real data. So the task for us is to understand the amplitude. By understanding the amplitude, I mean two things at least. One thing is that you have to have an efficient numerical way to compute this correlation function. The second part is you want to understand the analytical structure of this correlation function. Because as I said, there is a very close relation between the analytical structure with the physical process, with the signals encoded in these correlation functions. So that's the motivation. That's the motivation for studying all these cosmological correlation functions. But it is hard. To explain why it is hard, I will not bother you to show you the whole expression, but very schematic form. The whole thing you need to compute is a Feynman diagram. And also remember that we are talking about correlation functions instead of asymmetrics. So it is not in our amplitude. It is not something you send particles in and you collide and you send some particles out. It is an equal time expectation value of some quantum field fluctuations. So you have to do this in a space-time asymmetric way. More concretely, for every Feynman diagram like this, with internal lines, and also loops, you have to finish an integral of this form. In this integral, you have, of course, the loop momentum integral, very similar to flat-space story. But in addition to that, you also have integration over time variable tau associated with each vertex of this diagram. This is very important. So the difficulty of computing a correlation function increases not only with the number of loops, but also with the number of vertices. This is one point we have to make. And inside this integral, the integrand basically consists of the external propagators and the bulk propagators. External propagators are typically easy because they represent the quantum properties of either inflaton field or harmonic gravitational tensor mode. These are just the simple exponential functions, which are called external line. The real trouble is the bulk line here, described by these blue lines. Here I've been very schematic. This capital H actually represents the product of many Hankout functions. A Hankout function, the argument being the product of momentum and time. And to make the whole thing worse, you also have these time ordering theta functions. Because you are talking about a time integral, there are arbitrary ways to order the time variables. So there's a lot of theta functions entering here, nest the whole integral together. So this is a stuff we need to deal with. In the past few years, we have been developing techniques tackling this problem one by one. There are several complications, so we have several techniques. One is the so-called partial mining bands I will mention very briefly. This is kind of central method, which is very useful. And also for spectral loop process, the so-called spectral decomposition of these generations can also be very helpful. More importantly, you need to deal with all these time orderings, which are called nested time intervals. So this family tree techniques is developed to deal with all possible arbitrarily nested time intervals. Also, around the same time, people are also developing other techniques. One called cosmological bootstrap. I think Tonggang will emphasize this method. Also, the full ADS line amplitude and also the differential equations like kinematic flow. So let me just mention some of these techniques. First one is so-called partial Melling bands. So Melling transform is a simple mathematical transform. You can just think of this as the de Sitter version of Fourier transform. In flat space-time, we do Fourier transform because there is a good time translation symmetry. But in de Sitter, we do not have the symmetry. Instead, we have a dilatation symmetry. So we do not expand mode in terms of plane waves, rather in powers in this x to the x minus 1 is power function. Exactly because these power functions are nothing but dilatation eigenmodes in the zero space time. I want to emphasize that this method is actually independent of symmetry. You do not really require existence of dilatation of the zero boosts to apply this method, so it's actually very flexible. Now, what is the partial Main invariance? Partial Main invariance is that we make this Main transfer to all the bulk lines, but not to external lines. For example, as I mentioned, there's a Hankel functions in operators in the space-time for the massive field field. And if you take the Main transform for this Hankel function, now appears in the integrand is a simple factorized powers of momentum and time. So momentum and time are factorized in integrand. That what makes Main invariance useful for us. Of course, you still need to finish this integration over the Main variable x, which has the integration contour running through the imaginary axis. This is a general structure. After you take this partial Main invariance to all internal legs, then the very complicated loop integral and time integral just get factorized. You have a factorized loop integral and the next time integral, so you can deal with them one by one. Loop integral are similar to fast space time, so I will not spend time on that. Time integrals are more challenging due to the time orders I mentioned many times. Of course, even after you finish this loop integral and time integral, you still need to finish the Main integral over this s value. But this turns out to be rather trivial because for very general theory where you have perturbativity, the integrand of this Main integral is meromorphic in the sense that they are only poles, not branch path. So you can just finish this Main integral by picking up poles. It turns out that there's a very rich pole structure, and this pole structure tells you a lot of physics for these diagrams. As an example, this is an old work. In this work, we have been able to prove the factorization theorem for the wiggles, for the signals in arbitrary loop diagrams in the zero space time. The method here is a detailed analysis of pole structures of the Main integrand. And you identify certain poles that contribute the oscillations, and you get the result. And you can show that they're factorized. In particular, you can get a full analytical result for these loop signals. There's a lot of technical details I will not touch upon. But as an application of this method, we are now able to compute the signals in arbitrary 4-point one loop topology. And these are some examples. But I emphasize, these are only for signals, for the oscillations. If you really want to get the full shape, the signal plus the background, as I mentioned, you need other techniques like spectral decomposition. People know how to decompose a bubble, like here, into linear superposition of tree diagrams by borrowing techniques from either spheres or from ADS, because you can do wig rotation of the theta, and you can do rotation either into a sphere or into ADS. So you can finish computation of such diagram by using ADS or spherical techniques. And with this method, we get the first and currently only known complete analytical result for massive one loop processes in the zero space time. And currently we are developing the dispersion techniques, exploring the branch path structure of correlation functions, the complex momentum plane, and turns out also to be very useful. I will not explain in detail. What I really want to spend some time on is this family tree decomposition, because as I mentioned, one difficulty of computing the cosmological correlation function is the nested time integral, because you have arbitrary products of theta functions nesting all integration variables out here. So if you look more closely, the most general time integral has this form. You have arbitrary sort of integration over this power variable, and the integrand thanks to the partial value lines now is just the product of power functions and exponential. And in addition to that, you can have arbitrary product of time ordering theta functions. So let me just finish the diagonal representation for each of its integral. I emphasize this is not a fundamental, just a convenient graphical representation. For example, here you have the 4-layer integral nested in a particular way. Like tau 1 is earlier than tau 4, 2 earlier than 4, 4 earlier than 3. Then you have a certain order structure in this diagram. So you have 1 earlier than 4, 2 earlier than 4, 4 earlier than 3. So you have this time flow in this diagram. And also to each vertex, I associate several variables. First, I have this time variable tau to be integrated over. I also have this omega, which is nothing but the energy injected into the integral of this omega. And I also have this Q factorization of this. So this is typically from the background evolution, the time dependence of the interactions. So this is a general structure. You realize that all computation of evaluating such an integral is from the theta functions. If there is no theta function, then the answer is very simple. It's all the gamma. Integration over products of power and functions, all the gamma. But if you have theta functions, it's a little bit complicated. You cannot remove the theta functions, but you can switch the direction. This is a key insight of this method. By using this trivial identity of theta functions, you can arbitrarily flip the direction of this time flow at the expense of generating additional keys, which is factorized. Since it is factorized, it is simpler. So that's a trick. The so-called family tree decomposition says that whenever you have a nested time integral nested arbitrarily, you always flip some directions such that all nested graphs are partially ordered. The way is partially ordered. For each pair of vertices connected by a dielectric line, I can call the earlier term another, the later term the daughter. And if you adopt this chronology, then a partial order diagram simply says that another arbitrary number of daughters. But the daughter must have one element that is partial order. So in this way, every resulting nested graph can be incorporated as a maternal family tree. That's why we call it family tree decomposition. So just flip directions. This is a notation we designed for these family trees. I will not explain in detail, but only by examples. Say I have a very simple 3-side chain. 1 flow to 2, 2 flow to 3. My notation is just 1, 2, 3 in square brackets. But if the minor 1 has 3 daughters, then I add parentheses to its daughters to highlight that these are the sisters, which they are not the mother daughter relation, they are siblings. But if one member has her own daughters, I add more parentheses. So this is just a convenient bookkeeping notation to denote this family tree integrals. Here is an example. Suppose you have an arbitrary 5-fold integral like this, with arbitrary time nesting. Then what you do is you just pick up an earliest time. In this example, the side 1. Then you can decide whether to keep or flip the direction of each one, and resulting in several graphs, all partially ordered. And our notation is like this. So it's trivial exercise to do this flip of direction exercise to resolve all possible nested integral into partially ordered diagram. The question is, why do you want to do partial order graph. Why do you want to do family tree decomposition? The reason is that once you have a partial order in type, it is possible to finish this time integral layer by layer in the reverse direction of the generation. You begin with the latest generation in this example 2, 4, and 5, and finish in the first layer of the integral. And this gives you incomplete gamma function because you have a integral limit, not zero, it's a fixed time. The trick here is that you do partial Mason balance to the integrand again, and integrand becomes our expansion again, so that you can keep going and go through all the layers and finish the 9-max integral to get a result. That's the method. The result of this series, integral is a series expansion of the original family tree. It's a series in terms of momentum ratios here. And there are some notation here. I need to explain quantity. Whenever you see a parameter with a tilde, it means the sum of all q's on side j and her descendants. So in this way, you can just write down the analytical answer, the series expansion for arbitrary nested time integrals without even computing them. So this is a result. Some examples. If you have a three-side chain in the correct order, 1, 2, 3, then you have a series expansion. But if it's in a different direction, 2 to 1, 2 to 3, then you have a different series expansion. So realize that the family tree decomposition is actually very flexible. You can flip direction in arbitrary ways, and each way gives you a distinct expression for this series expansion. You might realize that all these family tree series are just a multivariate hypergeometric series, in the sense that you have many arguments, many power factors in the series, and the coefficient just being fractions and products of all the gamma functions. These are so-called hypergeometric series. And in this way, we always expand the reciprocal of earliest energy and prefactor gives the monogamy. Here the twist factor Q can be arbitrary, complex numbers. So you can read the monogamy of this result directly from the prefactor. And you realize I think in this way, when you do family tree decomposition, you always ask the maximum energy to sit at the earliest site to improve the convergence of the series. So these are all very complicated series, but for simpler cases, for these simple family trees, they do sum into known hypergeometric functions. So one side is nothing but all the gamma, two sides is Gauss hypergeometry, three sides, sometimes they can be described as uphill functions. More complicated ones are converted to real functions, etc. And more complicated family trees are not yet named, but they are still valid hypergeometric functions. One thing I want to emphasize here is that the flexibility of the many integral, the many variance representation actually leads to many distinct expansion of family trees in terms of either large or small, single energy variable or partial energy variable or total energy variable or energy difference. By total energy, I mean the sum of all energies in the diagram, and by partial energy, I mean the sum of several energies in the diagram. So you realize that there's many equivalent ways writing the same expression in terms of many different series. And for simple cases, this flip direction trick gives you a lot of functional identity of known functions. For example, this functional identity between Gauss hypergeometric is something you can look for in a good mathematical table. But for more complicated ones, these are likely new results. And we have infinitely many such functional identities. The important thing here is that when series do not, when they do not sum into known special functions, this functional identity amount to analytical continuation beyond regional convergence. So this is exactly the way how we learn a new special function analytically. We try to expand the function in all possible parameter region, and we want to do analytical continuation among them. So this is what we can do for family trees. And you can further show that the family trees are not a minimal set of functions describing all these naturally integrals. In fact, you can further do one layer of decomposition by using the trivial identity of theta functions, but in a reverse direction. Here, without explaining the details, you can actually observe by eye that whenever you have a branch structure in the tree, in this case, if the mother one is 2 daughters 2 and 3, you can always further decompose this branch tree diagram into the sum of 2 chain diagrams without any branch. Practically, you just compare the birthday of family members and you sum over all possibilities. So that's why I call this birthday rules. But if you are familiar with polygons, for example, you realize this is nothing but take shuffle products recursively among all family subfamilies. So here is one example. You have a 5-side diagram with a branching structure, and you can do this family chain decomposition, resolving it into a sum of 6 chain diagrams. But this shows that family trees are actually overcomplete. It can actually be further decomposed into chains, but at the expense of raising the tree level topology. These family chains are some integrals with total order, some partial order, total order. So it has a standard iterated integrals. So it enjoys all the mathematical structure of standard iterated integrals like the Hopf algebra. And this structure allows us to define the so-called transcendental weight of the function. By identifying the transcendental weight, you can show that these complicated family trees cannot be expressed as the combination of known special functions. They have to be studied separately. These are all very technical, but let me mention some applications. These are applications we did. Since you can do arbitrarily nested time integrals, you can compute diagram with arbitrary number of nested propagations. But here's one example. We consider the 4-point function with 2 massive changes resulting in very complex structures. So if you really want to look for a cosmological guided process with 2 massive changes, you really need this result. You will get a company. Another application is so-called conformal amplitudes. As I said, this is a model. This is not a real model. This is a toy model, which shares a lot of structures with real cosmological collider models. It consists of a massive scalar field with non-minimal coupling to the richest scalar, with coupling tuned to the conformal value. On top of that, we add arbitrary polynomial interactions. There's a lot of structures behind the correlation functions of this model, and people realize that you can actually have cosmic polytopes can only perform twisted cohomology, etc. And in most recent works by Nima and Hamid and his friend, they are now able to find a very sophisticated rule to write down the differential equations for arbitrary tree level diagrams. But with family trees, we can actually write down the full analytical answer directly without even writing the differential equations. These are some details. I do not have time to go into the detail, but just to show you that by saying amplitude, I actually mean 2 different things. One is so-called wave function coefficient. Another is a correlation function. These are conceptually very different, but technically they are connected. So if you look into the Feynman rule for either wave function or correlation function, you'll realize that the integral you need to perform is nothing but family trees. So the whole problem boils down to find an appropriate procedure to decompose arbitrary amplitude into family trees. Here's the rule. You have a very simple rule: decompose any diagram into products, the sums of family trees, so that you can write down the answer for arbitrary tree diagrams directly. Here are some more examples, including the two-side chain and the four-side star. For example, if you look into the differential equation for this four-side star, it consists of a total of 64 differential equations, coupled first-order differential equations. Just imagine how to solve that. But with this family tree, you can write down very compactly the result just in 3 lines. And each factor here is a known hypergeometric function. This slide is just make connection between our result with the energy integral developed by Nima Akani-Hamed and his friends. Basically, the time integral and the energy integral are related by Fourier transform. So by doing Fourier transform of family chain, you can directly prove that what you get from family tree is nothing but the energy integral discovered by the other group. Also, it's interesting to look into the inflationary limit, where you send all the twists to 0, then all family trees just reduce to polynomials. So in this sense, you can say family tree integrals are kind of generalization of polylogs. So let me conclude. The cosmological classical physics provide us a very interesting and promising way to probe very high energy physics, very complementary to ground-based classical physics. And for this to be possible, it is very important to have better ways to analytically or numerically compute these diagrams. And since 2022, we are now able to compute a lot of diagrams that are important phenomenologically, so that nowadays we are ready to template. A lot of things have been done, but a lot of open questions. I will not read this one by one, but I will be happy to chat later if you are interested. That's all I want to say. Thank you very much.
Okay, so I mean,
For this family tree diagrams, we also have some loop diagrams with the generalization.
Sure, it's actually trivial because unless the time integral never form a loop. Right. Time flow cannot form a loop. So whenever you have a loop diagram, the nested time integral term is still true. So this is directly applied to loop diagram.
The state of this machinery is based on Schwinger-Keldysh technique.
That's right, that's right.
In particular, this retardation properties and so on. So when analyzing all these structures, didn't you have any signs, find any signs of possibility of obtaining all this diagrammatic technique as a kind of analytical continuation from Euclidean picture, from Euclidean space time?
Good. So some techniques are actually direct analytical continuation from Euclidean signature, like the spectral decomposition I just mentioned. If you want to compute this bubble, writing it as a linear solution line, so we need to do is to analytical continue the theta to sphere. Now all the modes just become spherical harmonics. The whole problem boils down to the harmonic analysis. This kind of thing. But for time order of the integral, actually we do not need the analytical continuation of space-time itself, because once you do that, the notion of direction of time just disappears. Right.
What I mean is that if you, for example, calculate, for example, non-related, but say, effective equations, motion for in field, in program, in any program.
Yeah.
Some particular case, it's not a smaller effect, but at least is simply to be let remove past problems. Previous definition of it was very advanced. There are possibility, for example, to derive these quick equations for the fields by such a procedure. You will calculate the fraction in the and then perform a kind of analytic continuation, which basically reduces to the replacement of all non-localities by retarded one.
Sure.
So is it possible to construct something like this for this multiple correlator, not just in field, but correlator?
Yeah, these are correlators. These are correlators. But I think for low point correlators, it's possible. For high point, the climatic data is so complicated, making the practical and legal continuation difficult. It's my best. So we can try.
Okay, now we can discuss that. So, assistant speak again. Our last speaker of this session is Donggang Wang from the University of Hungary.
Let's go. Converted to I think I just use this one USB-C. Okay. But I didn't share screen yet. Maybe I should share screen first.
The title of his talk is Possible to Bootstrap Theory and Observations. So, welcome.
Yes. Yeah, should I share the screen? Yeah. Okay. All right, I hope it works. Okay, thanks a lot. So today I'm going to talk about this newly developed research area called the cosmological bootstrap. It's mainly based on a series of works that I have been doing with my wonderful collaborators in the past 7 years. So here's the plan. Here's the plan of my talk. So first of all, I will introduce this new approach, the cosmological bootstrap, or why we are interested in this new approach and how we are going to realize the basic idea and what is the current research status. After that, I will apply this new approach to study three leading scenarios for quantum inflation, single field inflation, cosmological collider, and also the multi-field inflation. And then start the predictions. And then I will present the recent observational package for the prediction from the bootstrap analysis. If I still have time, I will give some comments about hypothesis in the specific space. Okay, so the next object we are interested in as cosmological coordinates, and George already talked about the integration, and here I will just keep it short. Let me just close this. So in cosmology, we know the leading description for the primordial universe is given by the theory of quantum equation. And what is remarkable for equation is that the quantum fluctuations during equation could be stretched outside of the horizon, and they will form the primordial perturbations and the annual equation. Then this tiny
primordial intermediate will be evolved into the CMB temperature and social phase we observe today, and also the after 10 million years of evolution, they will form the galaxies, clusters, cosmic webs, even including us and Shanghai Tech today. Then by measuring the statistical information of matter distribution across the whole universe, we can learn important information for the primordial physics, what is new physics effects during inflation. And nowadays, we already know the 2-point statistics, the power spectrum observation from the legacy instruction surveys and also from the CMB. And now we can go beyond the 2-point statistics, and we can study the 3-point correlation function and also the 4-point correlation function and even higher order. And these higher order correlation functions, they contain much more important information about the primordial physics. And in this case, the cosmological correlators is a unique probe of the beginning of our universe, and also gives us a very good window to test new physics effect and extremely high energy scales. So for new physics effects, normally we study particle collider experiments, and there is the object we are looking at scattering amplitudes. We can draw some final diagrams, like the contact diagram here, and also the exchange diagram with some intermediate message states. Then we can start with the signatures in the collider experiments, and there the energy scale will be around 1 TeV also. Then for cosmology, we are looking at something a bit different. It's the cosmological quality here, and here we draw a different time of there. So time flows from the bottom to the top, and so during inflation, we expect there will be some new physics effects. And it could be new particles, new interactions, new symmetries, and so on. And then this new physics effect would leave influence into the correlation functions and the annual inflation. And then we will test them into astronomical observations. Since the energy scale of cosmic inflation could be as high as into 13th degree, so we expect in this way we can learn about this new energy physics during inflation. The traditional method for computing these cosmological correlators is the so-called yin formalism, or the Schrödinger-Kelvin formalism. So the basic idea here is that if we just look at this space-time diagram for our inflation, then the bulk of the specific space-time can be seen as the duration of inflation, and then the end of inflation it corresponds to the future boundary of the specific space-time. So time flows from the bottom to the top. And here, annual inflation corresponds to the case, the conformal time beta goes to 0. So what we normally do in this traditional approach is to track the time of evolution of various interactions based on specific models. And in the end, we derive the final result for the correlation function and the annual inflation. This is a quite general approach. We can do many complicated and quite helpful computations, and since Maricina developed this approach in 2002, we have been doing this for over 20 years. But there are two major issues for this approach. First one is it's quite model dependent. We need to specify a model first before we do any computation. And also these computations are quite difficult, like Zhongzhi already showed in his talk, and it involves complicated nested time intervals to compute these correlation functions to the end. So this gives us a motivation to start this new approach, the bootstrap philosophy. Now here we want to build a connection between fundamental principles with observable predictions. So for the fundamental principles, it could be something like symmetries, unitarity, and locality. And for observable predictions, if we study particle physics, it will be scattering amplitudes. And for cosmology, it will be the correlation functions we have been talking about. And in theoretical physics, we already have two successful examples in the literature. The first one is the S-matrix bootstrap for particle physics for the scattering amplitude studies. And then we also have a conformal bootstrap that is for the conformal field theory. And here we want to apply this bootstrap philosophy to the studies of cosmology. And here, this bootstrap basically is this kind of thing on your shoes, and you can pull yourself up by the bootstrap, and you don't need this model building project. And for people who read Chinese, I could hear several Chinese translations for this word. All right, so then for cosmological bootstrap, we want to derive the correlation function from symmetry, locality, and unitarity. It's a new trend in theoretical cosmology since 2018, including people like Daniel Bowman, Enrico Pio, Stephen Mentel, and also Nima Penny, Hammond, and Juan Macena, and so on.
And if we compare this new approach with the traditional linear formalism, the time involution approach, the basic idea of this approach is to forget about the time evolution in the ball during inflation. And we just focus on final observable, that is the correlation functions and the end of inflation. And so this is the so-called boundary perspective of time without time. So in this way, there are both advantages at the conceptual level and the practical level. I will show it a bit later. Now let's just look at one very simple example. It's the first realization of the cosmological bootstrap. Nowadays, we call it the considered bootstrap. And this was proposed by Ima Cunningham, Daniel Bowman, Hayden Lee, and Deep Pimentel in 2018. So the basic idea here is to use both space-time symmetries for the system. And here we have these four types of space-time symmetries. The first two of them are quite simple: the spatial translation and spatial rotation. If we consider their implication, their constraints on the final observable, the correlation functions, and the end of inflation, then basically these two symmetries will tell us which kinematical variable to use. And here I will just show this 4-point correlation function as one simple example, and then we are left with these two momentum ratios. And so basically the correlation function will be a function of these two momentum ratios, U and V. And then the third symmetry is the de Sitter dilation, which corresponds to the time translation in flat space-time. And in this case, the symmetry tells us that the correlation function in the end should be still invariant. And the last one is the de Sitter boost symmetry. And this one is the most non-trivial one. So here we can see the generator of the symmetry is a bit complicated. And then if we consider the constraint, the implication for cosmological correlators, still we can see this 4-point function as one example. We find we can derive something called the conformal wider identities on the de Sitter boundary when the conformal time equals to 0. And this is the set of differential equation that should be satisfied by this 4-point function S. So what we really mean for this differential equation, I can write something here, you can see, is let's just look at this 4-point correlator as channel exchange with some intermediate massive particle with mass I. Then what we are really doing there for the correlation function, for the differential equation, is to use this differential operator. And the effect of this differential operator is to collapse this intermediate massive particle, this intermediate massive line, and it gives you a contact diagram like this. So this contact diagram is something simple. We can we already know it's analytical form, and then this delta U is a second order differential operator there, and this equation can be solved by imposing physical proper boundary conditions. And in this way, we derive the full analytical solution of the correlation functions on the future boundary. So sure. Yeah, the kinematical variable is your choice. So basically, these two symmetries tells you that you can just use these two independent variables for.
Yeah, but can you have also satisfy like the dot cross ratio manifest satisfied? I think it's already satisfied.
Right. Yes. Yeah.
If you also have P, dot cross ratio,
right.
Satisfied the special form.
Yes.
But here is
yeah. This one already satisfies the direction symmetry function. Yeah.
I have cross ratio. That is also boost.
We didn't use cross ratio here, so we didn't use it's still U and V, but it's a bit different from the one in the conformal, right? Yeah.
I wonder why.
Yeah. Here it's everything is still perturbative, and also everything is still in the momentum series. We are not working in the real space. All right, so. One interesting thing to notice here is that for this differential equation approach, there's no time involved in this description. And since we can see this differential equation, time disappears. And one way to understand this is that time is not a fundamental variable. Time is not a fundamental quantity. It's a kind of emergent quantity. By changing the pattern of the parameters on the feature boundary, what we are really doing is to probe time evolution for different type of interactions in the ball. So in this way, it's kind of emergence of time. And we're trying to understand it in cosmological background. We can have a timeless description for the evolution of the whole universe based on this idea. And in addition to the conceptual understanding, we also have some practical advantages. And first of all, it's a model independent approach, since we do not need to specify a model to do this kind of computation. And it's also quite a powerful computation tool, like shown here, and also Johan's talk, and also Johan's poster has already shown some. There's a lot of new computational techniques has been developed in the past several years. It also gives us a quite systematic classification of all the predictions from cosmic equation. So in the rest of the talk, I will try to use the bootstrap measures to derive all the possible inflationary three-point functions. And in particular, I want to identify the large signals and also new shapes that could be interesting for observations. And in the end, I will test them in the real data. If there are some questions for this part of the talk. All right. Now the leading scenario, the leading observational target we are looking at the triangles in the sky. So if we look at the sky, we can draw some triangles like in the CMD map, and also in the large scale structure surface. And then all of these three-point correlation functions of all of these triangles could be traced back to the unknown equation, and they were generated by the three-point correlation function of the primordial curvature perturbation Z. And what we normally do is to start it in the Fourier space. It's the primordial bispectrum. And here, for this primordial bispectrum, we have two important parts. The first one is the set parameter XNL. Basically, it tells us how easy or how hard the signal could be detected. Then we also have the shape function S, which is the function of the three Fourier modes, P1, P2, P3. And this shape function, it contains a lot of information that could be interesting for the primordial physics. It's a major focus of this talk, and it's also the main target for like CMB, scale structure, and also continuous centimeter observations. Then in series, in our current understanding, if we assume the inflation theory is nearly still environment, and everything is weakly coupled, then we can just look at tree-level leading order contributions. Then there are three different types of primordial non-Gaussian signals. They correspond to these three different types of time diagrams. So the first one is super simple. It's just this contact diagram, and that is due to the self-interaction of the infrequent fluctuation. So all of these external lines are the infrequent fluctuations. And this just tells us corresponds to the single field inflation scenario. Then in addition to that, we may also have some intermediate massive states, and this is a massive exchange diagram. And this is the so-called cosmological collider that we already talked about. Then the third case is that in addition to the infrequent external lines, we also have some additional line scatterers. And this is the scenario called multi-field inflation. Now the question becomes, can we use the bootstrap analysis to bootstrap measures to derive all the possible predictions for this correlation function in these three different types of scenarios? What we want to do is to classify all the possibilities. And also, we want to identify if there could be new traits or new technologies that can be tested in observations. Now let's look at these three different scenarios one by one. And the first one is a single field inflation. And the standard prediction is given by a shape function called the fractal non-Gaussian. And this is what the shape function looks like. So this shape function is a function of the two momentum ratio, K1 over K3 and also K2 over K3. So this is the kind of typical prediction from single field inflation. There are two important things to notice here. For single field inflation, in the most general situation, the Boost symmetry are actually broken. We will be able to have this kind of Boost breaking interactions like phi dot Q, phi dot di phi square, phi double dot di phi square, and so on. And this is commonly seen in models such as QX theory, DBI inflation, and also ERQ inflation, and also the one with higher derivative operators and so on. And normally you would have a small sound speed with the sound speed for the infrequent fluctuations smaller than 1. And then the signal there could be enhanced. Technically, we have this relation between the size of the oscillating signal FNL collateral. It's proportional to 1 over CS squared. So if we have a small sound speed, then the signals would be enhanced. Then the bootstrap analysis was performed by me and also the Cambridge group, especially a pilot several years ago. So what we are trying to do here is to first write down ansatz for the correlation function. Since in this case, it's the correlator from the single massless interaction scale. And then the ansatz could be very simple. So upstairs, we would have a polynomial, and the polynomial is a function of 3 symmetric polynomials like kt is k1 plus k2 plus k3, and e2 and e3 are the other symmetric polynomials. Then downstairs, the denominator we have k1 times k2 times k3 times kt to the power. And then based on this ansatz, we keep imposing constraints from the unbroken symmetries and also locality and unitariness until we fully fix the form of the correlation function. And in the end, indeed, we develop a complete set of 5 spectrum templates from single field equation. And it's a generalized version of this equilateral number setting. So it's not only this very simple form, it can have other equilateral type shapes. And then for the second case, the cosmological collider, here, the key insight is that if we look at the squeeze limit for the inflationary 5 spectrum, then if we take one side of the momentum triangle, it's much smaller than the other 2 sides of the triangle. Then this squeeze spectrum, it contains information about heavy particles in the during inflation. So this exchange new heavy particle. And this is the general expression of the squeeze spectrum. And we have this cosine oscillations. And the frequency of the oscillation actually tells us about the max for this new heavy particle. And then we also have this angular dependence. So the angle is between the angle between K long and K short here, this angle. And this is the round polynomial, and the index of the round polynomial tells us about the spin of this entire particle. The bootstrap analysis for the cosmological collider was performed by me and Deacon 2 years ago. What we are looking at is just this massive exchange, very simple there, but we consider the most general situation, the most general all the possibilities for this massive exchange level. So all the external lines are the ones for the infrequent fluctuation, and they have the sound speed CS. Then for the internal line sigma, it could be a massive particle with any mass and speed, and also we include the sound speed parameter C sigma here. Then the bootstrap allows us to capture all the possible phi sigma cubic interaction, and also all the possible phi sigma horizontal interaction for both scalar exchange and spin exchange. And these are the several examples I show for the possible cubic and also quadratic interactions. I'm not going to show all the technical details here, but in the end, it's quite remarkable. We found one formula to find out the results. So we start with the scalar seed function, it's IX. And the scalar seed function, its full analytical solution could be derived by solving this differential equation here I wrote before. And then we use 2 sets of differential operators to map this scalar seed function into the infrequent bispectrum. We use the spin raising operator, this U, to change the spin of this sigma field. And then we use the weight shifting operator W to capture all the possible phi sigma cubic interaction. And then in this most general result, indeed, we found interesting cosmological collider signals in the bispectrum. And for the first 2, I already mentioned 2 slides earlier. It's oscillation and squeeze limits given by the mass of the new higher particle, and also the angular dependence from the spin exchange. And the shape function I will show you a bit later. Here I want to highlight a new shape from the non-trivial sound speed that was not identified before. Here, the situation is that if we consider there's a hierarchy between the 2 sound speed, the sound speed for the sigma field, and also the sound speed for the inflaton fluctuation. Then this oscillatory signals, this collider signal could be even shifted outside of the squeeze limit, and they would be they could even appear around the equatorial configuration of the momentum triangle. So previously, if we just look at the squeeze, the collider signal is these small wiggles in the squeeze limit, this color, and this blue surface is the standard equatorial shape from single field inflation. And then if we change the hierarchy between the two sound speeds, then we can see this orange shapes. The oscillations were being shifted outside of this small corner, and then it also appears around the equatorial configuration. So we call it the equatorial shape. And this provides large deviation from the standard predictions, and it provides some interesting targets for the observational test. Now we managed to bootstrap the first two scenarios, single field inflation and also cosmological collider. We are left with the last one, it's a multi-field inflation. And the standard approach for computing non-Gaussian entities in multi-field inflation is an approximation called the separate universe approach of the delta n formula. And then people derive this prediction, the local shape of non-Gaussian entity over 20 years ago. And the question we are trying to answer here is that if this computation is complete or not, since this is still an approximation. In this approximation, we are trying to say if anything was missed and if there will be an interesting new physics effects. But when we talk about multi-field inflation, it's like Pandora's box. There are too many possibilities. They have been extensively explored after 30 years. And normally the predictions there are quite model dependent, and we don't have uniform things. And that is bad news for the bootstrap analysis. But then we realize that there is one very important aspect for multi-field inflation is that there will be two types of perturbations. One is axial curvature perturbation, and then the other one is a curvature perturbation. So the curvature one is related to the inflation fluctuation. It's related to the external lights. And then the axial curvature perturbation is one that is associated with the additional light scatter. And there is a conversion process in the multi-field scenarios. And this conversion process is basically described by this massless exchange diagram. And the next thing to notice is that this massless exchange is not the massless limit or the massive exchange. If we naively just take the massless limit of this massive exchange diagram, we found what we would have 1 over m squared, and it's divergent. And this is just the IR divergence from interaction light scattered in the vector space. And in this case, the correlator becomes IR divergence. And to deal with this IR divergence in the cosmological bootstrap, we need to modify the conformal weather identities we talked about earlier. And we need to introduce some conformal anomalies, which corresponds to some additional thought term in this differential equation. So we will have an anomaly term here. And this anomaly term depends on the error cutoff. So here, I don't want to go to too much details, just one simple example for this 3-point scatter seed function. Previously, we can just write down this scatter seed function as a function of this momentum ratio U. And here we also include the cutoff, the late time cutoff eta naught, which is the underwood equation. Then in the case this sigma field is massive, so we just go back to the standard scenario. And we can just write down this differential equation and everything is fine. The correlator is IR silent. But for the case sigma field is massless, the correlator becomes IR divergent. But we will have this additional source term that is caused by this IR cutoff scale eta naught. And then we need to solve this modified differential equation for the boundary correlator for this scatter field function. And after doing that, we derived the true shape or multi-field non-Gaussian from this massless exchange diagram. And here is the final result for the local shape. And the or we call it the true local shape. And if we just compare this this shape function with the standard local ansatz, we'll see this one is a bit more complicated. And it's mainly because there will be two logarithmic functions. And the first one we call it the logarithmic k equal, and this is the one from the cubic vertex here. And then we also have this logarithmic K1, K2, K3 pose, and the other one from the linear mixing. So this singularity structure were not captured by the Dirkman formalism computation, and the logarithmic singular secular growth behavior. So notice that there is this error cutoff, this latent cutoff cannot. If we take inter not goes to 0, and this logs becomes more and more dangerous. And this is the secular growth behavior, and actually it just tells us about the conversion process from the isocurvature perturbation to the curvature perturbation. So these error divergences, we already observed that there will be this logarithm of secular growth. But the question here is that if they are really divergent, do we need to worry about higher order contributions like loop level divergence? So for the loops, if we just increase the number of loops and also increase the number of interaction vertices, then this secular growth behavior could become more and more dangerous. And actually, there was a controversial claim by Polyakov many years ago saying that the zero spacetime is not stable, and just because of this error divergence behavior. But I will come back to this point a bit later. So now let me just summarize for the bootstrap part of this talk is that we apply the bootstrap analysis to study these 3 different types of scenarios for cosmic inflation and single phase inflation, cosmological collider, and multiple inflation. And in the end, we derive the most general result from these 3 different Feynman diagrams, and we identify the new phenomenologies. For the next part of my talk, I will talk about the observations, and we can perform the observational test for this bootstrap result. I will mainly focus on the cosmological collider signal, since here we have 3 different types of different new phenomenologies. So normally there could be comments like this. It's quite interesting, but so the signals are super difficult to be for observational tests, and maybe they would never be detected. If this is the comments like 1 year ago, I don't have really good argument against it, but now what we managed to do is to get them tested in the real data. And this is mainly because of the recent progress in the data analysis of the CMB. My colleagues in Cambridge developed a new pipeline, the data analysis pipeline called CMB BEST. The CMB best spectrum estimating is a public Python pipeline. It makes use of the latest CMB data from Trump satellite, and it works for any number of sensor shapes, even including the ones with these oscillatory features and cosmological colliders and so on. So in general, it's quite a powerful tool to test primordial non-Gauss center. So what we did recently this year is to search for the cosmological collider signal in the ground data. And so this is like a prediction from the cosmological bootstrap analysis. Then we put it in the CMB data, and we were trying to say if there will be interesting constraints from the temperature and also the polarization observations. And here I will just show 3 examples. The first one is the oscillations in the squeeze limits, and this is a shape function. What the shape function looks like. And here is different mass for the external for the intermediate mass particle. And these blue surfaces are the standard predictions from single phase inflation. So it's a background shape. Then on the top of that, we have this collider oscillator signals. So it's small wiggles in the squeeze limits. And then we also have angular dependent shapes. And this is the one from the metric spin particle. And here is the example from the spin 2 templates. And here, in addition to these small wiggles in the squeeze limits, we also have the angular dependent profile. And so this is the overall profile of the whole momentum triangle configurations. And also it's for different mass scales. And then this is the result from the data analysis. For the scalar templates I showed before, we can say FNL equals 0. We are scanning over the mass parameter here from 0 to 6. And this is the 1 sigma and also the 2 sigma control. So we can see for FNL equals 0 from many parameter spaces, it's still fine, it's still within the 1 and 2 sigma control. But there's a regime with maximum significance. The FL equals 0 is excluded outside of the 2 sigma control. And for the maximum significance, we found sigma equals 2.3 for mu equals 2.13. And after taking into account the loop elsewhere effects, we found the most significant signal is 1.8 sigma. So we were joking about this is that we got 1.8 sigma detection for the quantum multiplier, but for sure this is not enough. There's still possibility this is due to some statistical fluctuation of the data. And in the future, we need more data to check if this is a real physical signal or it's just some problem in the data. And then for the spin 2 templates, we also scan over the parameter space from mu equals 1 to 8. And still we can find the most significant signal is for mu equals 4.7. And it's also around 2 sigma. And this is the new shape I mentioned, the equatorial collider shape. And this shape function provides a big deviation from the standard single field inflation prediction. And in this case, still we scan over the max parameter mu, and we see the most significant signal happens when mu is around 4. In the future, we can use large field structure and also 21 centimeter surveys to search for the quantum multiplier signals. And for large scale structure surveys, it contains much more data than CMB since it's a 3D map, and CMB is a 2D spherical surface. But this one is normally contaminated by the late-time gravitational evolution. But for the 21 centimeter intensity mapping, in principle, we can reach the dark ages, and we can map the matter distribution across the whole universe in the dark age of the universe. And this can give us a very powerful constraints about the primordial foundation. And in the future, there will be huge improvements for the observational test. And this is a picture from the Snowman white paper 2 years ago. And for the CMB, we still have some room to improve it, like CMB stage 4, early experiment, Siemens observatory, and so on. But in the future, there will be more and more large scale structure surveys. Now we already have the both data, and actually around the same time this year, the group from Princeton IIS, they also use the both data also search for the quantum multiplier signal. And their error bar is still quite huge, it's like several thousand or even 10,000. But in the future, we will have easily SST, especially the square X, and it will lower the error bars or the number of authentic signal, and it would be comparable with CMB and even surpass the CMB constraints. In the end, I will just comment about the conceptual side of the quantum multiplier bootstrap. We still know very little about quantum field theory in the Sitter space-time and also the quantum gravity effects in cosmology. Like I already mentioned, there are many open questions. Like I already mentioned, there will be there will be the error divergence issue in the Sitter space-time, and also in addition to the scalar correlation functions, we also have a tensional authentic graviton correlators. And we also want to understand better about the analytical structure in the loops. And in the end, we want to go beyond the perturbation theory and make some connection with the holographic description of the Sitter space. And I will just briefly talk about the error divergence, since I still have 2-3 minutes, maybe. Okay. Since I already mentioned a bit about the error divergence issue in perturbation theory, and now I want to go beyond the perturbation theory to check if this error divergence is real or not. What we are using is the wave function of the universe, capital percent, and everyone knows this relation P equals capital percent mod square. Then for this equation on the right-hand side, we have the wave function of the universe. And this is a central object in the bootstrap analysis. And in perturbation theory, what we normally do is to start this object, this wave function coefficient is small, and this wave function, this small segment, and this wave function coefficient is object that is related to the correlated functions. And there will be some simple relation between the wave function coefficients and the correlated function. And normally what we do is a perturbative analysis in the bootstrap. And then for the kids with error divergence, we found this secular growth behavior. Then on the left-hand side of this equation, we have another approach, another formalism is called the stochastic inflation. And there we have the so-called Fock-Clarke equation. And this is believed to be non-perturbative. And in the end, there's no secular growth behavior, and we found an equilibrium solution. So it looks like we are resolving some of these logarithmic secular growths. And so what we are trying to do in this work last year and also in a review paper we are writing right now is to build the connection between these two different approaches to say which part of the wave function coefficient is being resolved in the stochastic formalism. And there we found one simple result is that the Fock-Clarke equation actually is equivalent to the settle point approximation of the wave function. And this is the semi-classical piece of the wave function. And so in this case, the stochastic inflation can be seen as a summation of classical rules from the semi-classical piece of the wave function. And we also perform a non-perturbative derivation for the Fock-Clarke equation, and there are two parts. And the first part, the time evolution, the time dependence of the probability distribution comes from the wave function itself, and this is given by the Schrödinger equation, and this is a drift term in the Fock-Clarke equation. Then for the second part, actually the arbitrary equation. So we are using the potentially arbitrary equation, and the wave function in the end gives us the second term, the diffusion effects. All right, and since I'm already a bit over time, and I will just stop here. Here is a summary slide, and thanks for your attention.
Okay, thanks. So that's all. No. Oh, okay, let's start the speaker again. Let's have all the discussion.
I'm giving my talk tomorrow. My question is, normally I video record my talk. Could you do it with Zoom so that I don't need to use my laptop?
We have broadcast over there. They can record this.
I want to record the entire thing. Normally just record it like this.
And also that's everything that's
You
here.
did already.
Yeah.
Could you give it to me?
Oh, yeah, yeah.
I want to use it.
Yeah, I have. We'll give you that after the.
Fantastic. So you will record them.
Yeah, you can just contact Alexei. They already have that on YouTube.
Very good. Yeah, so I can post there and record.
Yeah. Alexei's one, the Zoom, they record that Zoom, everything on Zoom, and push that to YouTube. If you want more, for example, here I mean, on the link version, we can have that mastered. So how should I send it to you?
Because
You can give me your email.
Yeah. So you're saying by default you record everything.
Yeah.
But you put on YouTube only Zoom version. But you have everything,
Yeah.
and that everything you keep for what, for?
No, we don't want to push that on YouTube because we're in China. And we can really see something, so it's difficult.
But
push
what I can,
everything
you
to
can give me the thing, and when I go,
Yeah, we can give the video.
for that thing.
Yeah.
I will give you
The email.
Yes,
you can just
give you the output.
email. How should I?
Or-
Oh, I just sent them.
Yes.
And we see you by the change. Is that positivity as well?
Yeah, we're trying to say there could be like cosmological complication. But nowadays it's not right. So there's still some satellites, but since the first space now we can consider forward the main satellites. Cosmological constraints to have example about corridor is more complicated software. It's not so clear what is the power limit, it's not so clear. So what is the constraint on corridor? But it's a question people are thinking about.
Yeah, that question. Assumption. I don't know whether it's in one talk, but I'm arguing that. Into graviton is possible. It goes. So probably. In a negative probability, so since you mentioned positivity, you're trying to build that in. I'm saying you may not want to build that in because it may actually be a negative property in some non-gravity. Quadratic gravity. There's been two goes, and I'm saying that maybe allowed. You still have to make.
Yeah, I heard about the talks, but yeah, and that's what.
Well, I mean, you don't need to know about the talk, you just need to know that there might be a particle up there close to the Planck field, tipping field, I don't know. But it's not, doesn't tell us that equal positivity is negative. So all these assumptions about positivity, because question is, natural up. You change the sign, you have an exchange of mass particles, but the sign would be different. Does that change your lots in any way? Does it change the size?
Yeah, I think it would be very different. For free particle, I think it would be. There will be stability for this.
No, there's no instability. It's positive energy.
Yeah, I think the important information is what could be the case on supervisor scale. Look at this particle behavior on supervisor.
Whether normal, positive, normal, positive energy, normal. So it only shows up when the amplitude is negative. The exchange of the particle. Sign of the amplitude is not what's in. It's all that. So is your effect linear or not line? I mean, you're drawing that diagram here. Yes. This is just an amplitude. You're sensitive to the sign of that. Or you're sensitive to the mod squared of this thing.
The correlator is.
Measuring the actual coordinates.
Yeah, the correlator is benefit sign.
Yeah, and that's what you're actually sensitive to.
Yes.
So you're sensitive to the sign of this. That's this problem.
Right. Yeah, I think the really important thing is what is the behavior if this is for example goes in.
It's a straight through particle dimension. It just has the opposite symbol.
So you mean we can write down something like small function sigma. Let's say this is sigma. And in the standard case, we can just write down the one function here is like a function here. So a function and we this already.
So you reference this is function says time and yeah, subject, you know. Right, I don't think, yeah, this is just a very transforming moment. Yeah, we just have one more sign.
Then I think it doesn't matter if you just put the minor sign here.
Yes.
Then the propagator of this object actually it's like sigma k times sigma k star.
Oh, sorry, no, I'm talking.
You're talking about this one.
Yeah, well, I'm talking in the logic space, I'm talking the final property. And it's the wrong sign. Final property. So which of these objects corresponds to the translation of the final property? If this is recorded, this is what you guys
This is probably from one time eta to another eta time.
So in momentum space, I'm saying that's stratified. A final propagator with a wrong overall size. Isn't this the thing that shows up here?
Yes.
Yeah, okay, so this will have to do. Sign that you're not used to. So without that affecting your final.
Yeah, then if we just consider different copies, copy have different signs and that's it's not possible to distinguish.
No, not the copies. It's just it's
Yeah, I mean, we also have the freedom to change the sign of the copy.
well, it looks like you're squaring it, so that will make a difference.
It could be different copy.
Yeah, okay. So are you saying that's a different thing you'd look for? Sign showing up in that way, in your sensitivity. So it sounds like you may be sensitive to yours.
Yes, since now we are really interested in shape functions, and the shape function doesn't matter about the sign.
Yeah, but the big function is standard physics. I mean, we know what these propagators look like, so you're not expecting new physics there. I mean, what new physics? Or you just, it's the existence of some mass given. Hoping to see. I mean, your plots of your wavy curves. They depend on some overall sign. Yeah, so if you flip that sign, the way to go the other way. Is that right?
Yeah, I understand. Yes, but it's just it's not possible to distinguish it from the others. The one with the normal sign and the one with the offset sign. You can just change your copies and it will be different formats.
What? You can change the copies and absorb the sign?
Yeah, if you have the shape function, that's why so the shape function, 1 K2 K3.
Yeah.
And then you change the sign here. It becomes a new shape function that's this shape function and this shape function are not distinguishable from each other. So just corresponds to redefine your FNL part.
What's happening?
This FNL is in front of everything. So you have the pi spectrum. Pi spectrum equals L times. And we did what we already did in the shape function. The FNL could be positive one.
And it has no effect on the final form.
Yeah. What I'm talking here is something that normalized. One particular and when you normalize it, then we grant that it's and this B is the vice president is equal to 3.
Yeah, I can understand it. Is there a sign? Oh, sorry. Yeah, I'm not aware. Maybe there will be some positivity constraints. Maybe some constraints on this. You just lost me. Hello. Yeah, but we still don't have it yet.
Can you hear me?
Even if there was one.
Sound.
Can you hear me?
So go to Zoom. I think your mic setup, that thing you have done yesterday. Go to the larger setting.
There's a lot of background noise. I cannot hear what you're saying.
Yeah, you can. Oh, no, he made it here.
So Antonino, you here?
Yes, yes, I'm here. I'm here.
Ah, great, because I was talking to you like to a wall and there was nothing.
Maybe before, I don't know. But anyway, so can you see my screen that I've been sharing?
Yes, if you make it full screen, it would be really amazing.
Okay, sure. Get that?
Yes, kind of this. Now we just have to find our chairman. Wait a second.
Yeah, okay.
I'm gonna to find chairman as a kind of roaming around. Wait a second. Because it was some delay after
Yeah,
last.
no, I understood. Don't worry.
Wait a second.
Can you see the other slides?
Yes.
Okay. And this other one?
Yes.
Okay, great. Sorry, this work.
So, you make sure that, well, if you want to, in a series, you might. Oh. Probably it is. This thing,
Speaker one. Testing, sorry.
There's a lot of background noise. I can hear someone is talking to me, but not very well.
Oh, so maybe what's Okay. Hi, I'm talking about.
Hello?
Hi. Yeah,
You can't see me, right? And can you hear me?
yeah, I can see, but I mean, there's a lot of background noise, so I cannot hear you very well.
Oh yeah, but he's not showing here. What is this? This is my fifth house. Then I think you should plug this thing in your ear. Helps. Listen. No, so you will plug this thing in your USB Type-C, this one. Yeah, it can be why. So let's try again. Hello?
Okay, now I can hear you perfectly. Yes.
Okay, good. So maybe we can start. Should I close this? Yeah. Okay. Okay, so maybe we can start. Okay, let's start our last session for the day. Our next speaker is Antonino Marciano from Fudan University and FN. The topic is stochastic Ricci flow, emerging complexity in quantum and analog gravity. So let's welcome.
Okay, thank you very much to the organizer, to Alexei, Anna, and all the organizer for this. So I will talk today about the stochastic Ricci flow from the point of view of complexity, emergent complexity, and connection that can be driven with quantum gravity and analog gravity. So first of all, I want to introduce something which is basically a new perspective or a novel perspective that is connected basically to introduce Langevin equation for the relaxation toward the equilibrium of four quantum fields. So this, as I will explicitly, let's say in a few slides, is connected to the stochastic quantization work by Parisi and Wu. And the main point is that this is a novel path toward the understanding of the breakdown of the symmetries as connected to the equilibrium out of equilibrium dynamics of complex systems, in which that can be also considered as a particular way of realizing an RG flow from an effective point of view, in which there is a noise, which is a stochastic noise, okay, for the system that evolve toward equilibrium. So this in particular, we will discuss this today for what concern the application for, let's say, the gravitational field, and the gravitational field at equilibrium in the infrared following this RG flow will be basically providing the Einstein equation of motion that will be written in, let's say, probably non-standard or orthodox, well, is orthodox but non-standard way, which is basically introducing the Ricci target, which is nothing but a reshuffle of the energy momentum tensor, so that you can write the equation of motion as the equation of motion as a Ricci tensor minus Ricci target. So let me just remind very quickly the different perspective of quantization, method of quantization that can be considered. And the first, let's say, is of course the canonical quantization from a dynamic perspective. So we consider any kind of a mechanical system with a certain Lagrangian that will be function of the position of the, let's say, degrees of freedom and their velocities, and we extract, let's say, calculate the conjugated momenta of these degrees of freedom, and then we invert the conjugated momenta and Lorentz transform arrive to describe the Hamilton function, and then we minimize the action and we find the equation of motion, which is the Hamilton equation of motion, by introducing a Poisson brackets that provides a metric, let's say, in the symplectic structure of the phase space for the position and momenta, okay, of the degrees of freedom of the system. And quantization is provided by replacing this Poisson bracket with the commutators. As we know, this is the say philosophy of Dirac, that any dynamical theory must be first put in its Hamiltonian form and then should be quantized, which is exactly what he did for gravity. The other perspective, as we all know, is the one that concerns the path integral quantization, which is very much connected and intertwined with the ensemble average perspective in statistical mechanics. So we consider fields, in particular in 4 dimension, and there is a deep connection with statistical field theory. So we have a connection between generating functionals or partition function through a Wick rotation, and the same also applied to the connected Feynman diagrams and free energy. So in this scheme, there is a difficulty in handling with the symmetries, that is due to the fact that, I mean, its dynamics in both cases has to be limited by hypersurfaces in phase space that are dictated by the symmetry itself. So these constrained upper surfaces become basically operators that act on the physical state to annihilate them in order, and these are constraints that must be solved in order to quantize the system. On the perspective of the path integral formulation, we have that these constraints hypersurface are imposed through some delta Dirac in the path integral, let's say, sum over the quantum mysteries. But these bring, let's say, if, for instance, is implemented for gauge fields through the for the Popov determinant, this brings two problems like the Gribov, let's say, ambiguities, while indeed finding, let's say, the imposition of the vanishing of these hypersurfaces of constraints. So if you look at this, for instance, for gravity, you see immediately that if you consider the ADM, let's say, splitting variable in the Hamiltonian splitting, so we have your manifold, eventually globally hyperbolic, and you split it in some hypersurfaces which are space-like, and then you have a time flow which is orthogonal along, let's say, some normal orthogonal to these hypersurfaces. So the dynamical degrees of freedom are the component of the trimetric on these three-dimensional hypersurfaces, to which is connected, let's say, the extrinsic, well, to the conjugate moment of this is connected the extrinsic curvature, in the sense that the extrinsic curvature is the Lie derivative with respect to the normal, which is orthogonal to this to these hypersurfaces. And the Lagrangian then, I mean, it's enables to write then through following the usual, let's say, Legendre transform, the Hamiltonian in ADM formalism. And we immediately see that we basically introduce two Lagrangian multipliers that are the shift vector on the hypersurfaces and the lapse function along, let's say, the timeline that are orthogonal to these space hypersurfaces that have, let's say, a conjugate momentum which are vanishing. This conjugate momentum that are vanishing must be preserved along the evolution, okay, which bring basically to the imposition of secondary constraints to the system that are basically nothing but way to write part of the equation of motion, of the classical equation of motion of general relativity. So basically a combination of this, as you can see, is basically providing, oh, here there is a typo, it should be NH, is basically provided the, let's say, is basically providing the the Einstein equation of motion, the 0I and 0,0 component of the Einstein equation of motion. So these generators are nothing but the super Hamiltonian, that is the generator of the time reparameterization of time diffeomorphism, let's say orthogonal with respect to the space hypersurfaces, and the super momentum which generate the, let's say, space diffeomorphism on the space, let's say, hypersurfaces. And this can be seen as through a Poisson bracket. This basically the joint action through Poisson bracket is consistent with the Lie derivative with respect to the normal for the super Hamiltonian and to the shift vector, let's say, on the hypersurfaces for the super momentum for the space diffeomorphism. That means that the total Hamiltonian on the system vanishes. This happens at equilibrium, so when generativity holds. So now the point is that if we consider the symmetry in general relativity, summing over these histories from a path integral point of view by imposing these constraints basically means that we are imposing the system to stay on its classical equation of motion. So part of the system, let's say part of the sum over histories, cannot fluctuate over the classical configuration, over the classical path. But the classical path are super constrained and imposed in the quantization of the system and cannot emerge then in this perspective. So a different way to deal with this is the stochastic quantization perspective, which is very deeply connected to stochastic, let's say, quantization of mechanics, Alan Nelson, and then to a different way of thinking. This has been, let's say, investigated back in the time in 1980 and then published in 1981 by Giorgio Parisi and Yonchi Wu. And basically the idea is to introduce a stochastic time, but I mean, the name stochastic is improbable. This should be called thermal time, is really connected to a kind of heat flow. Is actually heats and heat flow, in which the drift term are the classical equation of motion, so the variation of the action of the system of a field that is here a generic field phi A, where A is a collective indices that can be denoting just a vector, a scalar, a spinor, or a tensor, okay? And the idea is to introduce then, I mean, it's the, let's say, out of equilibrium dynamics with respect to this thermal time with stochastic noise, okay? The stochastic noise may have different origin. Can become from integrating out high degrees of freedom, can be generated by chaotic chaos, so chaotic effect. So we can discuss about that, of course. And the stochastic noise, let's say in the easier way, we can consider this is a stochastic noise, which is a white noise, and has a distribution which is Gaussian. So if we do that, we can then take the expectation value with respect to this noise, and we can see that, I mean, it's automatically there is a theorem that allows to see that this is equivalent to the ensemble average with respect to the probability distribution, which is recovered by solving the Fokker-Planck, which is associated to the Langevin equation that I was showing you before, okay, in the previous slides. So on top of that is very important also the kind of stochastic calculus which is chosen in order to achieve, let's say, this stochastic and thermodynamic out of equilibrium. I say out of equilibrium because, of course, as it is clear, equilibrium corresponds, okay, in the first equation that you see in these slides, to having just the variation of the action with respect to the field equal to 0. So these are the classical equation of motion. Whenever you fluctuate over it, because of the presence of some stochastic noise, you have an out of equilibrium and dynamic because of the presence of the kinetic term, let's say, relation. So the stochastic calculus is relevant here because we cannot impose the standard calculus in this picture, but we have the choice of which is consistent, I mean, with the fact that we are using a stochastic variable, and because I mean the noise is stochastic, and then the 2-point and n-correlated endpoint function must be convoluted with the stochastic noise. So the stochastic calculus can be usually chosen to be either Stratonovich or Ito. And the one which is actually consistent with, let's say, the covariance of the superspace, for instance, for general relativity, is the Ito calculus. And the Ito calculus is a non-concommutative calculus, so does not fulfill the Leibniz rule. So it's connected to basically Hopf algebra, which is quantum groups. And also from the point of view of the way a functional F here, for instance, of any kind of, let's say, field of the system that you're considering, can be considered in terms of its derivative with respect to the thermal time, or stochastic time, So the stochastic Ito calculus introduces a quadratic nonlinear term, which is relevant at the level of the physical consequences of this. So the Fourier-Planck, as I was saying, whenever the system is extremized and converged toward equilibrium because the noise is disappearing, provide in asymptotic, let's say, time regime, a solution which is nothing but the expected in the Euclidean case, but then I mean this, of course, in the Lorentzian case becomes the weight for the path integral formulation, but in Euclidean case provide the negative exponential of the action. And we have, let's say that the Euclidean path integral measure then is recovered at equilibrium. And this is telling us that basically all the theorem that we know from the point of view of statistical mechanics can be applied here as well. So the other point which is relevant when we consider the stochastic quantization of field is the fact that the propagator that you consider as average ensemble average with respect to these probability distributions that depends on the thermal time have a part which is nothing but the part that you would have at equilibrium, which is gauge invariant and is, let's say, the part that does not contain any kind of divergences. And then you have a part which is, let's say, divergent, okay, in the equilibrium limit, and is gauge dependent. And this is the part that, I mean, it has to disappear when, of course, we converge toward the equilibrium and we recover the symmetries that are the symmetries that we have at equilibrium. So in this approach, there's no need of the Faddeev-Popov, let's say, determinant, and this has been applied by Parisi and Wu to gauge theories. As we know, gravity is a particular gauge theory, okay? And then we can apply, of course, this to gravity. So if, for instance, you take into account Einstein-Hilbert action for gravity and plus complemented with matter, we can immediately write the Langevin equation which is connected to that. So what we have done with Matteo Lulli and Xiao and Shan has been to consider a multiplicative ansatz for the noise. So the noise is in the equation, okay, the one in the, let's say in the box, in the first box, the upper one in the first box. So the last term is eta tilde, is the scalar component that multiply the fields, okay? So this is the scalar multiplicative ansatz that we have been deploying. But previously, let's say that was room in 86 to consider Langevin equation always in the Lorentzian with Lorentzian signature with additive tensorial noise. Okay, so what we've done has been to apply a scalar multiplicative noise ansatz and study this in the same framework, let's say that Rumpf was using, including the presence of the Ito calculus, which is consistent with the covariance, as I was saying, in the superspace of the gravitational field. And also, let's say that you have to consider that for this Langevin equation, the drift term, okay, which is the one that at equilibrium gives the equation of motion, is provided by contracting the variation of the action, the Einstein-Hilbert action plus matter, implementing matter if you have also matter, with supermetric, which is a De Witt supermetric. And for a choice, which is a particular choice of the parameter lambda, which is equal to -1, you have the Ricci flow, okay? Actually, you have a stochastic version of the Ricci flow. So you have the Ricci flow plus a stochastic noise. So the Ricci flow, I will not introduce it here. Eventually, I will have a slide later to say something, but it's been proven, introduced by Hamilton and then proven to be useful and actually determinant by Perelman to prove the Poincare conjecture and ubiquitous in many aspects of physics, let's say from string theory and running of nonlinear sigma models like the same Nambu-Godo action, but also, I mean, in more in general for QCD and more in general, let's say, also for high derivative theory of gravity. And indeed, the same Moravec gravity can be seen as a particular regime out of equilibrium, let's say away from the infrared equilibrium regime which provide the Einstein reduction, as a particular flow, okay, RG flow, which is regulated by the Ricci flow itself. So in this, with this choice of lambda equal to -1 in the Witt metric, what we have is that the equilibrium limit, which is in the box equation, the first equation in the box, the one in the brackets, are indeed the, let's say, Einstein equation, but complemented, written in terms of the Ricci target, okay, which is the part that encode the energy momentum tensor. And then you have your noise, which here is written in terms of noise, which is white noise. But pay attention to the fact that, I mean, you can choose a different kind of noise, for instance, colored noise. Then in that case, you would have to modify the delta 4 over x. X is a coordinate on the manifold, on the 4-dimensional manifold. Okay, so these are the 4-dimensional coordinate in space-time. If you put there some kind of kernel, any kind of kernel, you will have a different kind of noise. For instance, a kernel which is something that is connected to, let's say, the inverse of the distance, okay, for the in space, for the space coordinate, that is a kernel that is responsible for the correct, let's say, limit, semi-classical limit, and for the collapse of wave function, as I will show you later, and is a color noise. So there is a zero noise limit that indeed provide for this Ricci flow, let's say a dynamics flow toward, let's say, a target fixed point that reproduce the dynamics of the Einstein-Hilbert action. And the point is that we have here also something that we want to understand is what is the meaning of this stochastic noise. As I was saying, the stochastic noise can be seen from an RG perspective, from Wilsonian RG perspective, as the remnant of tracing out very high degrees of freedom, okay, that percolate in the low energy dynamics, RG flow for degrees of freedom. So, and to do that, the best way is to consider indeed the Langevin equation with the Ito-calculus. The Ito-calculus, as I was telling you before, is introducing nonlinearities. Then you look at the associated Fokker-Planck equation, which is the last equation in the second box, and you basically look at the extremized, let's say, solution of the Fokker-Planck equation. And if you sorry, the stationary solution, I mean, of the Planck equation, if you look at the extremization of it, you will find that the extremization will not provide the Einstein-Hilbert, the Einstein equation from the Einstein-Hilbert action, but will provide an additional term, which is a gravitational constant-like term. This gravitational constant-like term basically relate and give the meaning of the square amplitude of the stochastic noise to be basically the cosmological constant. So the cosmological constant acquire the meaning, if you want, of the amplitude of noise, stochastic noise of a thermal bath with which these degrees of freedom are interacting out of equilibrium. And let's say that, okay, as you can see, there is also a complex factor that can be tuned to 0, but this complex factor is actually something which is connected to the evolution of the equilibrium and complex, which is something that, I mean, is very well known and actually numerically also evaluated and studied, for instance, by people in QCD, and I mean, for people who do a numerical evaluation, so should not be anything that give you any problem. Let's say that, I mean, the imaginary component actually is also a powerful meaning in terms of definition of the initial condition for the evolution of the system, as has been, let's say, investigated by Holger Nielsen back in the time in his work on the complex action theory. So, so now, I mean, it's we can inspect more in particular what is the meaning of this stochastic Ricci flow if we switch to the variables and we look at the Hamiltonian formulation. And we can see that basically the lapse and the shift vector now acquires a dynamics, and this dynamics is acquired with respect to the thermal time. the generator of this dynamic will be still the super Hamiltonian and let's say Hamiltonian, let's say super momentum generators of the time and space diffeomorphism of the theory. But you have, let's say now an extra dynamics. And what is relevant is the fact that this, let's say, kinetic term is inducing a dynamics out of equilibrium for the lapse and shift vector. And the other point is that with these multiplicative ansatz, the stochastic noise disappear from the equation for the shift vector, which is one of the reasons why these ansatz of stochastic, let's say, of scalar multiplicative noise, we think is interesting. Is interesting because it is connected indeed with something which is basically a dynamics in which the dynamics of the shift vector is not affected by the stochastic noise itself, but as we know, these are the components that will basically, and I will show you later, will basically give you in the dynamic limit the Navier-Stokes equation, which is the semi, let's say, classical limit for gravity. Another point is about the meaning of this thermal time, which is connected to basically length, let's say, transformation, okay, scale transformation. And basically this is connected to a conformal transformation. So you can see this, this flow in a geometrical picture as really a conformal transformation by upper surfaces. And this also introduce basically a way in which you have to look at this evolution of the system. So you have 4-dimensional, let's say, 4 coordinates, okay, and you have a time, which is a proper time that you can define for the theory, but the proper time is not disconnected to the thermal time, but the two are related. The two are related through the norm of the normal to the hypersurfaces that now depends on the stochastic time because it grows, since basically the hypersurfaces can follow the dynamic out of equilibrium, which is the heat flow dynamics in terms of the thermal time. And the fact that, I mean, this can be connected to this is also can be seen if you consider the fact that derivative of the metric tensor, which depend on the coordinate, but also depend now on the thermal time with respect to the thermal time, can be recast in terms of the contraction of the normal with the covariant derivative of the metric. That would be 0, of course, if the metric, the covariant is the covariant derivative is metric compatible. So it means that it cannot be metric compatible. You have to use a connection which is a connection with the torsionful component. So it's a projective connection. This projective connection introduces interestingly introduces a cosmological constant indeed, and is related also to torsional degrees of freedom. And this torsional degrees of freedom, as you will see, I mean, it's from the lambda 2 term, not in the lambda 3. This is a mistake. There should be lambda 2 and lambda 4, sorry, in the last equation. But anyway, so this introduces also some specific, let's say, extra degrees of freedom with respect to the part which are the metric compatible ones. So as you can see, the splitting is in the very first equation. The metric compatible one, the Christoffel symbol, and then the torsionful one for this projective connection. So something that means like that, I mean, I will not show here, but basically these torsionful component are the one that usually are basically subtracted from the Ricci flow in order to solve it numerically through the Turk trick, okay? But actually these are extremely relevant because these are the degrees of freedom out of equilibrium, and they encode a lot of physics inside. For instance, this can be relevant, I mean, this can be understood easily if you consider the perturbation around some background, which is a curved background, de Sitter, anti-de Sitter. In a particular gauge that you can take, okay, in which you consider a traceless transverse degrees of freedom for the for the metric of perturbation, okay, basically the graviton degrees of freedom, you will see that the second perturbation of the Einstein interaction around the zeta and the zeta background without max degrees of freedom will correspond to the propagator of the graviton, which has a mass which is related to the cosmological constant in the zeta and the zeta, and that it's okay. But then you will see that there is a ghost. And of course, this ghost cannot be physical. Indeed, at equilibrium, we have a symmetry, which is a conformal Killing vector that allows us to gauge to zero the second term in the, let's say, equation in the second box, okay? But of course, out of equilibrium, this symmetry is broken, so you cannot do that. So this term becomes dynamical. And actually, this term is a matter of another study that I'm doing about cosmological implication at the inflationary limit. So coming back to the Hamiltonian analysis, as I was saying, you have basically the dynamics of the Navier-Stokes equation, which is related to the second box, okay, to the dynamics of the shift vector. For the lapse function, this is connected to a relaxation of equilibrium on a certain system that basically generate also the, let's say, evolution of Lagrangian equation for wave functionals. Okay, so this is connected basically to the relaxation of the wave function. And if you want to be a little bit more specific, the noise term cancel out, as I was saying, which is relevant here, and is one of the byproduct and the justification for this ansatz, okay, of multiplicative stochastic noise. So as you know, the supermomentum is connected to the covariant derivative of the conjugated momentum of the trimetric, and let's say non-relativistic limit with let's say low viscosity limit through, I mean, the connection with the energy momentum tensor. This is exactly, let's say, because I mean the Einstein equation, you see that this is connected to find the Navier, I mean the Brown, basically the covariant derivative of the Brown-York stress tensor, and this provides then the let's say divergent part of the Navier-Stokes equation equal to zero at equilibrium and the incompressibility constraint. So this is at equilibrium, but if we have the left-hand side of the first equation on these slides, you have basically a term, which is, let's say, a noise term, that I mean cancel out, but we have, let's say now, let's say, a term that introduce, let's say, turbulent regime and introduce actually turbulent fluctuations that are intermittent in the way these are introduced in this equation, which is the left-hand side of the first equation, which, as I was saying, is drifting away from the, let's say, Navier-Stokes easy Navier formulation of the Navier-Stokes equation. So you have here production of vortices, okay, and you have a way to look at the dynamics of turbulences with intermittent noise, and also the way this is introduced with intermittent noise also enable to do some bridges between the multifractal hypothesis that has been introduced by Parisi, Benzi, Vulpiani, etc., and other people for general relativity. Okay, so let me say that I mean it's another point which is very relevant is concerning the dynamic of the fluctuation and the kind of probability distribution that is here fulfilled. And here is very relevant, again, the fact that we're using the Ito stochastic calculus, differential calculus. And the point is that if we, this has been proven by me and Matteo for the case of radial symmetry, but I mean, it can be proven also for FRW geometry, okay? And the point is that basically, in a quasi-equilibrium limit, which for the form of the metric, which is in the first line, is the quasi-equilibrium limit, as you know, is nothing but one of the Einstein equation of motion. So that means close to the Einstein equation of motion, in which this constraint holds. You can write your system of stochastic, let's say, differential equation that fluctuate around along, let's say, the equilibrium limit, and you can recast all the dynamics just in terms of one variable, which is basically what is called the separation variable or height variable that define the Carda-Paris-Young equation. So the Carda-Paris-Young equation is an equation for a probability distribution which is not the one of Brownian motion, is different, and describe particular system like particles and polymers that interact in randomized systems, and also has been very much seen to be connected to the Barger equation, which is nothing but the easiest way of, let's say, reproduce intermittent statistics that is similar to the one that you have, for instance, for turbulent, let's say, Navier-Stokes equation. So this has a class universality which is Z/3/2, and as I was saying, has been deployed and for their physical consequences, one of which is to describe the evolution, the growth of surface. Okay, this H is related to this variable that model, let's say, the surface height. And as I was saying, I mean, intermittency is very much related to this picture. Okay, the point is that, I mean, it's with this you can do an analysis of the generation of gravitational waves that now can be addressed not only at the ring down but also, let's say, in a falling regime. And is a way, to study also low dissipation far from the horizon with no large stochastic noise that must be considered. Of course, I mean, there can be an important role which is provided, and this is all a work in process here, in, let's say, the dynamics of the propagation of the gravitational waves. So another important application of this is if we consider the mini space, which is nothing but, let's say, cosmological Freeman-Robertson-Walker, Lemaitre-Robertson-Walker. And in this case, as I was saying, the lapse function becomes dynamical. So is the other degrees of freedom that you have to consider out of equilibrium on top of the scale factor. But you have also the cosmological term that, as you remember, is generated by the torsional degrees of freedom out of equilibrium as well. And for this one, applying the rule of the stochastic Ito calculus, you find basically an evolution with respect to the stochastic time in which the variance enter, and the variance is basically the amplitude of the noise. So it's connected to the cosmological constant. But the cosmological constant in a simple model, like the one that we've been considering, which is a heuristic model, Freeman-Robertson-Walker, Einstein-Hilbert action in FLW with no matter, so is an unrealistic version of the universe because there is no matter. But in this heuristic, let's say, analysis, of course, because the square root of the cosmological constant is just Hubble, and then the inverse provide basically the age of the universe, and then provide also the time of expansion of the universe. So if you are looking, let's say, in the range of a redshift in between 1100, where we know that means, and let's say order 1 of the redshift, we know that it's the difference between the two measurements of the Hubble parameter is showing a discrepancy of 10%. So these at the order of magnitude can be achieved through this running of the cosmological constant. Of course, in this heuristic case with no matter, and now it's the case more realistic with matter is a matter of study with a student of mine, Jinglong Liu, and with, of course, Matteo and Luca Visinelli. So let's say that, as I was mentioning.
Excuse me, you have 2 minutes left? 2 minutes.
So I started at 15, right?
It's 40 minutes in total, right?
Yes. So I started at 15 and now is 52. So it's 37 minutes already. You're right.
Yeah.
Okay. So I will converge toward the end. So so this can be used to let's say look at the relaxation of the wave function, which is induced by let's say, interaction with the thermal bath, with its amplitude of the stochastic noise, which is connected to the cosmological constant. And this then can be used, let's say, using some relativistic semi-classical limit for the metric to write functionals, which are the functionals basically that describe wave functions of some systems with matter that, for instance, in our first analysis have been taken to be an ideal gas, okay? Is a good approximation because, I mean, as we know from Landau-Lifshitz textbook, the correction are I order in H bar cube. And interestingly, we can recover a master from the Langevin equation, a master equation, which is nothing but the Diauchy-Penrose master equation for the gravitational collapse of the wave function. And let me say that again, the Langevin equation for, let's say, the lapse function, which is the component that you have in the semi-classical limit, semi-classical metric, okay, that you use with n, which is related to the gravitational potential, okay, semi-classical gravitational potential, is relevant to achieve this result. Well, I mean, let's say skip this detail that are basically more or less the same detail as I was showing before for the cosmological constant, but you just repeat for the lapse function. And with, let's say, WKB ansatz for the wave functional, you arrive to identify what are these terms in the Diauchy-Penrose equation, and basically introduce an additional parameter, which is now the cosmological constant, as, let's say, amplitude of the stochastic noise in this picture. And let's say that from this, of course, you can switch to dynamics, which is nothing but the one, to a picture, which is nothing but the one of the density metrics. And then you can see that this evolution is non-unitary because, I mean, of course, is considering interaction with the stochastic noise, so with the thermal bath, but is trace preserving and is positive, so is of the same form as GKLS. So then we skip this, and just to say that, of course, this is so this is stochastic Ricci flow. You have a dynamics with the topology changes that, of course, are also relevant in the description of the ground state of physical system with matter that interact. And this topological way is nothing but connected to a different way to think in terms of, let's say, geometric phases, and can be applied in many contexts. And of course, has also an interpretation which is an holographic interpretation. But the relevant additional part is connected also with the fact that we can write and consider and study and follow, let's say, dynamics of vortices and turbulences in a new way, which is connected to change of topologies, which are induced by the RG flow and by the dynamics of this stochastic Ricci flow. This can be applied also out of equilibrium to describe algorithm connected to topological quantum neural networks. So basically, out of equilibrium version of let's say, models for topological quantum field theories. And this can be also applied, let's say, in several contexts, also in, this is my last slide, also in, let's say, condensed matter. For instance, here, I show a couple of pictures that have been taken by Filippo Boi for a work in collaboration also with Andrea Dazzi. And basically means here what we find is that the change of topology of nanotubes that is induced by basically the interaction with some doping, let's say, elements like sulfur in the case that we've been considering, follow a dynamics, which is a dynamics, an effective dynamics of a stochastic, let's say, Ricci flow, which is connected to the diffusion fix equation. So, okay, so I cut this because I think that more or less have been using also some extra minute. Thank you very much.
Okay, so questions? Questions from audience?
Hi, Antonino. I'm Leonardo. So I have a very simple question. Maybe I misunderstood something, but you said somehow the lapse function becomes dynamical, right?
Dynamical in the thermal time, exactly.
Not in T. So because I was worrying about more degrees of freedom that could be dangerous.
Is dynamical in the thermal time.
Okay, maybe it's not a problem.
Yeah, but in a certain sense, the thermal time is related to the proper time, as I was showing before. So you can have basically dangerous degrees of freedom from this point of view that are present out of equilibrium. Okay, these are present out of equilibrium. But the point which is interesting is the fact that, in a certain sense, this perspective is telling you that what you really look at the quantum level are the fixed point of the flow, which is indeed, I mean, it's the one that very well behave from the point of view also of the imposition of the symmetries, but also the one that do not contain the divergences. So, and indeed, I mean, it's one of the studies with BRST quantization done by Orava itself, intertwined between a phase which is a topological phase, okay, and the low energy phase. So what you quantize then are the fixed point of this flow, not the out of equilibrium one, because the out of equilibrium one, yes, you quantize, you may try to quantize, but basically they hold divergences, so they are pathological.
Okay.
So
Thank
it's in the holographic perspective, let's say the holographic boundaries are the one that are gauge invariant and are the one in which you may ask certain kind of question.
Okay, thank you. So due to time limit, maybe one quick question.
Maybe a very simple question. Normally the Einstein-Hilbert action still have the non-renormalizability issues, right? Here, your starting point is still the Einstein-Hilbert action. Do you have a similar issue when you're talking about the quantum theory?
No, the point is exactly the one that I was discussing now with Leonardo Modesto. The point that you don't want eventually to quantize the theory in one fixed point, which is connected to the infrared limit, but you want to follow the flow, and the flow may converge toward another fixed point in which the theory becomes topological, and then it's quantizable.
Okay, thanks.
Okay, so maybe let's go to the next talk and thank speaker again.
Thank you.
So next speaker will be Roberto Casadio. The title is Scales of Quantum Gravity and the Integral of Black Holes. Yeah, this one. Yeah.
Yeah, well, I'll try to be short. Where's the point? Oh, yeah. Okay. Okay.
Yeah.
This
will change the slides.
Down. Maybe you have to click there because it's not working. Okay. Okay. No. Maybe it's disconnected. Maybe like somebody took it. I can. Okay, I'll use the. I guess I'll use the arrows.
Yeah.
Okay. First of all, I'd like to thank the organizers for the invitation. And since this was the original plan of the presentation, since I'm the last speaker of the day, I'm sure we are all pretty tired and we don't want to be late for dinner. I'll probably cover just the first part, maybe a little bit more detail than I thought, and say just a few words about the second one. Now, it doesn't matter if you don't understand what the first part is or the second part is. I will explain in a moment. Let's start from something very simple, units.
I think this is an extract from Matt Visser's book, Lorentzian Wormholes, where he lists different choices of units that are used in the literature by different community. And of course, he calls the completely natural choice the one in which all fundamental constants are equal to 1. I call those the Newman choice because it doesn't let you check if you are making some dimensional mistake to begin with. What I like to use, and I will use through the presentation, is what he calls the semi-natural units. I'm fine with C equal to 1, but I will use the Newton constant equal to the Planck length over the Planck mass, and the Planck constant equal to the product of Planck length and Planck mass. The reason I'll explain in a moment. Now, first of all, what are the Planck length and Planck mass? We all know that. You have heard that a lot of times. This is usually, typically considered to be the scale of quantum gravity. But why is that? Well, you can put together those constants in a way that you get the mass and the length. That's not very inspiring. There's a little bit more inspiring way of getting there. Consider a particle of proper mass m and associate to it the Compton length, which is a measure of quantumness, perhaps, and the gravitational radius, which is a measure of how strong gravity is for that particle. If you equate them, put them roughly equal, factors of order 1 that don't matter, you obtain exactly that the mass is equal to the Planck mass, and therefore the Compton length or the gravitational radius is the Planck length, okay? Now, so that's why people think, usually, we think usually that that's the scale of quantum gravity. But why is that the scale of quantumness? Only in scattering processes, that's the scale of quantum. If you consider the hydrogen atom, a scale of quantumness, the Bohr radius, which is a couple of orders of magnitudes larger than the Compton length of the electron. Otherwise, if it were shorter, we would not be here, because the ultraviolet catastrophe of the classical electrodynamics would not be cured. And we know, we think at least, that there exist neutron stars that are quantum objects, kilometer size. So another property of that object there is that, a particle Planck mass, is that its compactness, defined as the ratio of the mass over size, is of order 1. To make it dimensionless, you multiply by the Newton's constant, which is length over mass, and you get dimensionless quantity. So let's entertain the idea that perhaps the scale of quantum gravity is not a length or a mass, but compactness of order 1. Okay, that's, well, it wasn't the starting point, it was a conclusion, but I can start from here. Now, what's the problem with this idea? It's physics, we should test it. The problem is to get to compactness of order 1 in nature, that's something we cannot do in the laboratory. An object of compactness of order 1 is a black hole, roughly close to be a black hole. We cannot build it in a laboratory. At present, we can just play with it theoretically. Until we find maybe primordial black holes that are smaller, I don't know. For now, the only black holes that we know exist for sure are order of solar mass, few solar masses at least. So what happens when a supernova explodes? We all know that. If the core is sufficiently massive, collapses, the horizon forms, presumably, everything ends up into singularity. This is the classical picture. Okay? To put things in perspective, a solar mass object would mean something of the order of 10 to the 57 neutrons, if you think it is just made of neutrons. If you don't like neutrons, use other particles. That number turned out to be quite large. If you trust the Bekenstein counting of gravitational excitations that you can associate to a black hole, you get 10 to the 76, because that's the square of the mass in unit of the Planck mass. This would be the topic of the first part of my presentation. That of the second one, maybe I will not get there. We'll see. I don't want to get you too tired.
Clearly, these numbers cannot be handled. There's no way we can model in details an object this complex, besides the fact that we cannot build it in a laboratory. So what do we do when we face these kind of difficulties? What we do in life usually, reduce and simplify. This is what we do in physics all the time. Recently, I think Rovelli and Tiemann use this as a definition of the relational approach. I think it's just physics, okay? This is something we are forced to do when the complexity is too large. In this case, reduce and simplify means I will consider the Lemaitre, Tolman, Bondi, Oppenheimer, Schneider model of gravitational collapse. What is it? It's a model in which the collapsing object is made of dust particles. Dust means particles that only interact gravitationally. It's quite unrealistic. And they are arranged in a perfectly spherically symmetric configuration, which is again completely realistic. But at least it allows to do some calculation. Okay? So the reduce and simplify means reduce enough to perform some calculation and reach some conclusion. But the point is that I will try to do that without any other approximation. Please.
Do you have any intriguing explanation for why we haven't found neutron stars beyond the 3-4 solar masses?
I don't know that. I don't know that. I have no idea. I never thought, I mean, it's not exactly the topic. But maybe, anyway, dust means, we know from the early days of Einstein's and collaborator works that for dust, the Einstein equation is equivalent to the geodesic equation. In other words, dust follows geodesic in the geometry that the dust itself generates. So we can treat this ball of collapsing, or ball of dust, let's say, by in fact analyzing the radial dynamics of dust particles that are in the ball. In particular, we can start by considering dust particles that sit at the surface of the ball. It doesn't really matter where, because I want to preserve perfect spherical symmetry. So whether the particle is here or there doesn't change. It's, of course, a large simplification. Everything is described in terms of radial dynamics. The dust particles sitting there would fall classically along a geodesic in a Schwarzschild metric with a mass parameter that is essentially equal to the total mass of the ball. Actually, would be the total mass of the ball minus the mass of dust particle at the surface. Given the number I showed you before, it doesn't make a big mistake if you consider the total mass of the ball. Okay. Now, this radial dynamics can be recast in the form of an Hamiltonian constraint. I call it Hamiltonian constraint because it's equivalent to the Einstein equation, as I told you before. And if you look at this expression and forget for a moment about this, this would be just energy conservation in Newtonian physics for the radial motion of your dust particle, right? And I can easily quantize because that's like the hydrogen atom with zero angular momentum modes. I don't want angular momentum mode to begin with because, again, I don't want to spoil spherical symmetry. There is, however, that expression that makes this Hamiltonian constraint different in GR from the one in Newtonian physics. Besides the fact that, of course, R here is not the radius of the sphere, 4 pi r squared is the area of the sphere, and the time involved in this dynamics is the proper time of dust particles, not the absolute time of Newtonian physics. But those are, let's say, minor differences for what I'm going to say. We can easily solve this. It's the spectrum of the hydrogen atom, okay? L equals 0 modes. And we can find the, let's say, call them energy eigenvalues. And we can compute the expectation value of the radius of the ball, which is given by the position of the dust particles at the surface in this discrete spectrum. Okay, yeah, that Hamiltonian, if I quantize it, allows for a discrete spectrum. Okay. And this is what we obtain. Now, if we forget again about this expression that comes from general relativity, we just look at script E as the sort of the energy or the eigenvalue of the Hamiltonian. This spectrum starts from, of course, n equal 1, like in the hydrogen atom. And if you compute the expectation value of the radius of the ball in that ground state, you get something like that, which is a tiny fraction of the Planck length, which is essentially a singularity. Okay? However, this comes from general relativity. We need to remember that. The only difference is there. The quantity that is conserved according to general relativity is this block E, that would be the momentum conjugated to the time coordinate of the dust particle. And we want it to be well defined if this has to come from general relativity, not from Newtonian physics. You might not agree. I think it should be well defined. If we require that this quantity is well defined, then we have a constraint on the quantum number n that must be at least equal to that minimum value. So there is a new ground state, which is not n equal 1, but n equal to this quantity. And if you plug in solar mass and proton mass or neutron mass, this is very large, 10 to the 19th or something. And in fact, the expectation value of the radius of this ball, okay, I'll go switch here, it turns out to be a fraction of the gravitational radius. So you go from essentially singularity, Newtonian physics, quantized Newtonian physics, to a macroscopic core, macroscopic ground state in case of general relativity. Okay. Now, of course, this model is extremely simple, extremely simplified. I told you it's dust, but the dynamics is GR. Okay, it's not, there's no approximation. It's full GR for this particular model. You go from 0 to something macroscopic. I find it difficult to believe that if you improve the model, you can go back to the singularity. I would find it very, very strange. Okay. Now, you can improve this model, in fact, by considering different layers, which means considering dust particles at different radii. The radial dynamics is defined by a similar Hamiltonian. The only difference is the mass function here would correspond to the amount of mass inside the position of each particular dust particle. Spectrum is similar. You get similar result. Again, if you insist in requiring that this blocky is well defined for the quantum state, you get, again, the same result as before. Of course, these ground states for dust particles that lie closer and closer to the center will be smaller, but never equal to 1, essentially. Of course, in all of this argument, I'm assuming that the number of dust particles is extremely large, 10 to the 56 or similar, which, by the way, makes a spectrum. We know what the solutions are, right? We can write the wave function explicitly, formally, but imagine a Laguerre polynomial with 10 to the 19 nodes. You cannot even deal with it numerically. So, of course, you have to play with simple cases, simpler cases, so to speak. Okay. Now, again, in the case of a let me go here. What are these MI? I mean, can I choose them arbitrarily? So, for example, in the Lemaitre-Tolman-Bondi model, the mass distribution is arbitrary. Dust simply collapses and the profile remains the same. Here, can I find a condition that gives me a profile without assuming it? Well, an idea that I like is that the thickness of each layer, so I have a wave function for particles that sit inside a certain layer. That wave function gives me an uncertainty in the area of coordinate. And I require that the thickness of that layer is of the order of the uncertainty that the wave function is giving me. It seems like a natural consistency condition to impose. And this, in fact, fixes approximately fixes this discrete mass function. So I can find a configuration, self-consistent configuration of quantized layers of dust. The outer radius is pretty much what I showed you before, and to be more precise, it's 3/4 of the horizon. So I could say this is probably a black hole because this core is mostly inside the horizon, although there's no geometry here anymore, to be exact. And if I play this fancy game of multiplying the quantum number for this ground state for the number of dust, total number of dust particles, I get an integer which is proportional to m squared, which looks a lot like Bekenstein quantization. I mean, it's funny how it comes out in different ways. Okay. Now, this is an example in which there are, I think, 3 layers. These are the wave function of 3 layers, and of course, very far away from a solar mass. You see the number of nodes is small there. So this, for example, would be the wave function for dust particles sitting in the outermost layer. This is the second layer, that's the third layer. This approximation neglects the fact that there are overlapping between this wave function. So for example, a dust particle that classically would be in the outermost layer has a non-negligible, well, non-zero probability of being found somewhere here, and so on and so forth. So the actual mass distribution is quite difficult to determine more precisely. We are still working on it. We can only do it numerically. Now, a few properties of this strange dust core. Energy, in quote, spectra, actually the quote should be in energy. If you compute, of course, beside the ground state, this, let me call it the general relativistic ground state, in which the quantum number is very large, there are also excited states, right? Okay, you start from that value and you go up to infinity, if you wish. Now, the difference in this Hamiltonian energy, which you can think of as internal energy, sort of, between 2 nearby states, when n is of the order of the ground state value, is given by that expression there. You might recognize something that looks a lot like the Hawking temperature or the energy of an Hawking quantum. It's very small. Solar mass, this quantity is extremely small. So it doesn't cost internal energy, basically, for a dust particle to get excited, or very little internal energy to get excited from the ground state to a slightly excited state. And there are slightly excited states that are still inside the gravitational radius. So from here, you get that there is a degeneracy, if you wish. Beside the ground state, I can consider many excited states, order of, in fact, you can estimate it, m squared, excited states that are still inside the, would be horizon. And maybe you can consider this degeneracy as justifying or explaining the usual black hole entropy. However, if for those 2 states, n and n+1, you compute the difference in block E, which would be the difference in energy that for those 2 states if those particles were at infinity. That would be the energy measured by an observer at infinity. This is Planck mass, very large. Now, when I attended a couple of presentations by Viet Valley about these saturons, he said that saturons are these bound states in which you can think as being composed by modes that are in the bound state are separated by a very small amount of energy, like here, but if they were free, they would be separated by a very large amount of energy. I think this is a realization of that idea. Also, in this model, we are breaking, if you want, radial translation invariant, of course, but not rotation invariance. So in principle, you could also add modes with little angular momentum, not too large, because it's too large, the thing starts spinning and the construction fails. But if you add modes with small angular momentum, again, you have a degeneracy, and you can estimate how many of those modes you can add. Again, it's order on a square. And this is exactly the idea that Gia has about Saturons. So I think this is sort of a realization of Saturons. I think I found this before it started talking about Saturons, but anyway, it doesn't matter. Maybe you don't like the idea anyway. Other properties. This model has been studied quantum mechanically many times, besides the classical solution that is known since the days of Lemaitre. Typically, what people do is, what people have done is consider wave packets and the evolution of wave packets to describe the collapse. I'm not attempting at describing the collapse. Okay? In fact, I focus on this discrete spectrum. When people study the collapse using wave packets, this quantized version of this model, what they find is that there is a bounce. In other words, the ball will collapse, never reach singularity, but bounce and re-expand. This is what Rovelli calls a black hole to white hole transition. It's something that classical cannot happen, but it was found before in these simple models by Ajcek, Kiefer, maybe even others. It's pretty solid result. The size of the bounce in that description, which starts from the Einstein-Hilbert action, follows the canonical procedure for a mini superspace that you obtain by fixing the metric in a certain way, the size of the bounce is never clearly derived. In my description, of course, the size of the bounce cannot be smaller than the ground state, because you have to think of those wave packets, the superposition of this discrete spectrum, and therefore you cannot get below that. So this is a prediction sort of the size of the bounce. I want to highlight the fact that this strange spectrum is a consequence of nonlinearity of general relativity given by that. It's very simple nonlinearity, E squared. Okay, if you forget about that again, you are back to Newtonian physics and you get anything like this. But this is the only trace of general relativity left in the model, if you wish. And I don't think you should throw it away. Otherwise, you're doing different theory. And while you can make connection with other ideas. Okay, let me see. Oh, okay. Now, I'm not sure. Wait, let me go back here. In this description of the bounce, in particular in explicit calculation done, for example, by Ajcek, I remember collapse of a shell of light. It is clear that near the bounce, there is not necessarily a notion of geometry. Everything becomes fuzzy, quantum. In fact, that's what you need to make this transition to from black hole to white hole. That's you can think of a sort of tunneling, quantum tunneling, right? So I'm not sure for this, we call it dust core, or ground state of the dust core, it makes sense to talk about the geometry to begin with. Geometry is a tool that we use in general relativity to describe the motion of test particles, and therefore gravity in a sense, but inside the core, nothing moves. In fact, if I build this ground state using the minimum value of the quantum number for all the particles, the radial position of the particles doesn't change. But the radial position inside the horizon would be a time variable. So it's like the thing is frozen in time. Does it make sense to talk about geometry? Again, I'm not sure. I have several reasons not to think so. But if we insist in introducing a geometry, we can do it. From the discrete approximate mass function that I determine self-consistently, you can infer that you can approximate it as a continuous Misner-Sharp-Hernandez mass function, which is linear in the radial coordinate. That would correspond to an energy density that goes like 1 over r squared. And of course, the Ricci scalar would go like 1 over r squared as well. So it's not, if you insist in the geometric description, it's not technically regular, but it's integrable. A behavior like this is perfectly compatible with the fact that I can think of the energy density as the square modulus of the wave function. And my wave function in near r equals 0 behave like that. They are perfectly integrable. That's why we call this kind of geometry integrable singularity. Again, the Ricci scalar goes like 1 over r squared. So technically diverges, but diverges in a mild way, because when I integrate it with the volume measure, I obtain something finite. In fact, I didn't put it there, but the total Lagrangian for the system is just a mass, as you would expect. So it's perfectly finite. Okay, that would be the first part. So the picture is a bit different now, the picture of the collapse, if you believe this description of the ground state of the dust ball. Of course, it's a bit difficult to describe the process of collapse, but I can imagine I have star, solar mass, few solar masses. It collapses. It doesn't go into a point-like singularity, but into a core with those properties, and horizon forms. Now, does it really form? It could be even worse. Yeah, it forms if it is dust. Okay, I showed you that the radius of the core is 3/4 of the gravitational radius, so I can imagine that the horizon really forms. But there is no angular momentum, there's no pressure in this model. I have no idea what pressure, which means other interactions between the particles. I have no idea what the pressure would do. It's very difficult to understand non-perturbative what the pressure does, because on one hand it pushes things out, on the other hand it increases gravity. So until I find a way to include it, I have no idea what it does. Angular momentum, perturbatively, I have a clue. If the angular momentum is small enough, I can still trust this spherically symmetric configuration. The angular momentum does two things. It increases the size of the core, centrifugal force, and reduces the size of the horizon. So there's a value of angular momentum for which the object never becomes a black hole. It remains horizonless. Okay. Fermions, essentially, because I assume that the thickness of each layer is given by the uncertainty relation. So it's essentially, I'm using fermions. That matter is usually made of fermions, isn't it? Okay. You can say that, yes, I am enforcing some sort of Pauli principle. Is there a problem? Okay. Oh, I can use it now. Oh, okay. Okay. Now, I don't know how much time I have, really. 10 minutes. We are not going to be late for dinner. So I'll briefly flash. That's a stretch. I'll briefly flash something about the second part. In this quantum description, there is no geometry anymore. Really, I'm only quantizing the dynamics of dust particles. And it's like I have integrated out the geometry, or we can consider it in different ways. How can I recover a quantum geometry? Because the idea now is to recover the Bekenstein area law, for example, more explicitly. If the situation is what I showed you before, that is, the collapse ends into that core. And I want to describe the geometry generated by this core using some quantum physics. Of course, not full quantum gravity, because I don't think anybody can do it. I want to do it non-perturbatively, although simplify and reduce, okay? Simplify and reduce, so I start from what kind of geometry I expect that core would generate. If it was classical, Schwarzschild de Sitter. Why Schwarzschild de Sitter? Because we live in an almost de Sitter universe. Okay? And this plays some role, but it's minor. So I'll show you just at some point why I want de Sitter. Fundamentally, I want Schwarzschild outside. Schwarzschild, I write it in particular reference frame, the one that is more convenient. And therefore, all I need to do is reproduce in my quantum theory this function here. Okay. Again, it's a very reduce and simplify approach. How do I get there? Basically, I want to reproduce this geometry as a mean field of some quantum operator on a suitable quantum state. I want to see if that quantum state exists and if it gives me restrictions. So that's why I choose the simple form of a Schwarzschild de Sitter, but you can forget about de Sitter. Focus on Schwarzschild, because then I only need one quantum variable that I want to reproduce as closely as possible that quantity there. And I do quantization as I know how to do it, Fock space. So I need one quantity, phi, I call it phi, but that phi will reproduce the non-trivial part of the Schwarzschild metric. And of course, I need to find the normal modes, define the vacuum, and so on and so forth. So how do I quantize that quantity? Which wave equation do I use? Well, I use the wave equation in a Minkowski space-time. But the Minkowski space-time that you see here is not the Minkowski space-time that we use to describe physics in a freely falling frame. This is global Minkowski. So this is Minkowski in a universe that doesn't contain anything. Of course, it's not our universe. The fact that it doesn't contain anything means that you can add as many dimensions as you want, because there's no difference between them. You can have 1 time, 10 times, it doesn't matter. There's no clock, no rod, there's no matter, no nothing in there. Non-perturbatively speaking, if you add something, the geometry must respond. So if you have exact Minkowski, global Minkowski, means you have nothingness. So my vacuum for that quantity is nothingness. Okay? And then you can decide, depending on the geometry you want to reproduce as a mean field, you can decide which modes you want to turn on, which excitation you want to turn on. Those excitations will reproduce. I will require that they reproduce as closely as possible the geometry that I want. This is the only way we know how to quantize things, I guess. So in particular, I want a spherical symmetry, perfect spherical symmetry, forget about angular dependence. The time is there, but I could have killed it from the very beginning. It's a static configuration. I just use it for, defining the usual creation and annihilation operator associated to, I treat phi as a sort of scalar field. It's not a fundamental scalar field. Perturbatively, that would be the longitudinal mode of the graviton that generates a Newtonian potential, but I don't want to think of it in perturbative terms. It's just the degree of freedom that I want to keep alive to describe the geometry I want. Because if I keep more, I don't know what to do. Okay, and then I require basically that the quantum state of interest is a coherent state. Because I know if I take expectation values of my quantum variable on a coherent state, I minimize the uncertainty and so on and so forth. That's the closest thing we know in quantum physics to classical configurations. Now, the requirement that the coherent state is well defined, one of the requirements is that this ng here, which you can think of vaguely as the total occupation number with respect to the vacuum that is nothingness, be finite. Okay, this is condition that must be satisfied, otherwise the coherent state does not exist. And this will place some constraint. Thinking in terms of occupation number, I'm not sure it's correct. Definitely, this is a measure of how far the quantum state that we are interested in is from the vacuum. You can consider it a measure of distance from the vacuum. Now, you want to reproduce that function there with the expectation value on the coherent state. If we compute the normalization or total occupation number, there we find something that diverges in the infrared and the ultraviolet. The infrared divergence is because, well, if we live in the sitter, in fact, we just get to the Hubble radius, so we can cure easily the infrared divergence. But if the black hole existed for 1 million years, you know, you cannot have that geometry farther than 1 million light years. So it's okay. And this is not particularly interesting. The ultraviolet divergence is more interesting. This comes from the fact that I would require this geometry all the way to r equals 0. But if I have a finite size core, I cannot go up to there. So I can, in fact, place a cutoff, being sort of agnostic to the details of the core. I place an ultraviolet cutoff, which is roughly the inverse of the size of my core. And this regularizes the coherent state, makes it well defined. And in particular, the leading dependence on this Nn of the mass is m squared in Planck units. So I'm sort of recovering the Bekenstein counting. Of course, there is this logarithmic function of the cutoffs that depends on the fact that I'm using sharp cutoffs. This is an artifact. I could do better. The point is to make it finite. So to make the coherent state well defined, I need to change this geometry in the infrared and in the ultraviolet. That's a message from quantum physics, if you want. Okay. And I guess I have to finish here.
You have to give something.
All right.
That was.
Yeah, I went to sleep. Okay. Anyway. That's okay.
It got heated up.
Anyway.
Yeah. Without any more. It will come.
Well, I can just say one more thing, and I'm done. Now, if you now go back and take the expectation value of this quantum variable on that coherent state, you get a quantum corrected metric. The expectation value will be different from pure Schwarzschild, of course. And this quantum corrected metric has the same feature that I showed you before for the metric inside the core. Namely, the Ricci scalar goes like 1 over r squared. So it's integrable. And another nice feature is that it doesn't have any inner horizon, which I think it's a sign that maybe this configuration is more stable than so-called regular black holes. And I could proceed with some rotating cases, but I don't think I want to go there. So putting the two things together, in the first part, evidence, I don't know if I can call it evidence, suggestion that the collapse doesn't end into a singularity, but in something macroscopic, possibly even not a black hole, but that's a bit of a stretch. And this is pure GR. There's nothing more than GR. There's no quantum correction coming from integrating a loop of matter fields or whatever. Very simple GR. The second part, reconstructing a geometry that is somewhat compatible with that core. We get that the very existence of a quantum state that reproduces a geometry requires the core to be finite size, the ultraviolet cutoff. And maybe quantum physics gets rid of singularities and all the problem like it does with the hydrogen atom in electrodynamics without the need to change the actual dynamics. That's my final message. Thank you.
Thanks for the very interesting talk. So I'm not sure I understood the discussion about geometry. I understand you are the whole construction is in flat space, there.
No, no, where? Which construction, sorry?
First part.
In the first part, there's no flat, what do you mean flat space? No, sorry, the dynamics that I'm using is full GR. And the metric that generates that geometry is far field. What do you mean relativistic, non-relativistic? I'm not sure. That's the Hamiltonian constraint written in specific reference frame. It's the same stuff that Antonino was showing, the Hamiltonian constraint. You can choose your gauge and quantize there. Canonical quantization, you have to choose a gauge. You have to choose time. Okay, yeah. That's pretty standard. There's no flat space whatsoever there.
I see that. So the ground state be also below event horizon.
Well, that's again, if I need the second part to talk about geometry, because in the first part, the geometry is lost.
Yeah.
In a sense. It's like working with a mini superspace. If you are familiar with mini superspace, you know, you take the Einstein-Hilbert action, you fix the metric to be a certain form. So basically, you end up with an effective, let me call it effective action for the degree of freedom that you want to describe, because it's your choice. Where is the geometry anymore there? You know, it's lost.
So that was the reason why I'm curious to ask you if you can have ground state below the gravitational horizon, then what does it mean that particle in the case will escape it, basically be quantum excited to
No. Wait a second. Well, there is a probability for particles to get out. This is pretty much almost the Hawking effect. But otherwise, no, you cannot get out. Everything is frozen there. You have to give energy to the particle too. And in the end, you can never give it enough energy. I'm not sure. And how can it escape? It's frozen. I mean, if the dust ball is in the ground state, it doesn't evolve. It's frozen there.
you get inside.
Oh, to excite it, you have to interact with it. Interacting with it means adding something to the model that is not in the model to begin with. So you should redescribe it from the very beginning. I mean, this is non-perturbative, okay? If you think perturbatively, it's a bit dangerous. Whenever you add something in GR, because of the equivalence principle, you are modifying the geometry, you are modifying everything. But thinking in terms of perturbation, sometimes it's particularly when you have objects of compactness of order 1, it's quite dangerous. You see what, I'm not sure I explain myself. For example, here, everything is frozen because you only have dust, and dust doesn't evolve in that core. There's no clock that ticks, because the only quantity that could act as a clock is the dust itself. If you add something else, you are not just perturbing the state. You have to repeat the construction from the beginning, add interactions, pressure, loosely speaking. And honestly, I'm not sure how to do that, because pressure is a nightmare, even at already at the classical level. Introducing interaction non-perturbatively, I'm not sure how to do it. Okay, but no, there's no way this stuff can get out unless something drastic happens. Two of these objects collide, maybe, merging. Photons. Yeah. Oh, photons were studied by, I mentioned Eychek and Kiefer long ago. They bounce off. So there's a transition from collapsing to expanding. But of course, in that description, well, photons were not real photons. They were massless shells. And there was no no friction, no loss of energy. Yeah. Yeah, but wait, classically, these are there. These are there. Yep, are there. I would say that the geometry has memory of what generated it. So the whole problem with information loss is not even there to begin with. Yeah, but again, this is a very simplified model. Photons, how do you create a black hole with photons? It's, yeah, in principle, you can do it. But how do you? Sorry?
Was called the black remained of photons.
Okay. But in nature, can it happen? You know, it's like the ultraviolet catastrophe in electrodynamics. It doesn't happen because the electron is light enough. The theory would admit it for like heavier particles, right? So.
More questions?
No.
Okay, now let's send us
Dinner time. Dinner time.
I would like to ask a question. You get this, those are attributes for different.
Yes, these are wave functions for dust particles in different layers.
You impose the potential wall.
No, there's no. Oh, because that's what my Hamiltonian tells me. That's the normalized spectrum, like the hydrogen atom. I impose that the quantum states exist and are well defined. That's all, like in the hydrogen atom. No. There's no Newtonian potential. The potential is the one from general relativity. Sorry. You know, that the dynamics of the radial dynamic is given by that expression there, and I can write it in terms of an Hamiltonian. And I quantize it. It's uniquely defined by GR. This is the equation for radial geodesics in GR for that case of dust, and it's equivalent, as I said, to the Einstein equations. Of course, there's a choice of variables or coordinates, if you wish, which is convenient. But in canonical quantization, you always have to make a choice. Then you could make different choices and see if you can do it in different coordinates. Probably you can't. Okay. That's the problem with GR, quantization of GR.
Okay, so maybe we can send more instructions to the conference team and then let's send the speaker.
We will start in 10 minutes, yeah? The dinner. There are students there, all of them, because we say do a lot of efforts. The longer you go, the less you have. Very simple.